Morning, Axel. Can you hear us?
Yes, I can.
Great, thanks. Can you just
Axel, can you hear us?
add me as a co-host, please? Test, 1, 2, 3. Second mic, test, 1, 2, 3.
All right, good morning, everybody. Welcome. So a quick announcement to all the speakers, virtual and in person. If for some reason you do not want your talk live streamed, please let us know beforehand so that we can adjust our tech here to avoid streaming your talk to YouTube, and then also, obviously, then also recording it. So let us know well in advance. We do have a break at 10, so come up then if you want, or write us on Slack. Right. Well, as I mentioned, good morning, everybody, and welcome, especially to those who came far to be here. I don't think our first speaker needs much introduction. Please welcome Steve Plimpton.
Thanks, Meg. You hear me okay? Okay. So it's great to be here. It's great to see all of you. My talk is What's New in LAMMPS, kind of try to highlight some things that have happened in the last couple of years since our last workshop. So we do hold these every 2 years. I think this is the 9th one we've held, most of them in this facility here. But this is our first in-person since pre-COVID 2019. So it's exciting to have people here, and yesterday for the tutorial. We're still doing it virtual, so welcome to the people that are joining virtually as well. We're glad to have you. Since we are in person, though, I wanted to give at least a little applause or some kind of pseudo award to people who've traveled from outside, far away. Has anybody here who's come from outside the US? Okay, I'm going to ask you what country? Austria. Okay. Was one back there? Japan. Okay. Some others? Peter? Okay. Anybody else? Okay. I think Japan wins the prize for the furthest travel. So thank you for making the effort to come. All right. So in the last 2 years, we've made an effort to grow the LAMMPS development team. We now have 10.5 people. I'll explain the half in a moment, but they're from a variety of institutions. These are just pictures off the web page, as big as I could make them on this slide, from Sandia, Temple University, Los Alamos, CMAP, Stevens Institute of Technology, and University of Chicago. The reason I said 10.5 is because I retired a couple of years ago, so I'm only counting myself as a half person since my brain is slowly slipping away. But it's still nice to be part of this group and community. So give you a little bit of developers' perspective on LAMMPS. We meet once a month to discuss various tasks and directions. There's a developers breakout tomorrow afternoon that's really a general session everybody's invited to. If you want to have some input into LAMMPS, suggest features, suggest things that you think would help the code or help you in your research, that's an opportunity to chime in and give us some feedback. Or you can always send an email to developers@lamps.org, and we look at those and try to respond. So LAMMPS as a code is maturing. It's been, I think, 21 years now that it's been an open source code. And so we're now doing basically one stable release a year where we try to do as much testing as possible, make sure we've got everything ironed out that might cause problems, although we still patch it sometimes going forward after that. And we do 3 or 4 additional feature releases where all the pull requests that have been submitted and merged in the last couple months get released. And so we try to test those as much as possible, though not as much as the stable, and make that all a good experience for users. We're spending, as a development team, I would say we're spending some more time now than we used to, now that the code is maturing more. We're doing some refactoring and modernizing of the code itself. It's a little over 1 million lines, so that can be an effort if we decide to change something fundamental. We do lots of different kinds of testing, regression testing against a suite of input scripts to make sure nothing has changed, or at least we understand why something had changed. Lots of unit testing. Axel tells me we're up to about 45% code coverage in the unit tests we have archived. And then we're now doing some automated Valgrind testing, which is more expensive to test for memory leaks and other things that might be subtle issues that we don't catch with just the output. So you might ask, if the code is maturing, what about the LAMMPS developers themselves? I'll leave that as an open question. You can be the judge of whether that's happening or not. Okay, so the scope of LAMMPS, it's primarily in the styles that it supports. As you probably know, we have pair styles, fixed styles, compute styles, etc. And all in total, those are kind of optional things, optional commands that users can put in their scripts if they build LAMMPS with support for that feature. About 1,300 plus styles now, and that doesn't include another 600 accelerated versions for OpenMP and Intel CPU and GPU. So close to 2,000 in that context. And that's a challenge for us to try to make all those features easily findable for the users and easy to use, hopefully. And so that applies to the code itself, to the documentation and the examples that we provide in the distribution. So if you have suggestions, it's hard to find things, or you have suggestions on way to organize that information so it's more easy for you as a user, that would be great feedback as well, whether today or in the future, or at this workshop or in the future. Just in the last couple of years, 450 merged pull requests. That's by 80 different unique contributors of those pull requests, 20 new fixes, 20 new pair styles, a dozen computes, and 5 new packages. So I'm going to highlight some of those today, but that you can always look at the GitHub pages on the different releases and see more details on some of the things that have been added. That also includes, or I should say in addition, 30 new Cocoa styles, which is the main way we have of supporting GPUs. And so GPU versions of various pairs, fixes, and compute styles have been added. And Anders Johansson is going to talk, I guess it's today, this afternoon, and give you an overview of some of the Cocos developments in LAMMPS. And Stan, one of our developers, will also be talking tomorrow at the breakout session and give you some ideas of where we're going with Cocos support and new changes that he's working on. Okay, so let's talk about 3 of the new packages I just wanted to highlight briefly. One is an APIP package by some folks in Germany. That stands for Adaptive Precision Interatomic Potentials. So precision in this context refers to the accuracy of the potential itself. And so the idea is to enable spatial coupling of a kind of a hybrid simulation where in some region you might just use a fast, quote unquote, low accuracy potential like traditional EAM, embedded atom method. But in another region, you might use an expensive, say, machine learned potential that's supposed to be much more accurate. And you can combine, the goal of this is to try to combine those two together seamlessly in one simulation. Another machine learning related package, we have several packages that start with an ML prefix that stands for machine learning. In this case, UF3, what they're calling an ultra-fast force field potential. And this is folks at the different institutions that are listed there. And so it's a classical UF3 potential, but it's derived from QM data. That's the machine learning part. But it's done using a B-spline basis set that allows the 2-body and 3-body terms to run quite quickly for speed. And then there's a new RIO package, which does not, I initially thought that's rheology, but it stands for Reproducing Hydrodynamics and Elastic Objects. Joel Klemmer, who's here, one of our developers with collaborators from Carnegie Mellon University, have implemented this and released it in the last couple of years. And it's an important point is you can use it in tandem with another package that Joel developed, the bonded particle or BPM package, to do interesting hybrid simulations. So I'm going to show you 3 movies that Joel gave me that I think are kind of cool. So this is an elastic balloon. That's the outer surface. That's these BPM particles. They're bonded together. Inside is a water-like fluid, SPH model. And so this little water balloon is going to bounce off a hard surface. And the colors of the water are a function of their vertical velocity. So you can see the kind of bounce of the balloon and the deformation and the waves that travel through the water. Okay, so here's a second model. This is now a brittle model with the BPM package on the outside. It's egg-shaped for a reason that'll be obvious in a moment. But it's enclosing the same SPH water-like fluid. And so now the coloring, especially of the particles in the shell, is going to represent damage, how many bonds have been broken between its neighboring particles. So you can see the egg crack and then the water flow over the edges of the hard surface underneath. Okay, One more movie. This is now a solid, but it's a column that's going to be heated on one surface, and a heat front is going to pass through the material and slowly melt it. The melted material is going to collapse down to the surface, and then as it cools on the surface, a kind of oxidized shell is going to form on top of the blob of melted material. So you can see that heat wave, you can see the collapse, and you can see the cooling on the exposed surface. I'll run that one more time. So the color now is a combination of the temperature and oxidation state of individual particles. Okay, so that again is the Rio package if you want to look and see information about how you can model things like this together with the BPM package. Okay, I'm going to highlight just on this slide a few of the new pair styles. So pair snap is originally a CPU implemented machine learned potential by Aidan Thompson and collaborators at Sandia. An Intel specific optimized version was created by Mike Brown when he was at Intel, and it's up to 4 times faster on an Intel CPU due to the optimizations. But I should say there's also Cocos versions of Snap that have been highly optimized for GPUs, and those can be up to 100 times faster than a full CPU node on an appropriate GPU. Pair Padone was implemented by Axel. Padone is a shortcut for the PMM-CS model, which combines a Morse term, a Leonard-Jones term, and a Coulombic term, all in one pair style. So if your model needs those kind of interactions together, you can look at that pair style. 2 more, there's a variant or a DPD with Coulombic terms that implements the short-range Coulombics with a Slater functional contributed by Eddie Barad. It allows you to do charged DPD particles, which are dissipative particle dynamics for a coarse grain model, if that's interesting to you. And pair hybrid molecular, something interested by or implemented by Axel. This allows you to do use different pair styles for intermolecular interactions between monomers on different molecules and a different one than an intramolecular model within the molecule. 2 more, there's a pair dispersion that uses a DFT-derived, what's called a D3 dispersion approximation energy correction that's due to Grimm, and that's implemented in a pair style if you want to use that same consistent dispersion model within the long-range interactions. And then pair LJ Pirani, this is what's called a generalized or improved version of Leonard-Jones interactions, which can be useful for some kinds of materials and mixtures. And so you can read about that and see if it might be appropriate for your science simulations. Okay, just quickly, a few details on a few new fix styles. Path integral molecular dynamics is something there's a basic fix for in LAMMPS where you treat different particles as a little ring of pseudo particles, and then you have different replicas which interact across replicas and within a replica. So there's a bosonic version of this that was implemented that allows you to do PIMD for bosonic or indistinguishable particles, which changes the algorithm somewhat. Pressure Langevin, this allows you to control the pressure as a barostat in a LAMMPS simulation with a Langevin stochastic barostat that was implemented by Germain, who's also one of our developers. Fix deform is a variant of the standard fix deform command, but allows pressure control to trigger the amount of deformation of the simulation box. So this is Joel and collaborators in the UK. For granular systems, this is nice because it allows you to specify a target pressure that you want the system to say to shear to or to elongate to, and that target pressure will drive the box deformation up to that point. Fix-av moments was implemented by Germain, one of our developers, and Sebastian Hutter. And like there's a fix-av time, fix-av, just a standard fix-av command for over time, for example, that gives you averages. This lets you do second and third, fourth moments of similar kinds of time series data if you want higher order moment information for analysis. And then finally, Fix GJF by folks at UC Davis. This is something that had been implemented initially as an option in Fix Langevin within LAMMPS, but they wanted to do a fuller kind of standalone version that included different options that Niels has developed in his group over the years. And so this is a family of GJ for Grombach-Jensen Langevin integrators that can be used or implemented and run in LAMMPS with this Fix GJF command. And for certain systems, this can allow you to do like a 5 times larger time step for a Lennard-Jones system. The downside, if you want to think of it, is it distorts the velocity distribution of the particles. So that part of, the particle attributes are a little distorted from what you would normally think of. But in terms of the motion of the particles, their coordinates over time, it's a stable system even with a larger time step. And then lastly, I wanted to mention a fixed set command, which we worked on, and it's kind of more a capability, but we had a particular application in mind, and it could potentially be used for other things. The set command itself lets you one-time set properties of particles, say that you read in from a file, or that you have a formula that describes, say, the spatial properties of those particles. But this allows you to periodically reset it, maybe every time step or every 100 time steps during a running simulation. And the example, the motivation that Aidan had is he wanted to track a shock wave traveling through a material and track just at the time the shock wave reached a particular particle or a set of particles, track their motion and their properties just for the time as the shock wave passed through where those particles were. And so this fixed set commands allows us to set a flag, detect when we want to sort of turn on output for those particles, and then track it, say, for 100 time steps with a little timer that turns off. And in that window, you'll get a dump file with information, say, for 100 steps about exactly those particles near the shock. And this is a plot Aidan produced where he's plotting the velocity in the x direction versus the position in the x direction of those particles. 3 particular particles here he's plotted as the shock front passes through it. And you can kind of see initially they have a high negative velocity because relative to the shock front, they're waiting for the shock to reach it. And then they have this interesting kind of spiral or looping motion as they move back and forth as the shock passes through in velocity space and position space. Okay, couple 3 computes that I want to tell you briefly about. One called rattlers per atom. This is again by Joel, one of our developers. The idea is in a glassy or granular packed system to identify what are called rattler particles, which means they're a little bit under-coordinated. So maybe they're in a little group of particles around them, but they're free to move within them because they don't contact all of them simultaneously. So those can be identified now with this compute as your simulation runs. Reacts per atom was implemented by Richard Berger, another of our developers. And this lets you, as you run a large react simulation, and it does chemistry and creates different bond types and molecules are created and destroyed in that reactive simulation. You can get all the information you need about the implicit bonds that are created and broken as the simulation runs and output them in a convenient format. And that's been COCO-sized by Richard to allow you to do it on GPUs, still in parallel, so you can do a very large-scale React simulation and get all this information as it runs, as opposed to trying to do it post-processing. 2 computes that are related in the sense they both do localized structure analysis, but by different methods. So by Paul here at CEA and Meg McCarthy, one of our developers. So the first one, SLCSA, uses this supervised learning crystal structure analysis method to look at an atom, its local environment right around it, and determine some basic structural information about that atom. And Meg's composition per atom does the same thing, looking at the different atom types in say, a high entropy alloy with many different species or some other kind of mixture to allow you to characterize that environment by its local composition around it. And now finally, how am I doing on time? So I got 10 minutes left. Is that 12 minutes? Okay. I'll just highlight a few kind of more general features that aren't tied to individual computes or fixes or pair styles. So for quite a while, with Peter Intveld's help, who's here, I mentioned from Germany, if I pronounced that the same way you did, LAMMPS will let you do traditional orthogonal boxes, rectangular or 3D orthorhombic. It also does triclinic, which are tilted boxes, here shown in 2D, but can be tilted in 3D as well. So previously, we've always required what we call a restricted triclinic box, where the A and B edge vectors of this 2D box, for example, the A vector had to be along the x-axis, and then the vertical vector had to be in the y plane, the upper y plane. So here it's shown a little bit tilted. But we now allow input of a general triclinic box, so those AB vectors can be anywhere in space, or if you have 3, they can be anywhere in space. This is convenient for crystallographic representations in solid state physics, typically that you might have sort of arbitrary A, B, and C vectors. And what we do is rotate those general vectors into the restricted form that LAMMPS uses internally, but for input and output, we allow you to use that general set of triclinic vectors that you want to define for the box. We've allowed a capability to invoke Python functions within variables in LAMMPS that are either equal style or atom style, where you specify the formula. And so we've added some syntax to let you in that formula embed a call to a Python function. And if it's an atom style function, then that function gets invoked once for each atom in the system. So here's a little example of how this would look like in code. This top yellow box is a little piece of Python code that's, for example, going to compute the X component of a force that you want to apply to each atom. So you're going to input as arguments to that. Hopefully you can see there are 4 arguments, the X, Y, Z coordinates of the atom, and maybe a scalar temperature of the system. And then it's going to return, in this case, the force on that atom in the X direction. So what you would put in your input script is a variable command and a Python command that kind of hooks a Python variable to this function, the Python code, and describes the nature of the different arguments, what their types are, etc. And then you might have code like this here, where the key command is this variable X field, which is going to be a per atom vector that stores the force on each atom that gets computed by this Python function. And so the formula for it might have other things in it, but it's going to have this pi X force, which triggers this piece of Python code to be evaluated for each atom. And you're passing in X, Y, Z, which within an atom style variable is the X, Y, Z coordinates of that atom. And this scalar temperature, which you might have computed with a compute if you want to pass, when this gets invoked, the current temperature. And so a command that might use this is the fix add force command, where you're specifying an additional force to be added besides the interatomic forces to each atom, like an external field that's being applied to the system. And you call it with this variable that's the X field, and that's going to trigger the Python code to be operated on, or to be evaluated for each atom and return X forces. You could do the same for Y and Z forces if you wanted a 3-dimensional field on those atoms. Okay. I wanted to mention type labels. If you were at the tutorial yesterday, Jake Gissinger, who's one of the key developers of this with collaborators, talked about this a bit. They were just released a couple of years ago for the last workshop, but now they've been broadened and sort of, I don't know if Jake considers it finished, but he's kind of got it in all the places in the code that would use types. So the idea of a type label is in place of the standard numeric atom types or bond types or angle types that LAMMPS uses. It allows you to define a set of strings that would represent each one of those numeric types. So maybe in a bioforce field, there'd be several different types of carbons, and you'd call this one C2 to match the force field. Could be gold, it could be CH as a type with a dash in it for a bond that indicates obviously what it's a bond between. Same for an angle. And then the idea is internally the code still uses numeric types, but there's a mapping between each one of these strings and a numeric type. But that allows you in the input script, be it a data file, a molecule file, or the input script itself, or output a dump file, you can choose to have those those string labels instead of the numeric types be in those files. And so Jake, I didn't think talked about this yesterday, but I know he was thinking about, you could ask him about this. I think one of the ideas with his fixed bond react, which is doing heuristic chemical reactions as a simulation runs, that as bonds were created and destroyed or angles created and destroyed, he could sort of auto-infer those new bond types, those new angle types from these concatenations of atom labels. And so that would allow you to do complex things with his fixed bond react in a very simplified manner for the users. And the people from the Kim group have also talked about having this as an interface to Kim, which represents its potentials for atomic species with these natural kind of AU labels, for example. So there's a how-to section of the manual on this, or since you're here, you can talk to Jake if you want to learn more about this. And that's something we're excited to have in LAMMPS. A somewhat related idea, which Jake also mentioned yesterday, is we now allow a JSON format for inputting molecule files, which can be used by fixed bond react, but it can also be used in other parts of the code. And so this again was done by Jake and collaborators, including Axel. And it makes it easy to interface LAMMPS to a database of molecular or other structures because they use the JSON format. And the plan is, now that we have the JSON infrastructure in the code, is to allow JSON formatted input and output for other kinds of LAMMPS files. Perfect. The last new feature I wanted to mention, and if you were at the tutorial yesterday, you know this LAMMPS GUI tool was used. This is work primarily by Axel, one of our developers. It's a GUI, a graphical user interface for editing, running, and testing LAMMPS input scripts. And the initial version was released just 2 years ago, right before the last workshop, but it's had lots and lots of enhancements since. It was yesterday used in the beginner's tutorial. There's a how-to section of the manual as well on this if you want to look at it. Here's just 2 screenshots of an input script with color coding for different syntax highlights. Here's a plot that it produces as a LAMMPS simulation runs to look at different thermal output, including averaging of it. And then 3 more screenshots. The bottom 2, these are the kind of graphics that can do natively and on the fly as a LAMMPS simulation runs for looking at your system, either molecular or, in this case, boundary conditions on a pipe that fluid is flowing through. And then up here at the top, editing input scripts. It provides little prompts and auto completions and other things that make it nice to work with an input script. And you can run all the tutorials that Axel and Jake and Simon Gravel have developed and was talked about yesterday. You can run those tutorials through the LAMMPS GUI. So I think, yeah, that was my last slide. A couple minutes for questions if anybody has something they want to ask about anything I talked about or more generally. Please just talk loud. Is that Susan? Yep. Oh, okay. Maybe that's better. Oh, that's better for the Zoom folks. Yep.
Thanks. I'm Emily Stein from Sandia.
Mhm.
Could you say a little bit about how or what problems are driving the development of new capability and how the LAMMPS development team works with LAMMPS users to create those capabilities?
Sure. I'll comment on both those. So in terms of priorities or what new developments we focus on, that's, to be honest, that's motivated by what funding the people who work on LAMMPS have and what projects they are and what needs those projects have. So that's typically the highest priority. But we do take input from users, from the community in general, whether at workshops like this or on the MatSci forum where people talk about needs or issues, and they can just post issues or feature requests on the GitHub page for LAMMPS. And we do look at those. And if it's a combination of, do we have time? Can they help us? You know, how much work it is, or is it fundamentally possible? But we do try to respond to user requests as well. So it's just a question of resources really in terms of what things we get to. Does that kind of answer your question? So. Okay, we can talk more, Emily. Thanks. Go ahead.
So regarding the general triclinic boxes, if I ask for thermo output of like vector quantities or tensor quantities, like let's say stresses, are those going to be in the internal coordinate system, or are they going to be in the coordinate system I input?
Yeah, so I think for the pressure tensor, it's in the general triclinic format. I think, I don't remember the list, but there's other sort of output quantities that could be vector or tensor related, and we try to put them in that coordinate frame as well.
Very cool. Thank you.
But you should check the documentation, then ask us if there's something you don't think is right about that. So.
Okay.
Okay, I will just say, well, thanks again for everyone for attending, especially those who came a distance and those who are attending virtually. And I'm going to turn it back to Meg to introduce the keynote and first invited speaker.
Thank you, Steve. Round of applause, please. All right. Yeah, while Danny is getting set up, hey, Danny. Our next speaker is Danny Perez from the Theoretical Division at Los Alamos National Lab. And I'll read a little bio and then introduce him with his title. After obtaining a PhD in physics from the University of Montreal, can't say the French, in 2006, Danny Perez joined the Theoretical Division of Los Alamos National Lab, becoming staff scientist in 2009. His research focuses on the development of novel atomistic multi-scale and machine learning models on their implementation in simulation codes and on their application to a range of energy-related problems. For example, his group investigates radiation damage in materials for fusion and fission nuclear energy, the formation and breakdown precursors and particle accelerators, and the design of new separation chemistries for critical elements. From 2017 to 2024, he led a national effort aiming at combining machine learning with traditional high-performance computing to demonstrate the power of exascale computing for materials simulation, culminating in demonstrations at scale on the first 2 exascale computers in the United States. And are we all ready to go?
I think so.
All right, yeah, thank you. Danny, today we'll be talking about automated generation of training data for LAMMPS potentials using max entropy.
Thank you so much, Meg, and thanks to the organizers for the opportunity to be here. But even more than that, I would like to thank you all for the amazing work you're doing on LAMMPS. That's really fueling a big chunk of our community. So I think I speak for all of us in thanking you for your time and your dedication to making LAMMPS what it is today. So what I want to talk about today is a question that's really at the core of molecular dynamics, and is the question of how we generate potentials or force fields for MD. So of course, whether or not an MD simulation is useful really depends on the quality of the potential you have underneath. And I think it's a general consensus that if we could avoid using potentials and just brute force our way through with quantum mechanics, that's what we would do, right? But of course, there's no way we can afford this for many of the problems that we care about. So for many, many years, we relied on something that's on the complete opposite axis of the spectrum, where we valued speed over everything else and use very, very simple empirical potentials that use like simple functional forms with just a few parameters. And these ran very, very fast, but of course the accuracy was not what it should be, right? So it was mostly a qualitative way of approximating materials. And of course, unless you've been living under a rock for the last 15 years, now we're on this new era where machine learning-based potentials are really what dominates the field, or at least is extremely rapidly growing in the field. And the idea of this potential is that you can basically get the best of both worlds, right? You aim for an accuracy that approaches quantum accuracy at a cost which hopefully approaches the cost of an empirical potential. So you can still do large simulation for a long time, but at much higher accuracy. So the question I want to explore today is, are we really in this brave new world where we can forget about quantum and just trust the potentials that we have more or less blindly? And if you follow the literature, you might be led to believe that indeed we are in this new era where the potentials are just so amazing that basically we can think of them as surrogates to quantum mechanics. So what I would like to do today is kind of give a reality check to that statement, but also provide a cause for hope that actually we might not be that far from this target here, but whether or not we're here, I'll leave that to your judgment. Okay, so let's just emphasize a few critical points that distinguish these classical models that we use for many decades with the machine learning models we have now, right? So basically, the way we did things for the first 50 years of MD is that we would guess the physics, right? We would put in physical forms by hand into the potentials with only a few knobs that we can turn. So these were not super flexible, but what they had for them is this kind of robustness, because the physics was baked in the models. So the natural limits of squishing atoms together, pulling them apart, were naturally reproduced by the models. Okay, so they were not very accurate, but they were very robust. And now in the era of machine learning, we rightly gave up on trying to guess what the physics is in favor of using extremely flexible functional forms with tons of free parameters that you can turn, which gives you extremely high accuracy in the regions where you have a lot of data, but they tend to be very hard to constrain in regions where you don't have data, right? So they can basically fit anything. If you don't give them anything to fit to, then who knows what they're going to produce in terms of predictions. So there's really a trade-off here, and we tend to value accuracy, but I'll try to show you that in fact that can be a dangerous game, but that you can basically exploit an accuracy robustness trade-off in a way that's very favorable if you design your training sets in the right way. Right, so these will be the key questions that I will be talking about today. Okay, so I won't give you an overview of the field of machine learning potentials. That's an extremely large field. It was moving extremely fast. There's been an amazing amount of work done in that field. And a lot of the early work really focused on developing the ML architectures that we will use to train the potentials. So what are the features? What are the neural network models? How do we encode symmetries? How we put long-range interactions? All these very important questions. And my personal view is that by now, there's a lot of very good models on the market, right? That we are not primarily bounded by how good the functional forms are. But you might have had this experience yourself of reading a paper about an exciting new potential that promises something like 1 millieV per atom accuracy. Then you take it, you go run it on the things that you're interested in, and either it blows up on you or it gives you really high errors that are not really jiving with what you saw from the paper, right? So in my opinion, and that will be kind of the theme of the talk, is that this comes from the fact that we don't spend enough time thinking about what we train the models to, and we spend a bit too much time thinking about the models, the specific form of the models that we train. Okay, and as an example of this, we did a very simple test on carbon. Okay, there are countless versions of carbon potentials out there. So we just did a simple test. It did a bunch of cold curves, different phases of carbon, energy volume curve, very simple, right? And then we picked some potentials from the literature that were published over the last few years from very strong groups, right? And just saw how they do on this kind of test. And these are examples of what we saw while running these tests on potentials, right? So you'll notice a common theme that if you look at low energy structures around the equilibrium density, these guys do great, right? Because they were basically trained to these phases. But if you start looking at the other phases, you see all kinds of weirdness, kinks, oscillations that shouldn't be there, very unphysical behavior that show up in these regions. Now, you might argue that you might not care about these phases, right? But it's important to have this in mind, that the potentials basically, you should expect them only to reproduce what they've been trained to, and not magically to capture everything else under the sun that you might be tempted of running with LAMMPS when you're experimenting in your own research, okay? So the point of that example is not to downplay the work that was done, right? These potentials are trained with certain problems in mind, and they might be doing amazingly well for what the authors have been training them to, right? But it's important to realize that transferability is really a challenge, and it's especially true in the ML era. So if you want robustness, the name of the game is really to generate training sets that will give you this very high coverage of your configuration space in a way that the traditional approaches don't give you. Okay, so what is the traditional approach to fitting potentials? If you go back 20 years or so, the way this was done is to get an initial training set, fit a potential, and then test it on something else and figure out that it's crap. And then you whack that mold and you fix it, and then the problem shows up somewhere else, and then you fix it, and then you keep doing that until you run out of sanity or you run out of patience, and then that's the potential that you publish, right? So this is the thing that we're trying to move away from, because it's taking a lot of time, and it's taking a big toll on the people that are developing potentials, okay? So a big innovation in the field was to introduce what's called active learning. I think a lot of you guys know what this is. And the idea is to basically train a preliminary version of the potential, but equip that potential with some measure of uncertainty or some confidence interval with the potentials. And then if you start running simulation on that approximate potential, and you encounter a configuration that you're not confident in, you just take it, add it to your training set, then retrain your potential and keep going, okay? So that is a powerful thing to do, but in a sense, what you did is replace yourself in the loop by a computer being frustrated in the loop, right? You fit a potential, you try to break it, then the computer fixes that thing that you just saw, and then runs it again until it breaks again, right? So it's the same kind of whack-a-mole cycle that you're going after. And the hope is that when this converges, you kind of eliminated a lot of the defects that would actually contaminate your real production runs by the time you run this. So there's another family of approaches where the philosophy is to say, okay, I'm not gonna try to guess the regions that are important for my MD run and start scoping MD runs there. Instead, I'm gonna try to broadly cover the whole configuration space. So you might start at random, use genetic algorithms, maybe refine them with a preliminary version of the potential, or use methods where, let's say I'm fitting to tungsten, but still I'm gonna generate a training set with a huge number of different crystal structures that have nothing to do with tungsten, just to build a broad coverage of my configuration space. So these are what I would call kind of global approaches to data set generation, where you're not tailoring your data set to the specific material that you care about, but you just say, let me try to cover as much of the configuration space as I can. So this is really the flavor of method that I'm going to tell you about in the rest of the talk. Okay, but I think what's important to realize is that all of these, again, live on a spectrum where there are trade-offs, right? If you have a very well-defined application space and you value accuracy very highly, then active learning is a great idea, right? You can refine your potential in the regions that you value a lot. And for your application, that might be the perfectly rational thing to do. For other thing that I do in my research in extreme conditions, it's much harder to have a good sense of what is it that even I will want to run this potential on a year from now, right? So I tend to value robustness much more, and I'm willing to take a hit in absolute accuracy locally in certain properties, so long as I get broad coverage over the whole space. So again, the claim is not that our method is the end-all be-all and that nobody should be doing active learning, right? There is a room for different techniques depending on what your end goal is, but my focus will be on that side of the axis here. And hopefully the conclusion by the end is that you can be up here at an accuracy that's still very, very good, right? And hopefully that's what I'll be able to convince you about. Okay, so what is it that we want? Okay, we basically want the inverse of what the traditional way of going at it is, right? So I'm a lazy person. I would rather not be in that loop, having to tweak a potential for months. So I want something that proceeds without my intervention at all, and hopefully that I can do end-to-end very quickly, right? These iteration loops, they take a lot of time. And if I have some science to do with the potential that I care about, I would rather get to it sooner rather than later. And so the basic philosophy is that I don't want to have to guess what should go in a training set, right? I want a training set that basically covers everything and then let the machine learning take care of it. So the way we get there is by reformulating this black art of generating a data set into a well-defined optimization problem, where the objective function is the diversity of the data set. And then we will automate that procedure and just let the algorithm figure out what should go in the training set. So to do that, you need an objective function, okay? And it's not uniquely defined. You could come up with many different objective functions to achieve your target. But the one we went after is information entropy, right? So that's important to distinguish from the thermodynamic entropy. So here I'm really thinking about the information content of the data set that I'm training to. So information entropy is just a measure of the information that you need to characterize a sample from a distribution, okay? So a typical low entropy distribution is something like a delta function, right? If every time I sample, I get the same answer, then I really don't need much information to encode the result of that sampling process. So that's a low entropy distribution. And the high entropy distribution will be something very broad and very distributed, where samples out of this can take a very broad range of values. So I'm going to need a lot of information to encode what's in there. So at a high level, what entropy characterizes is just the amount of information, of non-redundant information that you have in your data set. So if you're going to use this as an objective function, and say that you value high information entropy, you're saying that you want high diversity and low redundancy, which makes sense, because we're paying for that with quantum calculations to characterize all of this. So I would rather have something that's very information dense and non-redundant so that I don't keep recomputing the same things over and over with my quantum methods. So that's what we're going to use as the objective function of my optimization loop that I mentioned. Okay, so that's an idea that we've been pushing for a few years, and some of this work was done in collaboration with the LAMMPS team as part of the exascale computing project that we had a few years ago. So the basic idea now is that I want to maximize this number, where P here is some distribution function of features in my data set. And the information entropy is defined very much like a thermodynamic entropy would look like, right? It's just the integral of rho log rho over some space in which your distribution lives. And what makes sense in a machine learning context is to put yourself in a space where the distribution you care about is a distribution over features that you might be using to train your potentials, right? So we already developed a bunch of features that characterize the local environment of the atoms in your system. So you can be in the same space and then define a distribution over your whole training set and then take that integral. The problem, of course, is that typically our feature space is very high dimensional, right? So there's no way we're going to accurately compute that integral in high dimension. So we're going to need to do some kind of drastic approximation to this so we have something that we can deal with. So in these different papers, we do different types of approximations to that function, but I'll just focus on the last version of it that just came out literally a few days ago, where we do something very simple, where we say, okay, I have some distribution of features over my whole training set, and whatever it is, I'm going to fit a high dimensional Gaussian distribution to it. So it's a multinormal distribution in high dimension. And the covariance is going to be just the sample covariance of my distribution, and the mean is just going to be the sample mean, okay? So these are all things that are easy to compute. And then once you cast it in this form, there's just a closed form solution to what the entropy is. And it is telling you that the entropy is proportional to the logarithm of the determinant of your covariance matrix. So when you think about what this means, it's telling you it's essentially some kind of measure of volume spanned by your data set, right? So determinant will be the product of the covariances along all the principal directions in your feature space, and that gives you a sense of volume, right? You want broad distributions in all the directions in your space. So the claim here is not that numerically this is a great approximation to the full entropy, the exact result, which is probably not. But the claim is that maximizing this is something that makes sense in the data generation context. If you value diversity, that's a good way of measuring it, and it gives you a simple closed form solution that's easy to work with, right? So now I can take any data set, featureize it, stick it in this, and get some value, the entropy. So now the question is, how do you actually maximize the entropy of a data set as you construct it? So to do this, we use a greedy scheme where basically we initialize a box at random shape, random position of atoms that we throw in there. And then we take that box and we say, okay, let's pretend that I'm trying to add this configuration to my existing training set. What should I do? Well, I should move atoms around in the box so that the entropy of the whole training set would be as large as possible if I were to include that guy in my new training set, right? So I'm attempting to create a configuration that adds as much information as possible to my existing data set. So this is an optimization problem with respect to the position of the atoms in the configuration that I'm considering for addition, right? So I can locally maximize the entropy over these degrees of freedom, then check, did I manage to increase the entropy of my data set? If I did, but perfect, I include it in my data set. If I didn't, then I just throw it away and I try again, okay? So what's important to realize is that the entropy landscape is very rough, right? So I'm not gonna find the magical configuration that increases the entropy by the largest amount. That will be very hard, right? So we just take a pragmatic approach of it. that we shoot points at random, locally maximize the entropy. And then if we manage to find a good configuration, great, we add it. Otherwise, we just try again. Okay, so I keep saying that we maximize the entropy. In reality, it's slightly more complicated than this, because if you just maximize entropy, you'll generate lots of configurations where atoms overlap on top of each other, and that's not good. The energy will diverge, your DFT calculation won't converge, so you don't want this. So instead, we form an effective potential that has a core term that's totally non-informative, right? It's just an exclusion volume around atoms. We say, I don't want anything where atoms are closer than this, minus the entropy score, okay? And this defines an effective potential that you can think of as a potential that you would stick in LAMMPS. And that's exactly how we code this up at the end of the day, right? But this has nothing to do with the energy of the system, right? It's a purely topological metric that's telling you how much information is that new configuration giving you compared to what you had before. And then you just need to compute the gradient of this effective guy and move your atoms around to increase the entropy. And in the last few minutes, I'm going to tell you how we actually implemented this in LAMMPS. And I think it makes use of some very cool features that the LAMMPS developers included in LAMMPS. Okay, good. So what comes out of a procedure like this? Okay, so this is a highly non-random sample from the distributions that are generated, just to give you a sense of what's in there, but it's not weighted uniformly, okay? So you get a lot of configurations like you would expect, right? If I tell you this is a high information entropy configuration, you imagine things where all atoms look different from each other. So something very disordered. So you have something liquid-like with surfaces and stuff. But you're shooting for a broad coverage, right? So it's trying to hit every point in your configuration space. So you get a bunch of things that a material scientist would stare at and be happy to have in their data set, right? Things like stacking faults, like an interface between a disordered solid and an ordered solid, something that looks like grain boundaries, and a bunch of perfect crystal structures. And what's neat is that these crystal structures are not just the dense, close-packed thing that you would expect to get at random by just like throwing spheres and putting an excluded volume term. You get some low-density things like simple cubic, graphene, and you also get these low-dimensional order that show up like a cohedral in some structures. So we get a ton of different smelling structures in there without any human intervention, right? When I generate this, the code doesn't know whether the material I care about wants to be BCC or FCC or anything. I don't tell it anything. I say just span the configuration space, and that's what's coming out. Okay, so now if we go and measure how much entropy do we have in our data set compared to other data sets in the literature, turns out that we get a lot, right? But it's not surprising because that's exactly the thing that we're maximizing, right? But on this scale, a band about this big means that along all principal directions, we're about twice as wide as a data set that would be at the bottom of the band, right? So you can see that actually these data sets are by a huge amount more diverse than most of the data sets that we find out there, including some of the data sets that we generated in previous years, right? So that's not surprising because that's the thing we optimize. And now the key question is, are you getting anything useful from all that diversity, or is it just going to confuse your machine learning when you're going to try to fit to it? So what I want to do now is try to convince you that actually the modern ML approaches have no issue dealing with these kinds of data sets, and you can get close to an optimal trade-off between accuracy and robustness. Okay, so to demonstrate this, we generated an entropy set using the bispectrum components that Aidan introduced for SNAP. So we optimize in a 55-dimensional feature space, but then train potentials on a different feature space, right? So then we did DFT calculations with VASP with some high throughput workflows, and then we trained some atomic cluster expansion models to this data. So the data sets are, in the big picture, is not that big, right? We're talking about 30,000 configurations, and most of them are very small. So that's something that you can run on a GPU cluster in a day. Then we fitted these potentials up to body order 6, and they're not terribly complex potentials, something like 1,000 parameters per potential. But the key point here is that these are truly one-shot potential. We generate the data set, we do the DFT, we fit That's it. No hyperparameter optimization, no iterative cycle of putting more data in it. So this is basically the worst case, right? If I spent a few weeks tuning these for a specific material, they would get better than what I'm showing you. Okay, so we did a test for tungsten, which is important for applications to fusion that we care about. So here you have about 20 different crystal structures, and you're seeing formation energy, formation volume, and bulk modulus of these things. And again, none of these phases were in the training set at all, right? So just pure prediction, one shot, and you see over extremely wide range of energy, volumes, elastic properties, we're doing great, right? Without having had to put any of this by ourselves. So you're going to tell me that you really don't care if an A4 phase that has some very high energy is right? What you care about is that BCC behaves like it should. So we checked a bunch of things that people care about, generalized stacking fault energies, phase transition, transformation paths, phonons, defect diffusion, defect formation energies, and they all come out very nicely. So this is, I think, something that's very cool that shows you the trade-off between getting things that you care about right, but also getting things that you don't yet know you will care about in the future right at once, right? Okay, so then we did an experiment, right? As I told you, the object that we optimize over knows nothing about our target material. It's purely topological. So we just took the exact same data set, applied a global volume rescaling, and then did a bunch of DFT for different elements and repeated that same experiment. So you see same plots here, and this is beryllium, aluminum, rhenium, carbon, antimony, tellurium, very different materials. And it's not perfect by any means, right? If you stare at this, you're going to see problems here and there. But in terms of transferability across huge different number of phases, different materials, you basically get it all in a one-shot type approach, again, which you could get done in a single day, end to end. So this is something we're quite excited about. But you might wonder, okay, are you really doing better for many metrics compared to the way that the other people are doing it? So we try to quantify, go a bit further and quantify how much more transferable we are compared to traditional approaches. So going back to my initial example, that's what I was showing you, that like good potentials from the literature fitted by good groups, how they behave on these high energy phases. And then that's how ours behave, right? Again, no iterative improvement, just one shot through it, which is quite nice, right? It's not perfect, but it is much better than what you get without having this kind of ultra-rich data set. Okay, so then to really characterize this trade-off between accuracy and transferability, we went in the literature and looked at different potentials out there for tungsten and different data sets for tungstens that were published. And the numbers you see here are test errors on energies and forces in milli-eV and milli-eV per angstrom. Okay, so the numbers that are reported in papers where people hold out data from their training set and train to it and report to you an error is the diagonal here, right? So you see in this case, they reported the mythical 1 milli-eV per atom error level on their potential. Right? And this other one reported something like 27. And if you look at our number, you see 60. And then you would think, oh my God, all of this speech for nothing. Like, why do I care about a transferable potential that's doing 3 times or 2 times as worse as competitors? Right? But that, of course, doesn't tell the whole story, because if you start looking at the off-diagonal terms, now it tells you how this potential does against your neighbor's data set that built this data set with his own domain expertise of things they cared about. And now you see a very different picture, right? What was 1 milli-eV per atom on its own data set now looks like 100 milli-eV per atom on somebody else's data set, and looks like 400 on our data set, right? So that's a completely different statement than what you might be led to believe by just looking at that diagonal here. And this is something we see consistently, that Potentials really look good when tested against holdout from their own training set, but they really don't look as good against somebody else's data set. And this is especially true against this high information density types of data sets, where lots of potential really fall apart. And if you look at how we do across everybody's data set, we basically do the same, right? No matter what we test on, we get very similar energies and forces. So this, I think, is really a feature that's important to keep in mind, that that what you get, the impression you get from reading the papers and just seeing the quoted validation or test errors is really not an indication of how these would do if you push them out of their comfort zone and start doing things that the creators of the potential didn't think about. And this is what these high information methods get you, right? It might not be the lowest errors reported ever, but you can be pretty confident that to break this, you're gonna have to try hard. Okay, so going back to this plot here, we are definitely in this range over here, right? That if you need 1 millieV per atom for your application, then you should be over here, right? But if you're gonna beat your potentials to hell because you're doing extreme conditions, then you should be more comfortable on that end of the spectrum. Okay. So everything I showed you up to now was just on unary materials. You might think, okay, we're past this now. Everybody's doing high entropy alloys with 5, 6, 10 components. So how can we contribute to that field of chemical diversity? So we just went at the other extreme, from unaries all the way to the whole periodic table at once. And we looked at these universal potentials that are now popping out and that I think everybody's really excited about for good reasons, right? Because if we really get robust universal potentials, then this whole game of fitting potential kind of goes away, and we can go back to doing science instead of spending our time training potentials. So we collaborated with the group of Ralph Droughts, with Ralph, Yuri, and Anton. And these guys are the developers of the GRACE potential, the universal potentials. So we decided to kind of stress test the universal potentials that are out there. And the thing that's important to realize is that these guys are trained mostly to databases of perfect crystal structures and small distortions around these, right? So it's Alexandria, Materials Project, and then some MD runs around these configurations and distortions thereof. So you might ask, okay, great, how is this doing in the full diversity space that these potentials might encounter if you start to push them out of their comfort zone? So we generalized the entropy method that I told you about to multi-component systems. Turns out that's pretty easy to do, right? The thing we did is having some pseudo species in there where the exclusion volumes and the cutoff radii of the featurization just scale with the covalent radius of the materials, right? So I can throw atoms in a box, any mix of species that I want. Then I adjust the featurization for each one of them, and I just maximize the information entropy of that thing, just like I did before, right? So that will maximize the chemical diversity if your features are sensitive to that, and the structural diversity as before. So we generated about 1 million, a bit less than 2 million configuration, and then just blasted this through LAMMPS. And the first thing you can do is just say, okay, let's use this as a test set and see how the state-of-the-art universal potentials do on that test set. And they don't do so great, right? Okay, it's a mixed story, but if you zoom out, that's what you see, okay? And this is on the state-of-the-art potential from Ralph's group, right? They just fitted this to the OMAT dataset. So 100 million quantum configurations, which you might think is an insane amount, and it is a huge amount of data. But if you test it on the high entropy configurations, you see really mixed results, right? To be fair, if you zoom in and you look at the density over here, you're going to see that along the diagonal, there's lots of good performance there, right? There's lots of points where the potentials do great. But there's lots of points where when they don't do great, they just go nuts, right? And this is the thing that you want to avoid once you start doing MD with these potentials. And it's especially true for forces. You can see the diagonal are especially close to 0. The potentials are doing very good. So near equilibrium, these potentials are amazing. But as you push them out, then your mileage may vary. And it's even worse for stresses. And this is trained to a huge amount of data. Right? So what we did is to take our million-sum DFT configuration and train the same architecture on this, and then test on holdout data. And what we get is this, right? And this is something like 100 times less data than they trained to, and you get something that's way, way more robust. Okay? So that I think is very exciting. It shows that you don't need the full computational power of Meta for months in order to get a data set that gives you robust potentials. So it's not just the amount of data that matters, it's really the kind of data that you put in there. So we're still looking at this in more details. I mean, you have to give these potentials what they're due, because for crystal structure predictions, these things are amazing, right? They're trained exactly to these databases, so they do amazingly. But if you start looking at defects and extreme conditions, we do much better than these potentials, which is a trade-off. So now we're looking at basically fine-tuning this on this data to get something that's the best of both worlds. So we're writing this up, so be on the lookout in the next few weeks. It's going to come out. Okay, so I want to finish in the last 5 minutes and tell you how we actually did this using LAMMPS. And I think that uses some really cool features of LAMMPS that we were quite excited about. So the idea here is that in my example, we use the snap features. I don't want to recode the calculation of snap features myself. This was done very nicely in LAMMPS already, so I would just rather call it from LAMMPS. But this whole business of taking the gradient of the logarithm of a determinant of a feature matrix, I would rather not code this up in C++ myself, when we have all of these great tools in Python where I can just auto-diff through everything and don't have to worry about anything, right? So I would rather do the high-level stuff in Python and the low-level stuff in LAMMPS. So how do I do that? We use the MLIP package, which is a beautiful piece of code. So that's a blurb from the manual that basically says that the per-style MLIP is a generalized way of dealing with machine learned potentials, where you have this neat factorization into descriptors or features and models as two different pieces, and then you can mix and match these two pieces any way you want, right? So descriptors are what I call features. It is something that characterizes the local environment around atoms. And that piece of the code needs to compute these features given positions and the gradients of these features with respect to positions. And then you have another piece of the puzzle that's the model. It's the thing that takes features and computes an energy out of it, right? So that part of the code computes energy as a function of features, and then the gradient of the energy with respect to moving the features around. And then LAMMPS basically does the chain rule and puts these two pieces together to give you the gradient of your potential with respect to positions, which is what you need to run the code. But this factorization is what we're going to exploit to reuse as much code as possible from LAMMPS and do as little work as possible to implement our entropy thing. Okay, so at a high level, what our workflow looks like, it's all in Python. We use ASC. We create atoms object by throwing atoms at random, and then we connect it to an entropy calculator. And then we just do minimize, and that minimizes our objective function, which contains the entropy and the core repulsion. And then we do the whole logic loop that I had on my flowchart. We just do this in Python in a way that's very easy, okay? So now the question is, how do you implement this guy, and how do you update the entropy model here? And that is very simple, right? So the entropy model is a simple Python class. It contains the sample mean and covariance of the data set. It knows how to compute the entropy. And it computes this based on features that LAMMPS gives it. So we can code all of what we want using JAX or PyTorch or whatever you want, using features that LAMMPS gets us. So this class here is the model in the MLIP context. And the other class that we had to tweak was an ASC calculator for entropy calculation. And this under the hood initializes LAMMPS. With this pair style, you have the core repulsion here that I told you about that we didn't have to code up either because LAMMPS already did it, plus the MLIP package that used the snap descriptors and a model that is specified as later. And this is really the genius of that whole thing, is that when I define this, the model doesn't have to be defined yet. Right? I can define my model object later on in the code and connect it to LAMMPS with this call and tell LAMMPS, use that object to do the model calculation when I'm going to call it. Okay, so that looks a bit abstract. So I made a little cartoon. So the blue boxes are done in Python, and the orange boxes are done in LAMMPS. So we call ASC minimize, which maximizes the entropy on given an initial configuration of atoms. That creates an entropy calculator, again in ASC. That creates an instance of LAMMPS with this MLIP package underneath. And when it's time to compute an entropy and its gradient, now it's breaking out into computing the snap descriptors inside of LAMMPS and computing the model calculation inside of Python with the object that I created. Then LAMMPS puts all of this together and returns the gradient to ASC minimize. So you can just crank to this, go in and out of Python, do all of your updates in Python of this model object, and let LAMMPS do all of the heavy lifting. Okay, so that concludes what I wanted to tell you about. Just to summarize, I think this whole wave of MLIP is really, really exciting, but we have to be somewhat realistic with what we can expect from these, and especially this trade-off between robustness and transferability. So we propose a way to go around this, and this was really made easy by these incredible features that the LAMMPS developer put in there, where you can really combine state-of-the-art ML tools with what LAMMPS does great in terms of low-level, fast computation. And that really made it easy for us to implement this whole workflow. So I'll leave my acknowledgement slide. There was a big team of people involved in this work throughout the years, and I acknowledge our funding. And thank you again to the LAMMPS team.
Thank you, Danny. Thank you, Danny. All right, do we have any questions from the audience? Please take the microphone.
Thanks, Danny, for a very nice talk. I'm kind of amazed that it seems like you're still using a small set of snap descriptors to do the entropy maximization. I would have thought at some point you'd find that a different, fancier set of descriptors like ACE or something would give you better performance.
Yeah, that's a good point. And I'll use this to praise your code again, because it's basically a line change in the code to switch from snap to ACE. And if any one of you implements your own descriptor into LAMMPS, into MLIP, then it's really just toggling a switch. So to go back to the dimensionality question, that's an interesting question, because as I told you, the entropy landscape is not smooth. And the higher up you go in dimension, the rougher that entropy potential gets. So finding good high entropy solution gets harder and harder as we go up in dimension. Technically, we can, but you would just spend more and more time trying to shoot for something interesting in that huge space. And this is a thing we didn't explore thoroughly. But I mean, that's an example, right? We work in 55 dimension to optimize the entropy, but then we fit potentials in much, much higher dimension, and it's still working great. But I will not claim that this is the ultimate way to do it. I'm sure if we look at it carefully, and there's still gains to be had there. Okay.
Hi, thanks, Danny. That was a really fantastic talk. So I'm kind of a foundation model user myself, right? So I'm really interested in this, universal entropy data set that you've talked about. So you said that you generated like 1.5 million configurations, which obviously is a lot, but the configuration space you're trying to cover is enormous if you're doing the whole periodic table. So you must have been at least somewhat selective still about like combinations of elements. Like, did you only go up to 3 elements? Did you only do certain elements? Or like, did you truly somehow manage to do all of the elements and all the combinations of the elements in that few configurations?
Yeah, that's a great question. I'm still kind of amazed by how well we do with a small amount of data.
Okay.
But the configurations are really diverse. I think we went up to something like 25 components per cell max.
That's crazy.
And then we just do permutations. It's really a dumb random sample, right?
Wow.
We have some distributions. The probability that you pick that element from the periodic table is this. Just draw elements at random, throw them in the box.
So it really is. There's very little human interaction at all. Just kind of like.
That's right.
Wow.
I mean, we have a weighting thing that says, okay, people probably care more about the top of the periodic table than the very bottom. So we have just like made up weights that give you a sense of the probability that I pick hydrogen versus something else.
Yeah.
But aside from that, that's it. There's no other nub.
That's amazing. Thank you.
Hey, Danny, thank you for the
Right.
presentation.
Thank you.
I have a question. Could you comment on how you decided how many candidates were enough for your max entropy dataset? Was it a stopping criterion or did you
That's
have a
right.
budget?
There's nothing smart there. It's how much compute I could get my hands on. That's what determined. We had access to this great machine that was up, and we were up and running before everybody. So we just blasted it for a while until it got busy, and then we stopped. So there's no claim that somehow this is enough for everything, right? If I could generate more, I would keep going.
Okay.
So, but I think the good news is that you don't need 100 million to get very good results. But certainly, if you give me more CPU time, I'm going to use it.
All right. Sounds good. Thank you.
Hi, really nice talk. So my question is how this is transferable to molecular system?
Yeah, that's a very good question. Our focus was really on hard materials, but we tested on QM9, and we're doing surprisingly well on these kinds of things, which is extra surprising because we take no measures to create like molecular things that make any sense, right? It's really just things thrown at random in a box. But I would say if you care about molecular stuff, you should go with OMOL type potentials. It's likely that they're going to do much better than that data set for this.
Thank you. Very nice talk. I have questions that I have saw the very good result in crystal structure. But can this model be applied on a more complex structure, just like a solvated polymer, the polymer with water environment?
So we didn't look at any soft material. Our focus is really on hard materials. I think as I said to the previous question, if you care about molecular things, there are huge data sets really targeting kind of molecular chemistry type of approaches. I would probably suggest that you look at these first before looking at that. But if you're looking at like super high extreme conditions for organics like explosives or something, having some fraction of this kind of approach in there is probably going to help a lot. But if you care about like ambient conditions, chemistry, you probably wouldn't see a great advantage in using this.
And can we use this way to generate data setting, a data set in some water environment? You know, it's more flexible.
The data set or
the way to generate data set.
Yeah. So this should work just fine. And for water, for example, it might be interesting, like to get different crystal structure phases of water, for example.
Okay.
You might want to tune what features you use to optimize the entropy. If you want to look at like hydrogen bonding patterns or something, then you could add it in there. But the method itself is transferable to whatever feature you want to use.
Okay, thank you.
So do you have any idea of the application of ML IAPs to spaces like diffusive molecular dynamics, where you have very large timescales with respect to just regular MD?
No, I wish I did. Like most of my career, I worried about timescale issues in molecular dynamics and developing long timescale techniques. And finding good ways to machine learn this would be amazing. But I think the bottleneck there is how you generate a good reference data set to test these things against, which by definition would require some kind of insane computing power or some great trust in whatever sampling method you use to assemble these. So I think it's a super interesting question. From what I've seen, I haven't seen any kind of revolution in the way we would go at it using ML approaches. But if you have any ideas, I would be really happy to chat. It's a super exciting problem, but I don't have anything.
Okay, thank you.
About it. Yeah.
Thanks for the talk, Danny. It was really nice. So I'm curious, you've got what I would assume is a sort of relatively uniform distribution over like your descriptor space. So when you go to like train your force field, do you do any kind of like importance weighting based on like a Boltzmann weighting or something so that you're slightly more?
So that's kind of stuck. That's part of the hyperparameter we didn't tune. Right? So if you use like pacemaker to fit potentials, there's a weighting function that's energy based where you say, okay, I care more about things that are like 5 EVs from the hall. And in the paper, with Aparna that we just published, we explored this a bit, right? If you use different thresholds for how much you care about high energies versus low energies, then you get different trade-offs. But I think that's especially important if you want a super fast potentials with a few features. Then trying to fit the whole range of energies is going to bite you because you're going to be uniformly bad everywhere. But as you crank up towards potentials are more and more flexible, we see that you can basically fit everything rather well. But yes, right, it makes sense to use some kind of weighting. But I wouldn't advocate for something super aggressive where you just like exponentially damp the high energy thing because then you lose all the benefits from
Yeah.
those.
Thank you.
Awesome. Great. Thank you, everybody, for your questions. And let's give Danny one more round of applause. Thank you, Danny. All right. Our next speaker is Rebecca K. Lindsay, who is Dr. Lindsay, excuse me. Dr. Lindsay is an assistant professor of chemical engineering and by courtesy of applied physics, nuclear engineering, radiological sciences, and material science at the University of Michigan. Prior to joining UM, Dr. Lindsay earned her BS in chemical engineering from Wayne State University and her MS and PhD in chemical physics from the University of Minnesota, Twin Cities. Following, she worked as a postdoctoral researcher at Lawrence Livermore National Laboratory, where she later converted to staff, leading a variety of research teams within the Livermorian Energetic Materials Center. Her work in computational chemistry, for which applications have spanned sorption of soft materials, possible mechanisms for the origins of life, detonation, synthesis of unusual carbon nanoparticles, and more, has been underpinned by a strong interest in developing tools enabling work in previously inaccessible problem spaces. In addition to her work in computational chemistry, she leverages data science and machine learning to aid in interpretation of large experimental data sets and to develop material performance models from them. Her research has been recognized by a number of awards, the most recent of which include the 2025 American Physical Society Neil Ashcroft Early Career Award for studies of matter at extreme high pressure conditions, and the 2024 American Institute of Chemical Engineering Computational Material Science and Engineering Forum Young Investigator Award. So great. So let's welcome Dr. Lindsay and her. Maybe you can introduce, here's the title, Using Machine Learning Accelerated Simulations to Inform New Strategies for High Throughput Nanocarbon Synthesis. Thank you.
Well, thank you for reading all of that. And thanks to the organizers for the opportunity to be here. It's kind of cool. Roughly 8 years ago or so, I attended one of these in Temple where I learned how to use LAMMPS for the first time, and now here I am. So today I want to tell you guys a little bit about some of the efforts going on in my group to use machine learning accelerated simulations to try to develop new, tunable, and high throughput strategies for synthesizing carbon-based nanomaterials. So let's see if I can get this thing to work. No? All right, just do this by hand. Okay, so why do we care about carbon nanomaterials? So it turns out that you can synthesize these materials such that they exhibit a near continuum of chemical, mechanical, optoelectronic, and other physical properties. And so these have very promising applications spanning everything from quantum computing to drug delivery, catalysis, battery materials, and the list goes on. So while the potential applications of these materials are very exciting, we do run into one challenge though, which is, if we want to put these nominally next generation materials into user-facing devices, we need to be able to produce them at the scale such that we can actually do that in a cost-effective manner, right? So if you take inventory of the different techniques we have available to us to synthesize these materials, you're going to find that they kind of fall into one of two buckets. We have low pressure methods, so things like chemical vapor deposition and flame pyrolysis, which give you very fine control over how you make these materials. But you're going to be measuring throughput on the order of, say, microgram per hour quantities. Now, we can consider then high pressure techniques. So examples of this might include ball milling, or the very dramatic example I'll come back to a few times today, which is detonation synthesis, where now you can produce materials in kilogram per microsecond quantities at a maximum. So this is tremendous throughput, but now we're faced with the challenge that these are about as far from tunable methods as one can imagine. So again, in the case of detonation synthesis, if you are trying to discover new materials, the way you would do this is pick different explosive precursors and blow them up and hope that they give you what you want. Ignoring that, though, we also have a very limited understanding of the phenomena that occur during these synthesis techniques. And so we're missing the information you would need to control these processes. And so we became interested in the question of whether we could develop a synthesis technique that gives us the best of both worlds. So we want the control that you would have in your prototypical low pressure methods with the throughput that you get using these high pressure techniques. Okay, so in doing so, we wanted to start from detonation synthesis because it's the highest throughput of the techniques available to us. And there's a track record for this technique being able to produce a myriad of different types of nanomaterials. So here we go. This over here is a mixture of explosives called RDX and TNT. So this is referred to as Comp B. And when you detonate it, you form these beautiful nanodiamonds. And so industrially, this is actually how these nanodiamonds are produced. This guy over here, this is called DNTF, and it makes these beautiful graphitic nanoonions. So think concentric buckyballs. And then over here, we have picric acid, which forms these glassy nanocarbon particles. So again, you in principle can form all sorts of different materials. And so our idea was the following. So can we perhaps use something like a laser drive to take a system through the same sort of thermodynamic states that you would experience during a detonation on the same time scales? The idea being that if we can do this, then we can control things like the laser pulse width, the intensity, and the duration. And that gives us suddenly that fine control that we would really want to make this a tunable synthesis technique. All right, so here's the idea that we had, or kind of how this would work. So we would start with a carbon-rich molecular fluid precursor, and we're going to use a laser to impart a compressive shock wave into that precursor. So that's a supersonic compression. When this happens, we would be taking our system up above the carbon melt line. So think thousands of Kelvin and tens of gigapascals. And so during this event, you would drive a reactive phase separation of the carbon from the everything else in the system. At some point, and that would form these sort of liquid carbon nanoparticles. So that's what you're looking at over here. So at some point, your shock wave will pass through your sample and you will adiabatically expand back down to ambient conditions, and that should drive a solidification of the carbon nanoparticles into some solid allotrope. And this should all occur on sub-microsecond timescales. So that was kind of the idea. And so, okay, cool, sounds great, but will it work, right? And so what we wanted to do was to use simulations to assess the feasibility of this strategy before my experimental collaborator, Mike Armstrong, had to go and actually build the platform to realize this. Okay, so how we were going to do this is using molecular dynamics, which we've heard a lot about over the past 2 days. And I'm just going to quickly go through this, right? I like molecular dynamics because it's a pretty simple technique to work. In principle, you really only need to know 2 things to get going: some initial coordinates for your system and some interatomic model, right? Given this information, we can evaluate Newton's equations of motion to predict how the system evolves in time. And from that trajectory, we can get all sorts of useful information. However, as we just heard Danny talk about, if our interatomic model is not chosen carefully, we're going to find ourselves in a garbage in, garbage out regime. And so one of the things that our group thinks about quite heavily is this question of how do we identify and, if necessary, generate suitable models for our application. All right, so let's consider this shockwave synthesis thing that we're trying to simulate. So this is a condensed phase, reaction-driven, coupled phase separation and phase transformation occurring under highly non-equilibrium conditions and extreme temperature and pressure. So the short of it is we're probably not going to be able to take off-the-shelf models to study this process, right? So, okay, we want to be able to predict structure, dynamics, speciation, and kinetics as our systems evolve under these kind of crazy conditions. And so in order to do this, we need models that can describe chemistry. They need to work under high temperature and pressure, and they also need to be fast. And so to kind of give you a sense for things, if we want to simulate the formation of populations of nanoparticles, well, a single nanoparticle might have in it 100,000 atoms. So we need to be able to go rather big. And then finally, we like models that are transferable or could be fit quickly. That way we don't need to spend a lot of time in the model development phase as we move from precursor to precursor. So this is work that we started quite a few years ago now. And so back then, this was a time before the sort of universality of ML potentials. And so we kind of had to choose between first principles methods, which are very highly predictive, but of course very computationally intensive, precluding access to the scales that we were interested in, or conventional reactive interatomic models, which are by comparison extremely computationally efficient. But here the problem is that they are not well suited for modeling the types of phenomena that we are interested in, and developing new reactive classical potentials is not a trivial undertaking. And so this accuracy, efficiency, capability gap drove us to become very interested in developing our own machine learned interatomic models. And so I'm going to talk a little bit about that. So to put things in perspective, when we started working on this, again, this was kind of the Wild West days of ML potentials. There weren't many out there, and there weren't any that could do all the things that we needed. And so we decided to develop our own, which we call Chimes. And so I'm going to give you a sort of quick highlights reel of what Chimes does and how it works. All right, so Chimes is a compact, physics-informed machine learned interatomic model where we are going to describe our total system energy through a many-body cluster expansion. And so to write down any one of these cluster energy terms, we use a generating function that looks like the following. And so we have two key ingredients. In purple, we're highlighting the sum over this ty term. This is telling you that we're using Chebyshev polynomials as our basis functions. And then this product symbol is telling you that when we deal with our many-body interactions, we describe them as the product of interactions for constituent atom pairs. And so for those of you that work in the ML potential space, this is also telling you that our descriptor is essentially the fully connected graph between the constituent atoms that make up your n-body cluster. Okay, that's a lot. So for something simple like a two-body interaction, though, we can show that we end up with this very simple expression where each one of these t's is a polynomial of the subscripted order. We're plugging into that polynomial a transformation of the distance between our atoms, I and j, and then the coefficients out front. These are the parameters that we fit when we're trying to learn these ML potentials. And so we've heard a little bit about this already, but if we're just trying to develop a potential for a very simple problem, we might do this by first running a DFT MD simulation to get us our coordinates labeled with forces, energies, and stresses. And then we minimize an objective function that looks like the following down here, which is just saying that we want the forces on each atom predicted by DFT and our model to be as close as possible, subject to our fitting coefficients. And so if we kind of pause here and take inventory of what's on the slide, there's just a few things I'll point out. Again, Chimes it's rather simple, and it's a parametrically linear model. And so practically this means that we can generate parameters very quickly, and we can do this using relatively small data sets compared to a lot of the other ML potentials out there. Nevertheless, we're able to do this while still generating nominally quantum accurate models that are rather computationally efficient. And so this is a very sort of minimal example from a recent paper where we've developed a model for carbon that works from ambient conditions up to about 10,000 Kelvin and 100 gigapascals. And so this is just some of the validation data that we have in here. So your prototypical parity plot that's comparing the energies that we get from our reference method and Chimes. These are cold compression curves comparing with a lot of other popular ML potentials out there. And we find that our model for at least this temperature pressure space that we're interested in is the most accurate and also the most efficient on the market. And so again, Chimes is rapidly parameterizable and capable of quantum accuracy by design. So today you're going to hear me talk about its use in studying phenomena occurring under extreme conditions, but I just want to briefly point out that it's a generalized model. It's application agnostic, and in fact, it's really been an enabling technology for us. So this is just some of the different systems and problems we've applied it to over the years, which cover the gambit from modeling coarse-grained systems to looking at the structure in liquid water. But I guess a key point here is that if you look at the work that's going on in my group right now, every single project is using Chimes in some way or another, because there would not have, without these ML potentials, you would not be able to ask the questions that we're currently asking. So again, a very powerful tool. So one other thing I will call out is that Chimes is completely open source. And so I just want to kind of talk you through briefly what goes into Chimes. We have three main packages. We have Chimes LSQ, which is our most basic fitting code. You give it a training trajectory and some hyperparameters, and it gives you a model that may or may not work. Then, we heard Denny talk about how important data set selection is. And so we have our active learning driver, which is our autonomous sort of AI-driven model development workflow that incorporates a lot of the tools that we develop to help inform your data selection schemes. And so in particular, in the sort of space that Danny showed, we are somewhere between the, needing to have chemical accuracy to also needing to have our models be robust. And so we're not quite looking for the spread of energy scales that Danny's entropy method might use. So if you see any papers from us, though, that put out new ML and AI methods for training potentials, they're going to be integrated in that active learning driver. I'll also note that it's completely modular and designed to work with all different types of packages. So currently it supports VASP, CP2K, and DFTB+ as your quantum-based reference methods, and LAMMPS and ChimesMD for your simulation codes. But it's designed such that, if you maybe are a Quantum Espresso user, you can write a Quantum Espresso module in less than a day for this. So finally, cool, you have a Chimes model, you want to simulate with it. You can do this using the Chimes calculator. So this is a multi-language API for evaluating Chimes interactions. You give it a Chimes model and some coordinates, and it gives you the forces, energies, and stresses. And I'll just note that it comes with a script that will install it in LAMMPS for you. So if you're interested in this, we have the stable versions of our code in the RK Lindsay GitHub page. If you're interested in seeing what we're developing at any given time, you can check out the Lindsay Lab GitHub page as well. So, okay, that's all I'm going to say about Chimes. And so I want to get back to the science story here. So let's briefly recap. We are interested in developing a new tunable synthesis capability, high throughput tunable synthesis capability for nanocarbon materials. We've come up with this laser shock method, but we want to see if it's actually going to work. And so we wanted to use simulations to assess that feasibility. The problem was that there were not models that could describe that phenomena. And so we developed Chimes to allow us to do so. So now that we've got all these tools, let's go and see what we can do with it. All right, so again, this is what this process should look like. Step 0 in assessing the feasibility of this is picking a precursor to test this out on. And so we went through the literature and found these old shock experiments from back in the 80s, where they took a cryogenic liquid carbon monoxide precursor. And so what we're seeing over here, let me get my pointer, is when they weakly shock the system, so they're shocking it to low pressure, their data fell on a theoretical equation of state that basically says there's nothing interesting happening, you're just kind of compressing the system. But when they shock it harder, you can see that these data points here are falling on a theoretical equation of state curve that's accounting for the formation of carbon products. And so we thought to ourselves, okay, well, if this might be a system for which we could potentially form carbon nanoparticles. And so what we wanted to do was to use our Chimes simulations to predict whether or not these carbon nanoparticles can form from this system. And if so, if we can say something about the how. Now, in order to do this, we needed to develop a Chimes model for the system, which means we had to run DFT and D simulations to generate our data set. And so, something interesting comes out of this. So if you look at the DFT and D simulations that we ran, you don't really see anything particularly interesting happening. There's some chemistry, CO turns to CO2, and there's some oxygen floating around, but no evidence of nanoparticle formation. But using our model, we can scale things up to, in this case, over 1 million atoms. So these two boxes are shown to scale, and we're seeing a completely different picture emerge. So what we're watching is with atomic resolution, formation of a population of 5 nanometer nanoparticles. And so this was really exciting because this simulation suggested that, yeah, this laser shock technique could actually work. And so based off of this, my experimental collaborator, Mike Armstrong, actually built up a platform that allows him to run these experiments on the same precursor, the same timescales and overlapping length scales with our simulations. And so from his experiments, he recovers particles that look like this. And so this little Pegasus-looking creature is actually an agglomerate of smaller particles outlined in these red semicircles that turn out to be the same size, shape, and chemical composition as what we predict in our simulations, and they form on the same timescales. And so we have this compelling validation of our simulations that now gives us the green light to dig in a little deeper and say something about how this process works and potentially provide some guidance to our experimental colleagues on how to tunably deploy this process. So, for example, we can create plots that look like this. So this is telling you about the radially and time-resolved evolution of the composition of these particles as they form. And so why is this useful? So in our system, our particles, when they first form, are a mixture of carbon and oxygen. So let's say somebody wants to make oxygen-doped nanoparticles. We can provide guidance on how large, or the duration of that laser pulse in order to get you a given target composition. So this plot over here is showing how the size of the particles grow as a function of time. And so data like this is useful because we can now also provide guidance on, if you want to make particles of this size, again, your pulse duration should be roughly yay long. Now, the shape of this curve is also telling us that these particles grow through Ostwald ripening. And so basically that means if you have particles of two different sizes, your small particle is going to shrink and the carbon atoms that were in that particle are going to diffuse and cause the bigger particle to grow. But the question is, what's the transport mechanism of the carbon between those two particles? And so we can run additional analysis like this. So here we're looking at the time-resolved composition of the fluid, that reactive fluid that's solvating these particles. And what we found from this plot is that there's really no free carbon in the system. And so that means as your carbon is being shuttled between particles, it's happening through reaction-mediated transport. And so why is that interesting? Well, if I change the composition of my precursor, I'm going to change the chemistry that's ultimately shuttling that carbon between these particles. And so that gives me another way that I can modulate the slope of this curve, and so ultimately the kinetics of particle growth. And so again, from these simulations, we're already able to derive some insights that can help take this from a technique that, yes, can produce particles on in this case, microsecond timescales, and turn it into something that we can start thinking about deploying tunably. So that said, this study just kind of scratches the surface of what we need to know, right? So for example, this process works by taking your precursor from ambient conditions to up above the carbon melt line and then quenching it back down below the melt line. So we need to know things like, where are our carbon phase boundaries? What are the kinetics for phase transformation? And how do these things change when we start dealing with finite size systems? We also need to understand the role of chemistry in greater detail. So for today, I'm going to tell you talk about these first 3 points, which deal with phase transformations in carbon, which is work that's being done by my graduate student, Yanjun Liu over here. So I told you guys that we developed a new carbon model recently, and so he's deployed this to map out the carbon phase diagram. So this is for bulk carbon under nominally equilibrium conditions. Which is great, but when you're dealing with nano-sized particles, you have surface energy that's going to modulate where these phase boundaries are. And so we have studies going on right now where what we're doing is taking liquid particles, liquid carbon nanoparticles of different diameters, and we put them in an argon bath, and we can cook those at different temperatures and pressures. And so this is an example. So these are two 4-nanometer particles that start out as liquid at 3,500 Kelvin and 2 different pressures, 15 and 50 gigapascals. And basically what you do is you just run these simulations and you ask, okay, well, what phase of carbon do I get out the other end? And so for our low pressure case, we're getting these graphitic nano onions. So again, those concentric sort of buckyball-like layers. And in this case over here, let's see if we can play that again, we're going to end up with nanodiamond. And so we do this for a whole grid of temperatures and pressures. And this allows us to construct, in this case, this is the 4-nanometer nanoparticle phase diagram. And we are doing this for particles on the order of 4 to 10 nanometers. Okay, so this tells us, if we want to get a certain allotrope of carbon, where we should be targeting in temperature, pressure, space. So we can take this a step further and say, okay, well, what are the mechanisms and kinetics of solidification? So here we are still looking at this 3,500 Kelvin and 50 gigapascal state point. And this is our 4-nanometer particle we saw before. This is now a 10-nanometer particle. And when we run these simulations, we're going to observe that the solidification occurs through a classical nucleation process. So in the case of the 4-nanometer particle, there's a single seed that converts into a nanodiamond. In the case of the 10-nanometer particle, because we have a bigger volume, you have more seeds form, and so you grow this sort of polycrystalline nanodiamond. But nevertheless, in both cases, classical nucleation. What we find if we change the temperature just a little bit, and I have to apologize, these movies look to be of low resolution here. So we change the temperature by 500 Kelvin, and now we're looking at 6 and 8 nanometer particles just for fun. What you see is that we begin forming those concentric layers that's characteristic to graphitic nano onions. But in the 6-nanometer case, if you watch the middle, and in the 8-nanometer case, if you look here and here, you see that after you start to form these layers, you begin also nucleating diamond. And so we have this kind of 2-step nucleation mechanism. So why is this important? Well, we're learning things like the following. We can see that very small, at least for us, changes in our temperature and pressure conditions can manifest very large changes in our solidification mechanism and the corresponding kinetics for that. This is also giving us insight into how we might make even more complex particles. So for example, perhaps we can play around with this more and figure out how to make core shell particles that are perhaps diamond at the core and graphitic nanoonion at the exterior. And so again, through these simulations, we're able to start to derive the insights that we need to turn that shock synthesis into a tunable process. Okay, so with that, I'm going to wrap things up. I want to thank the various funding agencies that have supported this work. This is work that I started when I was a postdoc at Livermore and have since continued through the work with my amazing collaborators there. And now my students are taking over all of this. And so I'll stop there and would be more than happy to take any questions.
Let's give a round of applause. All right, if anybody has questions, please come on up to the mic.
Thank you for the interesting talk, and I hope to maybe get a chance to talk with you afterwards. When you say ultra-fast laser, I'm assuming it's like a femtosecond laser, and your precursor is?
And this, so for the simulations I was showing before, the big ones, it's a cryogenic liquid carbon monoxide.
Oh, carbon monoxide.
Mm-hmm.
Okay. I just want to make sure. And so are you using like ambient atmospheric conditions, or are you using like a shield gas?
So for that case, the experiment is done. There's a little baby cryostat that's cooling down the sample. So the actual sample was at like 80 Kelvin or something like that during that shock experiment.
Okay. So it's like atmospheric conditions.
Oh, right. The pressure, yes.
Okay.
Mm-hmm.
Could you check? We have any online questions? Oh, we haven't. Maybe we can.
When you mapped out that phase boundary, how confident do you feel about where that boundary is? Is it just like after observing it for a few nanoseconds, what happens?
Yeah. So there is a much more complicated version of that figure that exists that I am not showing because it would take me like 5 hours to explain it. So there's a couple things. So the graphite diamond phase boundary experimentally is actually very well constrained. And so for that, that was just based off of thermodynamic integration calculations. You can compare it directly to experiment, and we match up very beautifully. For the melt line, that's a little bit trickier because there's two main methods that you get high pressure phase boundaries. One of them is using something called a diamond anvil cell, which has diamond in the name, which means it's degrading as you're trying to measure your melting point. So you can't really rely on that. And then the other method is shock-based techniques, but the experiments are so short, it's very, very difficult to get temperature measurements. So we can compare to experiments, and there is agreement within the error of the experiments, but that's not really enough to say this is, perfect. So in this case, what we did is compare to some DFT predictions at high pressure, and we can show that that maps up, as well as some predictions from other ML potentials that have overlapping domains of applicability. So I think the diamond melt line we're pretty confident on, whereas the graphite melt line, there might be some kinetic effects that are in play here. And so that's actually something that we're exploring right now.
Thanks.
Mm-hmm.
We have 2 online questions, and then we'll take a final in-person question. So Ivan Petronovich online asks, what method do you use to distinguish between diamond and onion structures?
Aha, so we're using an order parameter essentially for this. So the order parameter takes in the coordination number and the angles between atoms. And so, yeah, that's basically it.
Okay, thank you. And we have another question from Sagar Patil. Question for Lindsay. What force fields did you evaluate before realizing the need to develop chimes? After development, how does chimes compare with the existing force fields in terms of the criteria you laid out in the initial slides?
Yes. So when it comes to modeling systems like this, your choices are pretty much ReactFF. There's not a lot of reactive potentials out there. So ReactFF is good for a number of reasons. It's good for, well, insofar as there are parameters out there that you can use. Where it tends to have challenges is when you're dealing with very high pressure conditions and when you're dealing with things like phase transformation in carbon. So when we were deciding whether or not to do this, we basically ran a series of DFT-MD simulations to look at speciation, We looked at, phase properties of carbon and so on, and just found that, the existing parameter sets weren't sufficient for our application. And again, developing new parameter sets for that model is, it's a little bit of an art form. So yes.
All right, thank you. All right, we had one person in person. You sure you don't want to ask? We have time. Excellent. Okay, I'll answer by an online question. I think that's it for now. Oh, yeah. Okay, great. Let's give Professor Lindsay one more round of applause. Thank you very much. All right, well, that wraps up the morning session for now. I have 3 announcements. So first of all, for online speakers and anybody in person here, the organizers wanted to remind you that we are live streaming and recording. So as you're shuffling through files and getting everything on Zoom, just if you have anything private, make sure to obscure that. So that's announcement 1. Announcement 2, or rather question 2 for the whole audience is we will be having a dinner later that we wanted to get a head count for to make reservations and just make sure we have everything in order. So who tonight can come to the dinner? Please raise your hand. And oh my gosh, okay, wait, 1, 2, Mark, are you going? Yeah, okay, 1, 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 16, 20, 25, up to 26, 27. Okay, about 30 or so. Okay, all right. It's just a rough count. All right, so we got about 30 or so. All right, great. Thank you, everybody, for that. And then finally, we have coffee and water out in the lobby. So please enjoy your break. We'll meet up again in 10, 15 minutes. Thank you.
Hello. Can you hear? Hello. Can you guys hear anything? Yes.
Hey, Eduardo, we can hear you. I
All
just
right.
wasn't streaming.
No problem.
But it's fine. All right, everybody. Thanks again for coming. We are now in the second half of the morning session, and I would like to introduce Eduardo Bringa, who will be speaking about spin lattice dynamics of magnetic nanostructures, domain walls, defects, DMI, and machine learning insights. Take it away.
Thank you very much, and thanks for the opportunity to share some of our work here in Mendoza and together with many collaborators. So, first of all, I'd like to remind everyone that this is a huge advance that was made possible by the spin package in LAMMPS, where you simulate not only the usual, the atoms, the molecules, but also the spins, the magnetic degrees of freedom. And if you do that, then you assign this spin to each atom, and then you can calculate things like magnetization versus temperature. Here on the left, you can calculate hysteresis curves. You can look at finite size structures like nanoparticles. And there are many new options that make possible comparison with experiments. But I'll focus on a few of these examples. And in particular, I want to start showing some domain wall motion in iron and cobalt nanowires. And this is a collaboration made possible by contributions and calculations, mostly from Fernando Carbacho and Hugo Cross, that are directed by Samuel Baltazar. And as you can see, there is a very simple model for a domain wall motion where the velocity depends on basically the exchange, the damping, the external field. And if you use this very simple model and compare with the MD simulations, and these are simulations for two different anisotropies, you see that the agreement is actually excellent. Okay, so what we do is propose that the magnetization has this simple, analytical shape, and then we can track the motion of the wall and obtain a velocity. And as I said, we obtain excellent agreement with this very simple analytical model. Now, what happens when you go to a defective nanostructure, like a nanowire with a void? And this is a very simple, like non-magnetic defect. And one could expect that there is spinning of this domain wall as it advances, but actually, we are using fairly large magnetic fields, so actually the domain wall does go across the void. You see that as it's going across the void, of course, that transition can change. And here you have a movie of what's going on. And if you look at the position of the world, you see that far from the void, there is this very simple linear behavior, but actually the domain wall speeds up when it's approaching the void, and then it slows down and goes back to the initial velocity. So the domain wall width changes, when you're in contact with the defect, and that change also modifies its velocity. So basically, the idea here is that in a domain wall, you're basically passing from one orientation of the spins to the opposite one. And in this case, the fact that there are some less spins because of the void made that transition easier. So that's why you have the initial speed up, and then you recover, to the original place. So atomistic spin dynamics with LAMMPS, where you have the lattice relaxing, for instance, around the void, could open up the possibility to understand a lot better what happens with magnetization at these nanoscales. And one thing that for us was very important is that micromagnetic simulations, which are more or less the standard to compare with experiments, compare extremely well with our atomistic results, even though in these micromagnetic simulations, this spherical void is actually made of cubic voxels, like in Minecraft, everything has like a cube shape. Now, as another example that I wanted to share with you is the issue of the skyrmions, which are these very interesting topological features where you have a topological charge because the spins, follow a particular type of twist in the material, and you can, for instance, map a 2D spin texture to some 3D mapping to try to understand what's going on. Now, skyrmions are important because they may be used for information transfer and some other technological applications, and these may have applications, for instance, in quantum computing. This is a collaboration together with a group from the Universidad de La Plata in Argentina, Flavia Gómez Albarracín and Diego Rosales, and Gonzalo dos Santos is the one doing this in Mendoza. He will have a talk later today, the last talk in the afternoon. And for instance, in this Kagome lattice that has a very particular topology, so what we need is to have a Dasiloszynski-Morilla interaction in plane and also out of plane, okay? And the idea is to see this model has been extensively studied with, like, for instance, Monte Carlo simulations for a fixed lattice. So what happens if you apply a tensile or compressive strain, which is something that we can easily do with LAMMPS. But then we realized that we had a problem, and the issue is that this model, where you have one Dasiloszynski-Morilla vector, actually is mapped into LAMMPS by a vector where you have a cross product by the versor joining to a spin. And actually that poses a problem when you have in plane is okay, but when you have this out of plane, this doesn't really work because there is an asymmetry. And we hacked the code. Gonzalo did a few changes, and with a very simple hack, we were able to do skyrmions in this Kagome lattice with both in plane and out of plane Dasiloszynski-Morilla, and he'll be talking a bit more about some of the results later today. So the important result is that thanks to the strain, okay, now you change the phase diagram, and actually you can make the skyrmions, survive at the given temperature in a larger region of the phase diagram. And you can see also that, for instance, for tensile strain, actually you go from having skyrmions to having something like fried eggs, okay? And in this case, actually, when you see all green here, this is coloring with one component of the spin, but actually if you color with the in-plane component, there is some structure subjacent to this. And when you add the compressive strain, again, you change the shape and size of the skyrmion. Now, what happens when you try to understand a bit more what happens with these skyrmions? And one will be interested to know, well, do the sizes change? Their mobility, it has a large variability or not? So we pair with some machine learning experts and Universidad Nacional de Cuyo in Mendoza, and they use computer vision techniques to check for instance, for skirming size, skirming radius. In this particular case, is fairly constant. And one thing, for instance, that was a challenge is that in computer vision, you do not have periodic boundary conditions. Okay, so people are not aware of what periodic boundary conditions are in this context. So we have to hack a bit the code to be able to handle those periodic boundary conditions.
Okay, you have about 5 minutes left.
Then you can analyze different regions of the phase space, the gas, the liquid, and the crystal, and get the velocity, the RMSD that gives you the diffusivity. So this, we think, is a powerful tool that can be used for many, many different conditions. And I want to start closing looking at the last problem of the collision of magnetic nanoparticles. And the collision of two iron nanoparticles is important for many astrophysical settings, for instance, having to do with micrometeorites and so forth. And in this case, the idea is that if the collision is strong, the stress is large, and then you can have a BCC to HCP phase transition, and the HCP phase is non-magnetic. So what happens in this case for the nano size is that actually not much HCP is formed, mostly because you get a release very quickly from the other side of the nanoparticle, which is very small. And here you have the outcome of the magnetization. You start with two particles that are ferromagnetic, okay, and because of the collision and the heating, actually you are a little bit above the Curie temperature. This becomes non-magnetic. But then if you cool the nanoparticle, you align the spins again. So at the end, you do have a very significant magnetization. Here you have the temperature of the system, the lattice temperature that is very high because of the collision and then cools down, the spin temperature that joins the lattice, and here we're using the Nil anisotropy term that was inserted by Paulo Nieves in the spin package. And then the magnetization, as you see, again, as you approach the Curie temperature, it goes to 0, but then during cooling, you do recover the magnetization. And the next step for this is to use the new package developed by Svetoslav Nikolov that includes non-fixed magnetic moments and also the possibility of dealing with this issue that the HCP is non-magnetic, okay? So we have modified that to also be careful with the fact that the surface atoms in the nanoparticle don't have a well-defined Voronoi volume, so we have to put a cap to that. So I like to finish with that and look forward to any comments you may have on the presentation. Thank you very much.
Thank you, Eduardo. That was great. All right, do we have any in-person questions? We have 2 minutes for questions. Anybody? Okay, how about online? Let me check real quick. All right, I think that's it for today. Thank you, Eduardo. Thank you.
Thank you.
Welcome. Oh, you're very welcome. Let's welcome our next speaker, Alberto Fraile Garcia from the Catalan Institute of Nanoscience and Nanotechnology. They will be online, and their talk is titled High Velocity Dust Impacts in Plasma-Facing Materials, Insights from Molecular Dynamics Simulations. So go right ahead, share your screen, and take it away when you're ready. I'm not sure if you're speaking, Alberto, but we can't hear you yet in the auditorium. We can see you now.
Can you hear me now?
Ah, everything's good. We can hear you. Thank you. I'm sorry, now we can't hear you. Sorry. We can see your mouth moving. It looks like maybe there's a poor connection. Okay, we'll just keep trying. So we'll relax a bit in the room. Yeah, we still can't hear you. Okay. All right. Okay. It looks like we're having, I'm so sorry, Alberto, we're having these audio issues. We might need to swap you out for now to keep things moving along. Do we have a time?
Just put him at the end of the session.
Okay, we'll put you at the end of the session at about 11:45. I hope that's okay with you. Apologies. We do have some Zoom chat or something. Okay. Okay. All right. I think then we will move forward and we'll have Lucas Hale next. I think you're in person, right? Lucas Hale? There you are. Okay. I think Richard will, yeah. Okay. So Alberto, Richard will work with you offline to get the audio stuff resolved. In the meantime, Lucas, if you wouldn't mind coming up. Come a little earlier. Okay, apologies for the technical difficulties, but we'll get going in just a minute. Okay, so we'll come back to Alberto's talk in about an hour, a little less. And in the meantime, we will bring forward the talk from Lucas Hale from NIST, National Institute of Standards and Technology, who will be talking about NIST IPR, complex defect and dynamic structure predictions. Thank you for coming forward a little early.
All right, so I'm going to give a couple slides for the newbies just to say what the NIST Interatomic Potentials repository is, and then show you all the really cool stuff that's coming out pretty much right now. So why an interatomic potential repository? It serves as a centralized location where you can find and explore existing interatomic potentials, download their parameter files, and have confidence that the files you download have known provenance, so that you're going to have predictions that are consistent with the original authors and anybody else who cites that specific potential. Additionally, you can have multiple potentials for the same elements. They behave different ways. You can have even, like we've seen before, the traditional and the machine learning potentials can have issues if you're exploring regions outside what they were originally trained for. So we're doing our best to collect lots of different materials properties across the interatomic potentials, so you can easily go on there, compare how they behave in different ways. And with all that, all the data we're trying to do, and as well as the computational tools associated with those potentials, we're trying to make open source, easily accessible, and easy to use. So the three primary sites for the potentials repository, the first one up top is the classic static website. It's nice and pretty. You can go on there, select the elements you care about. You see citation listings. You can click on the potential and see a whole list of properties associated with those potentials. The second one is actually the underlying database that we're using for it. It's not quite as pretty as the static website, but it's a lot more dynamic. You can go on there, you can do searches, explorations. It also has an entire database of the potential specific relaxed crystal structures. You've got defect input parameters, and raw and process calculation results are all in there. Finally, if you just care about the potential parameter files for doing LAMMP simulations, you can go to this GitHub repository down here. It has all the parameter files for LAMMPs. And so you can just in like one download of that repository or cloning it, whatever, you can get all the potentials, all the LAMMP supported potentials in the repository. And then the supporting Python packages that have been developed through this project is potentials, nice, simply named. It provides user-friendly APIs for that database, so you can easily query, find, explore the existing potentials, and set up kind of your own local potentials database if you wish. Then Adaman actually inherits everything from potentials and includes the ability to build, manipulate, and analyze atomic structures, as well as set up and run LAMMP simulations. And then finally, IPRPy actually serves as a collection of the full complete property calculations that we use for the repository. So you can go on there, you can select the calculations you want to run for yourselves. You can easily build kind of multi-calculation workflow tools and management scripts. So you can, if you want to piece all the calculations in whatever order you want to do, you can do that. And finally, it actually has the APIs to then access that raw data in the public database. If you're interested in this kind of stuff, I'm giving one of the breakout sessions tomorrow and we'll go over a lot of those cool features. So as for the new stuff, in the last year, I've uploaded pretty much most of the raw calculation results that I've done over the last few years. So there's now 1.7 million records in this database. That includes the interatomic potentials, crystal prototypes, defect input parameters, potential specific relaxed crystals, bulk crystal properties, crystal defects, and liquid properties. You can search, view, and download the results by either going directly to the website or through the IPRPy Python package. And now for the other really cool new stuff, we've got new properties content that's coming up on the website right now. You can preview it by going to our testing site. So the normal site +/testing at the end. And the new properties include dislocation core structures, lattice and elastic constants versus temperature, liquid radial distribution functions, diffusion and viscosity versus temperature, free energy based thermodynamic properties for those crystals and those liquids, and melting temperature estimates from the two-phase equilibrium simulations. Currently, most of the results up now are focused on EAM potentials for no other reason than they are just simply cheaper to run, but we're planning on eventually escalating this to all the hosted LAMMPS compatible potentials. For the dislocation cores, right now we have over 850 BCC screw dislocation cores and roughly 700 of the edge type on 2 different planes that are currently available both in the database and on that testing site. We also have a few silicon dislocation screw cores in the diamond cubic that are in the database, and they'll be in the testing, or at least the website, whenever I get that updated. And the face center cubic calculations are still running. They're a little bit bigger because you have to use a periodic array due to the dislocations dissociating. So hopefully we can see if this now works. We're, of course, always trying to do live stuff. So you go to the potentials.nist.gov database. You can go data exploration, search by keyword. There's a list of all the calculation results we have. We're going to select dislocation monopole. We're going to pick the Chamaty iron potential, go screw core. And of course, this is in the way. Search. We get 3 results. So the middle one actually is an error, so we're going to ignore that one. But the other 2, I pulled up in separate tabs. So you can see here and here, where the difference between these 2 records is this one is the native LAMMPS version of the potential, and this is the OpenChem version of the potential. And if you scroll down, you get the nice Nye-tensor differential displacement plot. And if you want to, you can download the final relaxed dislocation core structure, as well as a dislocation-free reference structure for analyzing the core. And then if we, hold on, I can't see it. If you go to the static website, you can scroll through all the previous properties we had. You get down to the new guy, the dislocation monopoles, is a description of what we did. And you can see there's the screw core, edge 110 and edge 112 for that, as well as the downloadable dump files at the bottom. Right, and then, as I said, I'll give more information tomorrow, but you can also use IPRPy to do the queries. So you essentially interface with the potentials database, say you want dislocation monopoles, give it some delimiters about what you want, you download all the records, you can explore the metadata for further parsing, and then if you want to, you can automatically download that final defect configuration and then import it into Adaman for further manipulation and analysis, whatever. Moving on to the dynamic calculations. So all the lower boxes here are actually separate calculation methods, and this is simply showing the workflow where I start, in the case of the crystals, the solids, I start with the 0 Kelvin relaxed structures, relax them at 50, take the final configuration, pass that to the next 50 Kelvin, as well as the child property calculations down here. Liquid, same type of process, only I'm starting at a high temperature to get the melt, and then decreasing by 50 Kelvin and passing it to the properties that are interest of liquids. And so rather than show the boring things, we can go to the website again. And so this potential we got down here, you can see lattice constants as a function of temperature, elastic constants. There's FCC, here's HCP. You can say, click on one of these, it pops up an interactive plot. We can say maybe turn off A and B, there's the C. Go back. Scroll down, you get radial distribution functions, diffusion as a function of temperature, viscosity as a function of temperature. Here's the melting temperatures. So you can see that we have 2 reference crystal structures for computing those. So you got the FCC and the HCP. So about 1145 to 1150 is the range you see. And if you come down here to the thermodynamic properties, you've got the energy curves for the solids and the liquids, volume, delta Gibbs free energy. And if we zoom into this guy here, where the liquid crosses the solid, you can see that it falls nicely between 1140 and 1150. So it exactly matches what we see with the two-phase simulations. There's also entropy. It says entropy, enthalpy up here, but that's the typo. That's why it's on the testing site. I'm trying to find all the deep bugs and everything. And then heat capacity. So yeah. So yeah, so I pretty much just wanted to share all the cool new stuff. If you have any comments, feedback, feel free to email potentials@nist.gov. If you have potentials, submit them, put them in the repository. It makes it much easier for people to find your potentials, and therefore you're going to get more citations. If you have any feedback on the new calculations or the existing ones, if you have any ideas for future calculations you want to see in the repository, let me know. And finally, with the current kind of government funding uncertainty, the best thing you can do right now, if you like the Interatomic Potentials repository, and the thing we do is to send positive comments to that email address, say who you are, who you work for, and why you think the repository and the tools are such a great thing. So.
Great, thank you. Give them a round of applause. And let's send an email. Yes, thank you for this. All right, do we have any questions in the room? If you could come up to the mic so that the folks online can hear.
Hey, you mentioned about the interatomic potentials, right? So I just wanted to know, like, for the given interatomic potentials, do you have on the same site or like the same blog, do you have any information related to for what kind of structures those potentials can be used?
Yep. So if we go up, he's asking about the structures for the interatomic potentials. So if you go up here, there's this big table of all the crystal structures that we have computed for those guys. And we do 3 different relaxation methods. So the dynamic one is the most robust. And then the other ones are for if you say you want to compare to DFT or something where they haven't really fully relaxed the system. And you can see which one's the most energetically favorable and the lattice constants and everything.
So this table can give us idea for like what kind of structures for which we can use, right?
Yep, yep.
Thank you.
Thank you for your question. Anybody else in the room? All right, and we don't see any questions online right now. Remember that you can probably put them in Slack later and we can have Lucas answer them online if you have questions later. Okay, I think that's it. So thank you very much. Next we have, yes. Next is we have Fraser Burks, who is right over here, who is coming all the way from the University of Warwick in the UK. And today, Fraser will be talking about ML-Mix, a LAMMPS package for force mixing machine-learned interatomic potentials.
That's right. Is this the mic I should be using?
Yeah.
Yes. Can I take it out or is it? Hello, everyone. This is great. Very glad to be here. Thanks very much. I feel like I might be the only UK person here, but if so, it's great to be representing the UK. So all the way in Albuquerque, New Mexico. So yes, today I'm going to be talking about a LAMMPS package, which isn't actually in the official LAMMPS repository yet. It's still kind of in a GitHub, which is public. And this package, right, essentially has been developed to mix together different potentials inside of LAMMPS, right? And you might think, why would you want to do that, right? So let me just kind of pull some examples out of the literature for you, just kind of, I think, illustrate something which maybe motivates this method, right? So first up, this is a simulation of hydrogen embrittlement in steel. This is a simulation of stress corrosion cracking in silicon, and this is a simulation of nanoindentation in tungsten. Sorry, I'll move out of the way. I don't want to block the view. And the question is really, what things do these three simulations have in common, right? And I think there's some really obvious things, which are that they have very large atomistic domains and they run for pretty long MD timescales. But there's actually something else they all have in common, which is that all of these things have spatially localized accuracy requirements. And you might think, what do I mean by that? Well, if you look at this simulation of, for example, the embrittlement, the dislocation, where you have a hydrogen diffusing around the dislocation, the only part of that simulation domain that really has to understand how to interact with hydrogen are just the atoms that are next to the hydrogen in any individual time step, right? And as we've seen today, right, there's a kind of increasing use of these expensive machine-learned interatomic potentials, right? And Danny gave a really nice talk about it earlier, but there's this really key thing with these potentials, which is this accuracy, this kind of trade-off between essentially exploration and exploitation, right? You want to make big potentials, which cover a lot of space, but are also very good at certain things. And I suppose, right, you could argue that in situations like this, you only need those really good potentials in very local areas of your simulation domain, because most of your atoms are doing very little. They're just kind of usually in a sort of high temperature bulk configurations. They're just kind of vibrating around MD bulk. So this is where ML-Mix comes in, right? So what ML-Mix is it's a package to do this kind of spatial mixing inside of LAMMPS. So the selective application of different potentials. And the aim of this, at least the kind of original thinking of this, was to apply high accuracy potentials only when necessary in a simulation to allow you to speed up. But actually, having talked to some people here, I've realized that there's another application which is just actually using just a similar accuracy, but which are used for different things, right? So maybe you might have a potential which is good at excited states, right? And you switch to that in certain situations in a certain spatial region of your domain. And this package would work very well for that as well. So how does this package work? Well, I'm not going to go too much into this because I don't have too much time, but under the hood, it does something called force mixing. Now, force mixing is very familiar to anyone here who's done any QM/MM, because it's actually the exact same method, right? This is the exact same way that you mix together the DFT and your classical potential inside almost all QM/MM simulations. So the idea is that you start off with some mixed domain, right? And you split it up into two non-interacting subdomains, right? And you evaluate the forces on those subdomains separately, where you add this kind of little extra layer around the edge of each domain, which is just, it's called like a buffer region. And the idea of that is just to make sure that your forces on your non-interacting domains are correct. They're sort of the forces that you would get if the whole domain was evaluated by each potential, but only locally, right? You then recombine these forces, and you do that every single time step. And what ML-Mix does is it does this inside LAMMPS, right? And it's completely C++, so it's just a single fix and a pair style. There's no kind of external Python dependencies. So what I want to do now, right? Because obviously there's lots of stuff to talk about in the development side, but I don't have too much time for that. So I just want to go through a couple of applications that I've used this method for, which I think just help kind of illustrate what it could be used for and, why I think it's quite cool. So this here is a simulation that wasn't run by me. Actually, it was run by someone in my group, and they were looking at plasticity in tungstens. This is the kind of glide of a screw dislocation driven under some shear stress in tungsten. And you can see this is a really big simulation domain, right? It's really, really large. And what he did is he used MLMix to isolate his expensive potential, which was trained to do the screw dislocation. So it was an ace potential. He isolated that just around the gliding dislocation in a simulation. And every other atom he modeled with a significantly smaller ace potential, so only around 400 basis functions rather than the original 2000. And this led to about kind of 4 times speed up, which is pretty nice. I mean, not enormous, but it's still a significant saving. And I guess the question is, did he get the same results? And this is the expensive results. So this is glide velocities at different shear stresses and temperatures for different glide planes, 2 different glide planes. And here is the mixed results, right? And you can see that effectively you get, within error consistently between the 2 methods. And for this cost saving you get, that's really nice. So that's the first application. The second application I'm going to talk about is something that I run myself, so I'm kind of more excited about it, and I think it's quite interesting. And I also think it's kind of very relevant to probably a lot of people here. And that's because it's looking at helium implantation into tungsten, right? And this is obviously kind of a fusion-relevant application. And the idea is, right, you have some helium atom and you have some tungsten surface, and the helium atom is moving towards the tungsten surface normally in this case. So, of course, you could do different angles and stuff, but what I've looked at is purely normal deposition at different energies. So this actually has been modeled before, which is partly why I chose it. And there's also some experimental data for this as well. And it was done in 2014 using an EAM, I believe actually at Los Alamos. And what they saw, right, is that with their EAM and pair potential, they actually couldn't reproduce the experimental data. So, all this kind of mixing stuff aside, this is already a kind of interesting problem, right? Can we actually get better? Can we do better than this with machine learning potentials, right? So that's the first thing I had to do anyway, right? Because I couldn't speed anything up unless I got something that worked. So the first thing I did, right, is I did something which I think is probably the right first point of call these days when you're tackling a completely new application with machine learning potential, which is that I took a foundation model. So I took the MPA foundation model, the MPA 0 medium, which is a MACE foundation model, and I applied it out the box to this problem to see if it would work. And did it work? No, it worked really badly, actually, unfortunately. So this plot here, actually, I should mention, is showing the reflection coefficient of the helium atoms, right? So essentially, this is looking at what portion of helium atoms reflect over many simulations fired at this surface. And you can see that what the MACE predicts, the foundation model predicts, is that huge numbers actually just go straight into the surface. So it really, really underpredicts the reflection coefficient. So, well, we thought, okay, maybe we can improve this. So what we did is we took a data set that we already had, right, which was a data set of tungsten and helium dislocations. It was nothing at all to do with surfaces or implantation, but it had lots of tungsten and helium in it, but we thought maybe it would just improve things a bit. And we fine-tuned to that. So we took the same model and we did some rounds of fine-tuning, only about 4 hours of training time. And we got this, right, which is significantly nicer. So it does look a lot better. It's still not perfect, but you can see that the main thing is for low energies, it's predicting now almost 100% atoms get reflected, which is, good, because that's what we see in experiment as well. And the final stage, right, was take a small amount of DFT data. So in this case, this was just looking at about 100 or maybe 150 configurations of actually snapshots from these simulations. So smaller simulations, but using this potential of helium hitting a tungsten surface, but a really small box. And we did the DFT of those again, only took an hour or so because it really wasn't that many configurations. And we fine-tuned that data and we saw this, right, which is a really nice imaginative experiment, which I personally was really happy and quite surprised to see because it's probably the first time in my life this has happened. So this is nice. And the next question is, can we speed this up? So this we ran on GPU. I think it's important to note these expensive simulations. And they're not that cheap with these big MACE foundation models. They're, particularly when you have big, deep cells, you have to use a few GPUs and it really starts to add up in price. And maybe here you have billions of GPUs, but in my group, we don't have that many. So I had to think of maybe a different way of doing this. And to do that, we applied MLMix. And we actually used, right, catering to my audience, we used the pure tungsten snap potential that was published by Mitchell Wood and Aidan Thompson, who are both at this conference in 2017. And we used that as the cheap potential. And then we just used our fine-tuned foundation model to model interactions around the helium. So you can see as our helium impacts the surface, we switch over to our expensive potential just to model those interactions, but all the tungsten atoms we still simulate with this super pure, the super cheap snap potential. I also want to note that to do this, I had to spend a couple months developing a Cocos version of MLMX to do this. So that actually also exists. And so this is all on one GPU. And you can see that what we could do with this, right, is we could do way more repeats. So it was about 10 times faster, maybe 12 times faster, the simulations. And that meant we could run 500 of these rather than 100 each of the repeats. And we'd also go to higher energies because we could go to deeper cells because the higher the energy, the deeper the helium goes in the system, right? So you had to increase the size of your cell. Sorry, I'm almost at the end, so that's perfect. So the other thing I want to show you very quickly is we didn't just measure the reflection coefficients, we also looked at the implantation depth. We didn't have good experiment for this, but what we can show is that the expensive and the cheap match really nicely, and the mixed match really nicely. I mean, you can see there's a little bit of disagreement here in the middle. That's actually just because, and I don't know if this is like a recognized phenomenon, I think it probably is. Some helium atoms tend to go extremely deep into the tungsten, at kind of quite a low probability. And that means that if you're only doing like 100 repeats and only 50 of those go in, and you don't see like any of those super deep ones, or already a couple of them, that can really skew your mean a lot by just missing out one or two of those. So when you have more and more, like more repeats, you get a much nicer kind of straight line, which is what we see in this mixed simulation. So yeah, this is also really nice. So with that, I just want to kind of, own up and say there are some limitations of this method. There's no such thing as a free lunch. And what I'm promising here is speed up, but you do have to sacrifice something, right? And the main thing you sacrifice, and this is true with any force mixing method, so you also sacrifice this when you're doing QMMM as well, is energy conservation. Oof, that's a big one to lose, right? And you also sacrifice the fact that there is no defined total energy. So that makes minimizations a little harder because you can do like a force criterion, but you can't necessarily do an energy criterion. I'm going to argue that the most important thing is the quantities of interest you're measuring, not necessarily energy conservation. And in practice, if you have very well matched potentials, the actual energy drift you see is very, very low. So I'm talking a few Kelvin over 100 picoseconds in a kind of NVE simulation. So clearly, the kind of shadow Hamiltonian the system's following in these force mix simulations is very close to the true Hamiltonian if you have quite well matched potentials at your boundary. But it's something you got to check, right? It's another thing you got to think about. So this is a caveat that I really have to mention. And there are also some kind of specific limitations to this package, which could be fixed in the future, perhaps. And the first of those is that not all pair styles are out-the-box compatible. That's a shame. So the kind of ethos of MLMix was to make something which is a complete wrapper. So it's like a pair style hybrid overlay kind of wrapper, which just calls pair styles inside it and doesn't care what's going on inside them and can mix them together. Unfortunately, to do that, you have to make some assumptions about what happens inside pair styles. That means that it works with almost all the ones written by people at Sandia. So it works with like Snap, it works with ACE, it works with Mace as well. It also works, I think, with all of the kind of basic ones like Leonard Jones, all those, etc. And UF3 as well. So it works with a lot of potentials, but there's certain potentials like, maybe the Allegro type stuff, the stuff that's been done at Harvard, which are more complicated and it doesn't work out the box with those. So that's worth bearing in mind. And some of the Cocos ones as well, it works with Snap, ACE, and Mace, I think, in Cocos, but it doesn't work with UF3, for example. Just because it's something they've done inside the pair style. But these are things that I'm hoping maybe we can have a dialogue about, but we'll see. And another thing as well is that some pair styles like EAM, if you try to run them in parallel, so you try to have lots of domains, which I use the kind of LAMMPS auto balancing to make the simulation work well in parallel. Because EAM has a synchronization step inside the compute function, because it has to form this embedding, right, and communicate it between processes, that acts as a synchronization point, right? And when you're evaluating potentials on subsets of your atoms, that can cause a big issue in your simulation. Basically, it can destroy your load balancing. It can really slow things down. And finally, at the moment, it's limited to only 2 potentials. Right, this is not something that's maybe fixed, but it would require a lot of coding to change that. So yeah, just want to end by saying it's on GitHub, and I'd love to talk to the LAMMPS developers about potentially bringing this into a more official thing to the LAMMPS package. I know it's very similar to what Ralph Drout's group has kind of done, but it's meant to be more general, so it's meant to be easy to use and has lots of potentials involved rather than just EAM. And yeah, with that, I can say thank you very much for listening. It's been great. Thank you.
Thank you, Fraser. Great job. Thank you. Excellent. All right. I didn't see any questions online yet, but if anybody in the room would like to hop up to the mic. Steve.
Thanks. Nice talk. So if you had a big system, lots of dislocations, they're moving around, do you have a way to sort of auto-detect where you need to focus those expensive potentials and everything else can be cheap?
Yes, we do. So that's how we did. Obviously, in this case, this was just a single dislocation, this simulation that I showed you. Let me go back to the GIF. this one. This is just single dislocation, but the way we do this, right? So there's two ways of classifying how to, pick your expensive regions in this kind of simulation. One is just using a LAMMPS group. Obviously, that won't work when you have a dislocation because the atoms involved in dislocation called change as dislocation moves. So what you can do instead is you can use like the output vector of any fix in LAMMPS. So what we did for this is we used compute common neighbor analysis. Then we used a fix to average that over time. And then we use that every 10 time steps to classify the expensive atoms, basically. So you can do, if you have 10 dislocations, it would easily do that, right? It would detect all 10 dislocations in the same way, and it would put your expensive regions on those dislocations, and that would work fine. It does get more complicated when you have lots of processes. So if you're doing a really parallel simulation, the load balancing can struggle a bit, the native load balancing in LAMMPS, because that obviously resizes domains dynamically. And if you have like expensive atoms which are moving, I think I've found that LAMMPS load balancing can struggle a little bit. But generally, yeah, that what you said would absolutely work, yeah.
All right. I think that's all the time we have. So thank you again, Fraser. Let's see. Yep, that. Yeah. Great job. Thank you. So Ethan Holbrook is next. I thought I saw him. Aha. Okay. Sneaking behind me. All right. Hey there. So next we'll hear from Ethan Holbrook from Purdue University, who will be discussing natural language to LAMMPS, LLMs as interfaces between researchers and scientific software.
Yeah, if I can get this shared. Nice. Okay, so yes. Hi, I'm Ethan, and here we go. So I want to talk a little bit about the typical procedure for somebody like me engaged in running atomistic simulations. So I take a script, a set of instructions for LAMMPS. I pass it off to our supercomputer, and then the supercomputer passes me back data. Now, how do we get these input scripts? So traditionally, I've gotten them either from previous group members or from my advisor or from literature, different papers in the literature. And then I will then go through the LAMMPS documentation to modify those scripts. And so this is great, but like the LAMMPS documentation is great, super helpful, but these still have a lot of complex syntax that we have to sort through. So these are all domain-specific languages, and with them being domain-specific languages, we are taking a compromise where to do all the complicated back-end math and physics that we require, we have these relatively simple commands in their place. So these scripts can be quite complex to get so these scripts can be quite complex to get the physics that we desire in our simulations. And to try to simplify that, traditional approaches have been like this one in the bottom right. So this is an example of a sim tool on NanoHub where we have basically the script is created in the back end by these drop-down boxes and tweakable parameters. And then we have the analysis out here. And so this is great, but it's only as flexible as the developers of this tool allow it. So with new tools, like what we have seen a lot of yesterday with the LAMMPS GUI, this is much more flexible in the user input and still supports the user in a lot of different ways through visualization and script creation in general, but it still requires a complex understanding of the syntax. So with all the advances in LLMs and AI, we want to see if we can use them to sort of bridge these gaps and cut down some of the barriers to making better scripts that give us good physics that we want to dive into. So LLMs have shown a lot of potential. One, from summarizing information from publications. I'm sure most of you have tried this out. And then as a code assistant, whether from simple auto completions like this I'm showing here, or complex debugging tasks. And then they're also becoming pretty good at extracting AI-ready data from publications. So this is sort of, I want to discuss this new possibility as a software interface. So going between the user and the interface to make these complicated scripts. Current efforts have already seen success. And this is an example of an Orca paper that came out recently where they create their scripts using a fine-tuned large language model. And largely, they are valid scripts that are actually useful. So we decide to look at it as an interface for LAMMPS. So in some of our previous work on archive in 2023, we ran through a few different prompts to try to generate some LAMMP scripts. So this is an example of one of them where we have a relatively simple system where we have a bulk nickel sample and we're heating it from 300 Kelvin to 2500 Kelvin. So we send this prompt into ChatGPT or GPT-4. This was back a while ago. And then we get out our LAMMP script. And then we tried to create different methods for evaluating its progress and its accuracy. And so going through this, we would annotate the scripts to see which commands were always correct, which commands are either sometimes correct or don't need to be a particular specific value. And then in red, we have our commands that are giving us something different than what we're actually asking for. So we looked at a few different prompts of varying complexities, and we have for very simple scripts, it does very, very well, giving us a valid LAMMP script, a script that runs, and then most of the time also giving us a script that accurately represents what we want. But as you increase this complexity, this falls rather quickly. So we say in our experiments it worked, sometimes. Can these LLMs be a general interface is this question that we really want to ask. And so these are the tasks that I do in my research. I've sort of simplified them, but we want to simplify the ones in green. Use as much infrastructure as possible to handle them. And so what I'm going to show you here is a tool that we have on NanoHub, and it's a little bit, and I'll be going through this along with my colleague JC at the workshop tomorrow. So we're adding in a few different descriptive parameters just to index the simulation. And then it goes quite quickly, but we added a ChatGPT API to generate this script. So on the left, we have our prompt, the same one that I showed you earlier. And then on the right, we have the script as generated by the LLM. And I'm now going through and editing it. So the script actually works completely fine, but the pair coefficient was not the same name as the one that I had, or the file, at least was not the same one as I had. So I changed the file name, I upload my potential, and then I scan the rest of the script. And as it looks good, I hit the run button. This is a little bit of a longer simulation. So instead of showing you, it'll skip ahead here in a second. But then we also have this part built in where we can generate a methods section from the input script, just like fed directly in to the API once again, and then outputs it. And you'll see that in a second. But here I'm downloading the log file to examine the results. And it looks like the simulation was successful. And so now generating the methods. So this, as a part of the 5 tasks that I do as a computational researcher, this has finished the run, but now we're looking at the analysis of the data. So we have a querying section to load in the data, and again, a similar prompt and Python script creation section for making a plot. So this will be a very simple plot showing all the properties in the log file versus the time step, but it creates that Python code, and then I'll click run and you'll see the plot. And very simple plot. If I want to look at other stuff, I can change this. So I say do subplots because you can't, break apart the individual values since their magnitudes are so different. But yeah, so very simple plotting and analysis for now. And so this is kind of the workflow as we have it, where we have NanoHub acting as like an infrastructure bridge between some of these steps. And then we have the OpenAI's API keys acting as a bridge between the other two. So there's still a little bit under construction here. And as the syntax poses such a difficult problem of getting that correct with these large language models, we've been thinking about ways to make it better. And so one way is by trying to add guardrails with a parser. So thank you. So the parser we create using these abstract syntax trees. So this breaks down all the commands that we have in a LAMMPS input script. And so as you'll see, we have a simple units command. And so you have the first breakoff go to token units. And then so this means that it recognizes the command units, and then it's expecting an additional argument called unit style. In this case, that would be metal, real, LJ, whatever your unit statement would be. So it captures that. Similarly with boundary, you have one boundary statement, and then you have, it's expecting then 3 different boundary styles, which could be periodic or shrink wrapped or whatever you may use. So this enables syntax error detection and can serve as a linter, something that most languages like Python or C have, where you can, before you actually run or execute your code, see if you have problems. So we have developed a workflow where we first run scripts through a sanitizer. And so what scripts? We have 4 different models and then 3 prompts. We revisit those of simple, medium, and high complexity. And for each of these, we do 10 scripts. And we want to see how they go through the workflow. So 7 of these 120 scripts are stopped by the sanitizer. So they have like really basic spelling errors or variable expressions that are never actually defined. And then we have the parser, where we see if the syntax is off in some way. And then we have the rest of the workflow where we see that pair style issues are the most common, where it mismatches like either the embedded atom model with a different potential file or something else, or the units are off in some way, or the region and group specifications are not correct. But so this is a pretty complicated workflow where all the scripts go, but in general, it does a decent amount. And we think that with this parser acting as a guardrail, we can at least ensure that the scripts are valid and runnable, but it's still a little bit of a stretch to make sure that they are completely and fully accurately describing the physics that we want them to describe. So, yeah, so I guess the main thing is that I want you to think a little bit more about how we could potentially use a parser like this, a linter, to sort of form good guardrails for generating these scripts and potentially making an automated workflow where, like Iron Man asking Jarvis to do some sort of scientific task, we can ask that of our computers as well. So thanks for listening. I'm part of Alejandro Strachan's group at Purdue. Yeah, feel free to ask questions. You can look at the tool here or check it out at the workshop tomorrow. Thanks.
Thank you very much. All right, any questions here in the room? Oh, comment. Okay, so Richard has a comment.
I'm just saying we're going to get really close to our running joke, the April Fool's thing, dump paper.
All right, Stan.
So how much of like custom training data did you put in, like LAMMPS specific, or is this just the stock ChatGPT?
Yeah, so these are all just the base models as well. So yeah, there's definitely a lot of room for improvement with that.
All right, anybody else? I think I see a stretcher over there, not a question though, right? Okay, just want to check. All right, no online questions. So thank you, Ethan.
Yeah, thank you.
Great, thanks again. All right, next we have James D. Tunakau. Thank you. Tunakau from the University of South Florida. And he will be talking today about phase transformations in glassy carbon under dynamic compression.
Hello? That was pretty loud. No, that's fine. So, good morning, everyone. I'm James. I'm a second-year PhD student at the University of South Florida, and I'm working with my major professor, Ivan Olenik. And I'm here to talk about our group's efforts in investigating the phase transformations in glassy carbon under dynamic compression. So first of all, what is glassy carbon? Glassy carbon is a metastable, pure, sp2 bonded or threefold coordinated network of twisted graphene sheets with a density that is typically lower than that of graphite. The amorphous nature of glassy carbon allows for structural configurations that are otherwise difficult to obtain in crystalline materials. So it is our interest to explore this amorphous nature in facilitating phase transformations or phase transitions. One example of that pursuit is found in a recent Nature paper published in May 2025 by Dominic Kraus, of which our group is a part of, where recent laser shock experiments at EOXFEL using the dipole laser found transformations from sp2 bonded glassy carbon to sp3 bonded amorphous carbon to a diamond liquid coexistence, and then to liquid carbon, each of which happening at higher shock intensities. However, the structural evolution of glassy carbon, or the atomic scale mechanisms of these phase transformations, especially at low pressures up to about 1.5 megabars, remains largely unknown. For example, the XRD analysis of these shocked glassy carbon samples in experiment allows us to estimate the densities, but temperature is otherwise difficult to obtain. However, molecular dynamic simulations allows us to provide full pressure temperature trajectories, local bonding statistics, and kinetics, particularly that of diamond nucleation. To that cause, it is our goal to perform large-scale molecular dynamic simulations to investigate the structural transformations of glassy carbon under shock compression. In particular, we want to investigate the fundamental physics of these phase transitions by obtaining, first of all, the shock Hugonio in terms of pressure, temperature, and density. We also want to look at the X-ray diffraction patterns of the shocked glassy carbon samples in simulation. We also want to look at fractions of diamond, sp2 bonded atoms, and sp3 bonded atoms, and ultimately compare that with existing experimental data. So we performed our molecular dynamic simulations using LAMMPS and using the quantum accurate atomic cluster expansion, or ACE, potential for carbon. So ACE is trained on roughly 17,000 DFT structures of carbon over a wide range of pressures and temperatures. And these simulations were performed on the Frontier, which is an exascale supercomputer at the Oak Ridge National Laboratory. So, cooking our glassy carbon sample is a multi-step process. First, we start with building individual graphite grains suspended in liquid carbon, and then we assemble multiple grains into a large simulation cell. We then raise the temperature to initiate nucleation, or the cross-linking of the sheets across the grains. But doing that alone leaves us with a sample that is that has a density close to that of graphite. But we know that amorphous carbon has densities that are lower than that. So we rescale the box to a target density, and then we subject that sample to a sequence of rapid compression and decompression at high temperature. And then we quench that sample to ambient conditions. So here we've got a comparison of the XRD patterns. This green XRD pattern is that of our simulated glassy carbon sample at the very top. This black XRD pattern is from a recent EOXFAT campaign ambient condition pre-shot sample measured in late 2024. And then these last two XRD patterns are from a paper by Thomas Scheel in 2019, where they compared 4 different glassy carbon samples. And as you can see, there is a good agreement in peak positions across all glassy carbon samples. Here we have a comparison between images of glassy carbon obtained from transmission electron microscopy from the same Thomas Scheel paper in 2019. And here on the right is a snapshot of the glassy carbon sample that we cooked. You can see some empty voids there, and that's because this is a thin 20 angstrom slice from front to back. But it is evident in both cases the prevalence of these wrinkled graphitic sheets. So we cook a large sample for our shock simulations with dimensions 50 by 50 by 1400 nanometers, which contains about 400 million atoms, or close to 500 million atoms. So what we do is we drive a piston through the sample at a constant velocity UP, and the Hugonio condition is achieved in the compressed region, or basically is the assumption that mass, momentum, and energy is conserved across the shock. So as you can see here, as we shock the glassy carbon at high enough pressure, at about 100 picoseconds in the shock simulation, you can see that if this is the shock front, behind that is this white material, which would be the amorphous carbon material. And dispersed among the amorphous carbon matrix are these diamond crystallites, which are these navy blue structures. Oh, sorry about that. So, however, because we can't run these shock simulations forever, direct shock alone does not give enough time for these diamond crystallites to nucleate or to reach their maximal size distributions. So what we do in a process called shock trapping is we cut a sample behind the shock front in the steady state region, and we remove the center of mass motion. We fix the boundaries along these edges via shrink wrapping, and then we integrate that sample in the NVE ensemble for a long time. In this context, we did it for 1 nanosecond. And then we finally measure the pressure, temperature, and density of the sample after the long shock trapping simulation. So here we have a movie of the shock simulation with a piston velocity of 4.4 kilometers per second. So what you're looking at is a visualization window right next to the piston, moving at the same velocity as that of the piston. So it would appear that the compressed region right next to the piston is at rest, while the uncompressed material is moving in the opposite direction. And as you can see, as the shock simulation progresses, the diamond crystallites continue to grow and nucleate, of course, with the appearance of stacking faults due to the misalignment of atoms in the rapid compression. Another way to look at the diamond nucleation in our shock simulations is to look at the XRD patterns of the shocked samples at different times in the shock simulation. So this gray XRD pattern where's my cursor? So this gray XRD pattern is that of the ambient conditioned glassy carbon sample, and the black is the XRD pattern of this snapshot over here. So this is a snapshot taken at 60 picoseconds in the shock simulation where there is 27% diamond, and you can see the 111 peak of diamond prevalent here, but 220 and 311 are yet to appear. At 120 picoseconds, we now have 36% diamond, and these two peaks have started to separate. At 180 picoseconds in the shock simulation, we have 48% diamond, and these three diamond peaks continue to sharpen and intensify. And then at about 200 picoseconds, we now have 64% diamond, and we see these prevalent diamond peaks. So using this protocol and shocking the glassy carbon sample at various shock intensities or various piston velocities, we're able to obtain this Hugonio in pressure temperature space, and that would be the orange curve, that would be the direct shock Hugonio. And then these hollow points are the pressure temperature points after shock trapping. And as you can see, below 100 GPa, there is a slow nucleation of diamond behind the shock wave front, as shown by these arrows here. And we see that the glassy carbon Hugonio exits into the liquid region over here at about 100 GPa. So here we have the pressure density Hugonio after shock trapping, and we find a compaction region from 0 to 30 GPa, or about 1.5 to 3.5 grams per cubic centimeter. And this is due to the collapse of the graphene sheets and the conversion of sp2 bonds to sp3 bonds. At 3.5 grams per cubic centimeter, we see the onset of diamond nucleation, where there is a dramatic increase in pressure for a modest increase in density due to the high bulk modulus of diamond. And then at about 3.7 grams per cubic centimeter, we see melting to liquid carbon, as we saw previously at 100 GPa. Okay, gotcha. So these phase transformations that we're after are most clearly elucidated when we look at fractions of sp2 bonded atoms, or three-fold coordinated atoms, sp3 bonded atoms, or four-fold coordinated atoms, and fractions of diamond, each of which we obtained using a veto using the coordination analysis and expression selection that we saw yesterday. So when we look at these fractions along the Hugonio, so at about 8 GPa, which is a small compression, the sample is still predominantly sp2 bonded at 95%, which is what we expect for glassy carbon. At about 29 GPa, the sp3 bonded amorphous carbon is prevalent at 75%. At 37 GPa, we now have predominant diamond at 85%. At 64 GPa, we see a coexistence between 45% diamond, 28% liquid carbon, and 14% sp2 bonded atoms at the grain boundaries. And at 100 GPa, we see the prevalence of liquid carbon with 40% sp3 bonded atoms. Also, we look at the kinetics of diamond nucleation. We've shown earlier that diamond fraction indeed increases with time, but this rate of increase varies with Hugonio. And we further see that higher shock intensities, which in this context leads to higher pressures, decreases the diamond nucleation time, or the time it takes for the diamond to reach its maximal size distribution. And what this tells us is that stronger shocks lead to higher atomic mobility, which in turn leads to faster diamond nucleation, which continues to grow behind the shock front in the amorphous carbon matrix. And then finally, we have a correlation between our simulation and experiment. This is a waterfall plot of the XRD patterns of the shock glassy carbon samples from that Dominic Krause paper I showed earlier, where these XRD patterns are at increasing shock intensities from bottom to top. So here, this is a waterfall plot of the shock glassy carbon samples from our simulation. So at 0 GPa, here we see the XRD pattern of the ambient condition sample and the good agreement between the XRD peaks. Up to 37 GPa, we see the XRD pattern characteristic of amorphous carbon. 45 to 70 GPa, we see the XRD patterns characteristic of diamond. And then at 100 GPa and beyond, we see the liquid-like broad XRD patterns of liquid carbon. So finally, to conclude, our MD shock simulations reveal transitions from sp2 glassy carbon to sp3 bonded amorphous carbon to diamond to mixed solid liquid coexistence and ultimately liquid, similar to what we see in experiment. So we were able to map these pressures and temperatures of each of these phase transformations. We were able to obtain fractions of diamond, sp2 bonded and sp3 bonded atoms for each of the phases. And we're also able to look at the kinetics of diamond nucleation. And these simulations help us to design and analyze experiments at EOXFEL, which ultimately aim to investigate the behavior of amorphous carbon under shock compression. So finally, I'd like to acknowledge our collaborators at the European X-ray Free Electron Laser Facility, or EOXFEL, our funding from DOE, and the supercomputing facilities that make these computations possible. Thank you very much.
Thank you, James. Can everybody hear me? Hello? Hello? Yeah, okay. Oh, it's quite quiet, isn't it? Thank you, James. I do not have a question, but let's bring up folks who do. So come on up.
Thank you so much for your talk. I was wondering how you do the analysis of your simulations to determine if something's amorphous or diamond. I know you mentioned coordination number, but for determining if something was amorphous or liquid, how do you do that?
We use the polyhedral template matching modifier in Oviedo. So there's diamond, cubic diamond, hexagonal diamond, graphene, and hello. So those atoms that don't belong in those, that would be the others, and that we would take that as the amorphous.
Thank you.
Nice talk.
Thank you, sir.
Can you talk a little bit more about the boundary condition for the shock trapping? Because it seems like when there's an evolution of phase transition that might not be volume conserving, are you fixing the pressure or the volume, or?
We're fixing the volume.
What's that?
We're fixing the volume. Yeah, and then we just integrate it in the NVE ensemble, so we're allowing the pressure and temperature to relax toward what it would be at 1 nanosecond.
Okay.
Yeah.
So and the phase transition, is it volume conserving, or does the density change through the phase transitions?
After shock trapping, the density stays the same. What changes is just the pressure and the temperature, and also the size distribution of diamond, if any.
Thank you.
You're welcome.
All right. I don't see any questions online, so thank you very much, James.
Thank you.
And we have one final speaker. Thank you very much, Alberto, for being patient with us.
Thank you.
Oh, fantastic. Great. We have sound. So let me introduce
Can
you.
you hear me now? Okay, great.
While you get your screen set up. So, yay.
I'm sorry.
Oh, please don't apologize. We all know how this goes. Happens sometimes. So now we have Alberto Fraile Garcia from the Catalan Institute of Nanoscience and Nanotechnology, ICN2 in Spain, who will be talking about high velocity dust impacts in plasma facing materials, insights from molecular dynamics simulations. Thank you.
Do you see the screen?
Yep. Looks good.
Okay. So, yeah, thank you. So, okay, I will go fast. I mean, just 2 words about the motivation. So the idea of simulating tungsten on tungsten impacts is because there is evidence of high velocity impacts in plasma facing materials. For example, in this paper here in the Frascati tokamak unit. So the thing is that in the tokamaks, of course, they observe the craters, but they don't know much about the velocity of the impactor, or the angle, the size of the impactor, etc. You can do the experiment yourself, but it's expensive and it's complicated. And this is an example here in the center. And you can do simulations like we did. So the problem is, of course, the size, the scale, let's say, because in the experiments, for example, they did, it's in the microns, the size scale, and in the simulations, we are in the nanometers. So one could say, okay, the question is, can MD simulate high velocity impacts? And of course you can say yes, but I would like to stress that indeed we can, and I want to present some evidence comparing to recent experiments. So the simulations are basically this. I mean, we have a target that is quite big to accommodate all the stress after the impact, depending on the kinetic energy, to optimize it. So we have a block that is pure tungsten. The projectile is tungsten, it's spherical. We give it some velocity, and then we see how the impact creates a crater, and we can compute a lot of things like all the atoms flying away, or the size of the crater, and so on. So just to give a couple of details more, we use targets as big as size 600, 600, 400 cubic angstroms, about 200 million atoms and more in the biggest simulations that we did. We use 3 different projectiles, 4, 8, and 10 nanometers in radii, having like 2,000, 17,000, and 30,000 atoms. And then velocities ranging from 1 kilometer per second to 4.5 kilometers per second. So the time step is 0.1 femtoseconds. The simulations are NBE, so we have to conserve energy here. And we did simulations 200 picoseconds long. We use a simple embedded atom method potential developed by Giovanni Boni and collaborators. And this potential has to be joined to the universal repulsive interatomic potential, ZBL for short, as you know. So what it means, just briefly, is that you have to make your potential more repulsive in the short distances. Is to say that you have to make your perpotential, this is a schematic, more repulsive here. So you have to join it, the blue curve, to the green curve, that is the ZBL potential, and you have to do it in a smooth way. And then you can do some simulation, and this is how the simulation looks like. So this is an old video, but you can see here a lot of dislocations created by impact, and how after 100 picoseconds, more or less, the dislocations are not recombining anymore. So, but to be really sure, we did it 200 picoseconds. And okay, just in the interest of time, I will only focus in the crater, in the depth of the crater, in the diameter of the crater, and in the volume. That is what we compare to the experiment, because there are many other things that you can calculate, but there is no time. So the interesting part of this work, I think, it's we use something called pi scaling theory. That is a set of scaling laws called pi group scaling laws as well. Very useful to extend the findings of our small scale ND simulations to larger scales. So all the details are in these papers here, but basically the meaning of all this is that we have some physical impact parameters that we convert into some dimensionless quantities. For example, we define something called pi d, that is the diameter of the crater, times the density of the target divided by the mass of the projectile, the cubic root of that. The same way we do for pi h, that is the depth of the crater, times the same parentheses. And for the volume, we define pi b, that is the target density times the volume of the crater and divided by the mass of the projectile. So now we can plot, for example, pi d versus pi 3, that is this expression here. This is the yield strength, density again, and the square of the velocity of the impact. So if we plot pi d versus pi 3 in logarithmic scale, we can see that all our ND results here are in the same line that all the experimental data that we found in this paper. I think the agreement is really, really good. And they are all in the same line. We can do the same for pi versus pi 3, and we have again the same very good agreement with all our MD results compared to the experimental ones. And if the diameter and the depth are okay with the experiment, one could expect the same for the volume, and indeed we have again the same good agreement, right? So now having this, we can fit these 3 expressions, pi d, pi h, and pi b, to just this with 2 simple constants, k and gamma. And this is doable if we are in the strength regime. That means that the gravity is negligible. So we did that, and we calculated these values here for tungsten, on tungsten. And just for comparison, we calculated the same for impacts done in this paper, that is steel on steel. So just you can compare also your parameters to other materials. But of course, you can do more in your simulations. You can change the orientation of the crystal. So in the results before, the velocity was parallel to the 001 orientation of the crystal. You can change that as you like. And for example, if we do that for 100, 110, and 111, we have that the crater looks different looking from above. So here we have like this kind of square symmetry. Here it's more like two-petal symmetry, like symmetric along this vertical line. And in the 111, it's more like a circular or triangular. And I say triangular because, for example, if you look at the dislocations below, you have here like this is kind of a square. This is more or less symmetric along this line, right? And this is more like a triangle. So the point is not just that visual observation, of course, is that when you do the pi scaling trick, then all your MD results split in 3 different groups. And this is understandable because the yield strength depends on the crystal orientation. So having this in mind and taking these values for the yield strength of the tungsten, we have these plots, and again we can do the fits. So all looks good. And in this case, we didn't compare to the experiment because the experiments were done in polycrystal, of course. And also more important than that, in the second paper, we did a good study, I think, presenting a good study on the effect of the temperature and the angle of the impact. So for example, for the temperature, doing the same as before, in this case is for the volume, all the data are split in 2 groups, like this is like low temperature, and it fits well with the experiments that we have. We don't have much at higher temperatures, only this one that is 673, that is something in between. So we have like low temperature and high temperature groups. And then we also did impacts at different angles, and then we can compare with the craters observed experimentally, and we have these kind of ellipsoidal craters and all that. And we compare also all the geometrical features. So the comparison was again quite nice. But yeah, just to finish, a couple of things that are in progress. So one more thing that one could think is, well, instead of having a perfect crystal, you could have vacancies, interstitials, impurities, helium bubbles, for example, because the plasma phase material is irradiated with neutrons and all this transmutation. So if you have helium bubbles, you have, well, an extra level of complexity, and the shock wave will destroy the helium bubbles. Helium can escape if it's close to the surface. So this is now in progress, and a paper is coming soon. And finally, of course, one could also think about modeling polycrystals instead of a single crystal. And then, for example, the crater wouldn't be semi-spherical, but something that, but dependent on the grain boundaries and the details of the target in the impact region. So with this, I'm just finishing. The conclusion is just that I think that we can model high velocity impacts with molecular dynamics, and the agreement with the experiments was really excellent in my opinion. So if you're interested, just check these papers. I mean, everything started with this paper in 2022, and we published in Nuclear Fusion, and it was very nice that they selected one of our pictures for the cover. And then we published 2 more papers in Journal of Nuclear Materials last year. So yeah, everything is there. And with that, yeah, I'm finishing. So thank you for your attention.
Thank you very much. Great. That's very impressive. All right. Any questions for Alberto? Okay. I don't see any questions in the room. I'm sure he's got his email up there if you think of something later. No online questions. So let's call it for now. Thank you again, Alberto, and thank you for your patience.
Thank you very much. No, thank you. Thank you very much.
Take care. All right, everybody. So we have finished the morning session. Couple things though. We have a group photo right now. So please get ready to do that. After that, we'll have lunch hosted by Materials Design, a box lunch out in the foyer. And anything else I need to mention? And so we'll start the afternoon session a little bit later as well. We'll put a time up here. So, okay, please come up to the stage for a group photo.
Okay, I think we're ready to start the afternoon session. Thanks, everybody. First, I want to give a great shout out and a thanks to Materials Design for providing the very nice lunch that we just had. Maybe we can give them a round of applause. All right, and for all the speakers this afternoon, for your 15-minute talks, my plan is to give you a 5-minute signal when you're 5 minutes from the end of your time, and that way you can take 2 or 3 minutes to wrap up and still have time for a question or two. So I'm really pleased to introduce our invited speaker for the afternoon, Mitch Wood. He's been at Sandia almost 10 years, and I think of him as one of the most creative people I know at using MD as a tool to analyze and tackle interesting scientific problems. And I know he's done a long list of those just in the few years he's been at Sandia, and I think he's going to talk about some of his recent work today. He's also won 2 prestigious awards in the last couple years. The DOE Early Career Award, which is very competitive. And he also got an award from APS, the American Physical Society, the Neil Ashcroft Award for Early Career Studies of Matter at High Pressures, I think is the title. And I noted, very interesting, Mitch won that in 2024, and our speaker, Rebecca Lindsay, this morning won it this year in 2025. So I think it's cool we had both of the recent winners of that nice award here at our workshop. So I'll turn it over to you, Mitch.
Yeah, that's a community of shock physics people in APS. Really gets a lot of mileage out of that. Sorry for the in-person. Yeah, that community of scientists in the shock physics community at APS really makes great use of LAMMPS. And so we're appreciative that we can still do our good science because how well maintained LAMMPS is. So I'm going to talk to you about something that will get to what the title implies about how we're going to do sort of quantum-like physics in a classical MD simulation. But I think a more apt title is what's the next generation of interatomic potentials going to look like, and how are they going to show up in LAMMPS for us to use? So to get to that perspective and get to this specific use case, I want to provide a bit of historical perspective on like how we got here, right? I think it's easy to say that our computing power is ever increasing. I mean, if you plot out on the plot here, then the fastest supercomputer in the world, the blue line here, and the 500th fastest supercomputer in the world in orange, these lines just steadily march forward. And a few things to note from this is that it takes about 10 years time for the fastest computer to age out and become sort of the 500th fastest computer. And I can say that this gap between the fastest computer and the 500th fastest computer is more or less constant through time, although the new exascale computers that just came online in the last 2 years are really kind of pushing that gap a bit further, meaning that the frontier of computing is outpacing sort of what we call a commodity supercomputer at this point. And really the question I want to keep in the back of your head as I sort of promote these new ideas of what new physics we can be tackling in these MD simulations is our scientific usage of these big machines keeping up and keeping pace. My personal perspective on this kind of looks like this, where I started my research career in MD right around 2010, where I wrote in my undergrad, I wrote my first MD code as part of a course. And I think even though Steve and company had a 20-year head start on me, I thought mine was pretty competitive in terms of its use. A year later, I was using LAMMPS and never looked back since then. So in effect, I've seen computing go from the petascale, from the fastest computer in the world, to the exascale machine. So in just the 15-ish years I've been using MD as a research tool, the computing power has increased 1,000-fold. The other interesting thing is that if you took a PlayStation 5 today and took it back to when I wrote that first MD code in my undergrad, it would have been the 400th fastest computer in the world, right? So again, I'm not old, but that makes me feel old. So what does exascale computing look like for MD specifically? In this envelope of how many particles you can be running and how long you can be running them, we can maybe expect the same increase in power over the petascale as the floating point number looks like. So if we were at 10 to the 12th particles in the petascale limit, maybe we could be able to be running 10 to the 15th particles on those current machines. The answer isn't so optimistic on the time scale because of the way the integration scheme works. The communication overhead is really going to like bottleneck how much more time we could potentially simulate in one giant simulation. At the end of the petascale era, where those were the fastest computers in the world, I kind of picked out two examples of what I thought were sort of the cutting edge pieces of work at the time. At the very largest scale was this calculation of a trillion atom MD simulation back in 2008. This is actually some collaborators of ours, Tim Gurman and Kai Kadau at Los Alamos. They ran a simulation where they transcribed their friend Peter Lambdahl into a simulation cell and just let it run for a little bit of time. And unsurprisingly, Peter diffused away. So that was the biggest simulation at that time using Spasm, a different MD code than ours. But at the time limit scale, we had more a scientifically impressive calculation where the evolution of a plasma-facing material was shown out to microseconds and further by doing just direct MD simulations in that case. Now, what I want to put forth to you about the future of MD and where we're heading is actually not bigger and longer simulations, but more accurate simulations. You know, Danny touched on this morning. Becky talked about that this morning, that the frontier of MD is in the accuracy that we can run. So maybe we won't be pushing this envelope, but there is an extra dimension we haven't yet figured how to visualize on how accurate our predictions are. If you're wondering what the current exascale calculations look like for MD, here's one. Last year, I was lucky enough to get essentially unhindered access to Frontier, and they told me just to do something impressive, which is a bad idea if you know me. I'm going to burn through a lot of computing hours doing that. I did have a cool science problem that I wanted to run, which was similar to that plasma-facing material simulation, but now in a much more realistic material environment. What I'm showing you here in the bottom left is a tungsten zirconium carbide composite. So there's tungsten grains in this, and then there's small dispersoid particles of zirconium carbide that are in the purple mesh areas. At the top of the simulation, we're raining helium down. That's one of the ashes of the fusion reaction. And inside the bulk, we're hitting them with really high energy neutrons to simulate that damaged environment. So in a modest 4 Frontier days, which means I had 100% of the Frontier computer for 4 straight days to run this calculation, I quantified how much that material is going to erode over time. And that helps us qualify this material for potential use in a fusion reactor. But even though the simulation was a success and we got a lot of new information, including a really cool visualization out of it, 4 Frontier days is still quite a cost to pay for just one of these exascale calculations. So here's a final state of that simulation where we can zoom in and see where the helium bubbles are forming at the top and where sort of defects are clustering in the bulk. I really quite like this. If you were here yesterday for my Oviedo tutorial, this is all Oviedo. Okay, so more perspective. First, the thing to comment about that last slide is that was actually that simulation was running a machine learned interatomic potential. Danny and Becky both commented on this morning that this is the current state of the art, right? This is the most accurate and most efficient combination of potentials that we currently have in the world. And what this has done is it's really broken what we had thought was sort of the trade-off between accuracy and computational cost. Another example of that, and not just my own work, is in AlphaFold. You know, machine learning has beaten out every empirical model and every other predictions that we've had for protein folding, which I think, Steve, you said was the most impressive scientific result you've seen, was when machine learning overtook this problem for protein folding. The second observation that's important to say is that the model development, the interatomic potential model development, has been democratized. A lot of the tools like Pacemaker, FitSnap, Allegro, Flare, all of these things are available to the public now, meaning that there isn't a small group of people that are developing all of the models that we're using in MD. So more finely tuned, more application spaces are being opened up due to the availability of those tools. And in fact, you know, even though I'm saying this is all state of the art, even an AI tool can tell you what a machine learned interatomic potential is. And if you're clever and you can read the screen, you can ask it to explain this at an undergraduate level. And as an expert in this field, I think that's actually a pretty good explanation. So even the AI tools understand what we're doing with these machine learned potentials. So let me say that the exascale computing power, again, won't be used to push the frontiers of time and length in our MD simulations, but will be used to push the frontiers of accuracy. So here's a couple examples. So over time, how do these machine learning potentials fit in through time? Well, we've seen this plot a few times before, that these blue points when machine learning potentials first started showing up in the 2010s, they were more or less on par with this trend of increasing cost with time. So we as a community had a better appetite for more expensive potentials. But they all sort of fit on this trade-off plot, right? There's some error with respect to a DFT calculation that you could do, and that error kind of went up as you got better computational cost or reduced your computational cost, and then vice versa as you move toward these machine learning potentials. This being a hypothetical plot a couple of years ago actually had some real data applied to it back in 2020. This is sort of a plot of a bunch of different machine learning interatomic potentials that were all trained to the same data for a bunch of different materials. And you can make that accuracy cost trade-off plot, giving users the power to choose how accurate or how expensive their simulations are going to be, which again is not something that we got in any of the interatomic potentials that we had previously. If you're interested in developing a new method, a new model, a new way to do machine learning potentials, that GitHub link, Materials Virtual Lab /mlearn, has stock training data for you to try so that you can put your data on this plot and compare yourselves to the other potentials very quickly. Now, looking again toward the exascale, the real cost of these calculations is how quickly you can calculate their features, also known as descriptors. LAMMPS has a number of them already built into them for you. They either come as parastyles or computes, so you have access to them in whichever way you want. The good news is that a lot of the people in the room, the developers, are spending a lot of their time making those calculations faster and faster so that when you develop a model, it's ready to go on those exascale computers. There's no extra hurdle for you to run your particular model once you've gotten it into a fitted form. The two examples I'm showing you here are bispectrum components, which are features used in the SNAP potentials, as well as the atomic cluster expansion features. That's the plot on the right. And what you can see here is that the current state of the art of these potentials says that even for these million atom simulations, you can expect tens of nanoseconds per day on these machines, even for, well, a modest 1,000 GPUs that you can run this thing on. The other thing that's promising looking forward about LAMMPS on these exascale platforms is that these machine learning potentials are now sort of a qualification metric for the computer behaving as it should. And Stan can correct me if I'm wrong. It seems to be that that's going to stay true for any new machine that we get in the world, that LAMMPS will be running on it, and LAMMPS will have the potentials that we want to run in them will be ready to go once those machines turn online. Okay, now to what's the future of potentials in LAMMPS and MD. I want to give you 3 quick examples, and the last one being actually the one that's referring to the title of the talk. So let me first talk to you about magnetic materials. This was something that, in principle, 5-6 years ago, was not something that a classical molecular dynamics person was thinking about running, but there's a really important way that we've been able to reincorporate or have the ability to simulate magnetic materials in LAMMPS. So the first is that with the machine learning potentials, you can define your training set however you'd like. So if your quantum calculation includes spin effects, you can be clever and sort of collect training data that makes sense for the non-magnetic components and collect training data that represents the magnetic parts of the interatomic interactions. Fitting potentials to sort of 1/2 or whatever partition of the training data is non-magnetic will get you your interatomic potential that we're familiar with. But then adding in a spin Hamiltonian, adding in sort of a second potential energy surface to the system means that you can recover the magnetic material effects in a classically scaling simulation type. So this is just a simple graphic of how every atom has a magnetic spin vector attached to it. The atoms are evolved by a combination of the forces from your potential and the forces that come from the spin-spin interactions. Eduardo showed us some really impressive calculations that make this simple movie kind of put to shame. But this is really the meat of this, is that layering potentials gives you access to new physics. So think about your problem. Is there a degree of freedom that you're missing when you translate from a quantum calculation to a classical calculation? And maybe the answer is to sort of partition it into 2 separate models that LAMMPS can recombine for you in this. Now that these are not just toy models, you can actually do some really important and really cool physics for this. The architect behind the work that is being shown on screen is Svetoslav Nikolov, who took these spin molecular dynamics potentials, which are sort of both a machine learning potential and that spin component that I showed you, took these really large simulations of iron and shocked them into where iron would be at the center of the Earth. And because LAMMPS is super powerful, we had the ability to map out the entire phase diagram of iron using this combined spin and machine learned interatomic potential. And we actually can have the ability to compare directly to experimental data and be specific to the material that we're talking about. No more qualitative features about what we saw in MD. We actually have the accuracy and have all the right physics in play to show that we can compare directly to experiments on specific materials of interest. The next example for where MD is heading, in my opinion, about what kinds of potentials we can bring in, has to do with what Danny told us a lot about this morning in great detail, which is that there's a lot of extra use for the atomic descriptors that feed into these machine learned models than we're currently using. He showed us these examples where the information entropy of the descriptors that you have can be a really nice metric for how complex or how complete your training data is. But I want to put an idea in your head about where we can use this as part of a simulation going forward. In chemistry and reaction chemistry, we think about collective variables. What's the reaction coordinate that takes us from reactants to products, right? Well, there's a lot of information in those descriptors that can tell you a different view or a more complicated view of reaction coordinates in the system. So now you can have this collective variable in your system that you can drag your system from any reactant state to any product state. In a solid state system, maybe that's a phase transformation. In an organic system or a polymeric system, maybe that's sort of the lengthening of chains until you get to a lower information entropy state as defined by your descriptors. A way to think about this visually is that if you have a potential energy surface, again, the idea being we're layering a classical potential with some extra information to get new physics in the system. Let's say your classical potential looks like this curve in blue, right? The structure will try to approach a lattice parameter that's preferred by the energy minimization on your potential. If you add to it this entropic contribution, it could be a real physical entropic contribution or just some fictitious potential that you add to your system, call it the entropic or entropy potential surface, entropy energy surface. It may prefer a different structure. But by combining those two, you're going to get this curve in black, right? Essentially something that has no barriers to transition between all of these different states of your system. So what we're usually bound by in MD is very slow transition rates from one potential minimum to the other. But if you're clever and you can figure out a way to layer your potential with some extra information about the atomic descriptors, you can eliminate those barriers and make a really flat free energy surface that your MD simulation is being sampled from. But the problem is, and Danny said this as well, that we don't know what that entropy surface looks like. It depends on your descriptors. It depends on how you've calculated your entropy, your information entropy. But this is a possibility if we know a lot about our system and we construct our descriptors in a good way, we can figure out ways to more efficiently sample the trajectories that our simulations can be working on. Now, my colleague James Goff, who's sitting in the back over there, and I worked on a new method to actually demonstrate how you can use descriptors to change what's happening in your MD simulation. So it's not really just sort of a fictitious idea that I'm throwing in your head. We do have the ability to create these artificial potential energy surfaces and change the dynamics of your system to achieve some goal. The main goal of this, the way that we've implemented this our artificial potential energy surface, is to just minimize structures. And I don't mean get to lowest energy surface, but what if you saw something happen in a large simulation cell and you wanted to go back to DFT and see if that answer is right? In principle, there's no good way to do that, right? You just cannot take a full million atom simulation and take it back to a DFT calculation. You're computationally limited in doing that. But if you construct an artificial potential energy surface that uses the atomic descriptors to draw atoms toward a target structure, you can now miniaturize the problem. So in this example, what I'm showing you, we have a descriptor vector, distribution of descriptors that's defined by the large structure. And we're going to make a potential energy surface for the small box of atoms that I can run in DFT. And I'm going to put forces on the atoms that draw them to the same descriptor distribution as the large structure. And you can do this in LAMMPS by using the pair MLIP package. You can just write some code in Python that says the difference between your target and your proposed structure, based on the descriptors that they each have, constitutes an energy or a score. And you can write an effective potential of that system with derivatives of it that put forces on the atoms that move these atoms to get them as close to a representation as you saw in the large structure. Now, there's a bit of optimization that has to happen because that effective descriptor energy surface is quite rough. So you need some ways to get over barriers. But if you do this, and we showed this in a recent publication, you can construct small representative structures that represent a much larger system, some collective dynamics in your MD simulation. I think this is going to be really powerful as we go forward, not just to go and check our large-scale MD simulation with a higher level of theory, but I think it's going to be really important when we try to create new interatomic potentials, right? If you ran something big and you want to retrain your system to that, this might be a way to return to that training step and produce training structures that are representative of that large-scale physics you care about. So again, the takeaway message is that if you want to step aside from the hard physics and chemistry of your interatomic potential, you're going to have access to a lot more interesting problems to do in MD. Okay, lastly, I want to talk about what the title is actually about, which is what about excited state physics, things that are purely quantum behavior. This is an idea that I'm really pursuing right now and trying to demonstrate in a few different venues to try to make this more available to everyone. This is not necessarily a brand new idea. There was these ideas of temperature-dependent potentials or Sommerfeld potentials going back a few decades. But I think with the power of machine learned interatomic potentials, we're able to readdress this problem and get that extra physics of excited state dynamics like photochemistry or radiation damage back into LAMMPS and really make some important comments about those problems. If you want a quick explanation of what I'm kind of proposing here, the energy of your system is sort of defined quantum mechanically by how you occupy your states, right? So your Fermi-Dirac function of all of your occupied states times your density of states, which depends on your atomic coordinates of the system, integrated over all energies will give you the energy of that configuration, right? Now, if you do a slightly different temperature of your system, you occupy slightly higher bands in your electronic structure, but the positions of the atom hasn't changed, right? So in terms of a classical simulation, there's no difference in the energy of a structure, potential energy of a structure, if you've just increased the electronic temperature of the system. There's no way to represent that change. But if you had a way to effectively describe that, you could pull out the changes of the forces on the atoms that represent those changes in the occupation of the electronic structure. A quick example of how to do that is if you take a structure of tungsten, remove one atom, and calculate how much energy it took to create that vacancy, as well as move that vacancy one lattice site, you could get just the value that's shown on the very far left of this plot. If you increase the electron temperature and you change the way the electrons are occupying the band structure, that vacancy migration energy changes. And it doesn't just change with the electronic entropy of the system, it actually changes the free energy of the problem. Again, classical MD is stuck predicting this one point, but if you had the ability to represent the changes in the band structure in a classical potential, you'd actually get this temperature-dependent potential prediction out here. So here's a way that you can actually do this, okay? Top plot is the formation energy of two different crystal structures relative to BCC and tungsten. The purple lines are the A15 phase, the next most stable structure, and FCC, the next most stable structure in the system. And I'm showing you DFT calculations that show that the formation energy changes as a function of the electron temperature in the system. Again, LAMMPS and all the classical simulation types will only give you the leftmost point. It does not know about the electron temperature of the system. It has no way to change the forces on those atoms to reflect the change in the formation energy. But if you had a way to retrain a machine learning potential, you can get an approximate way to answer this question. The way you would do this is, unfortunately, rerun all of your training data in DFT that made up your interatomic potential, but now at a higher temperature. So now you have two potential energy surfaces, two machine learning interatomic potentials, one for the low temperature physics and one for the high temperature physics. And if you figure out a nice way to just draw a curve about at what temperature in your MD simulation you should be on the low temperature or the high temperature surface, you can recover this effect, right? It's approximate, I understand, but it is access to new physics that you didn't have before. In LAMMPS, you could actually do that with a combination of a couple commands. The first of which is an average temperature, the temperature on the atom averaged around its neighbors. And the real meat of this, the real important part, is a piece of code that Meg and Aiden had improved on in the last year, which is this hybrid scaled potential. It says that you can kind of sample from these two potential energy surfaces with some fraction of each, and that fraction of each is actually defined by each atom's environment, each atom's temperature. So here's an example for you. I'm just firing a high energy particle at a slab of material. So you see the real simulation on the left, and then the color coding on the one in the middle is actually how much of the low potential surface, low temperature surface is being used, and how much of the high energy surface is being used. So you can dynamically change which potential energy surface you're on, and hopefully recover the physics of whatever problem you're after. Now, this is all sort of toy problems. What am I actually using it for? Well, I'm using it for radiation damage effects, because when a neutron comes in and collides with the lattice, there's a huge energy deposition in the system, which I would argue is not well represented by just a simple classical potential without any temperature dependence in it. If you're familiar with the radiation damage process, one atom gets hits other atoms, et cetera, et cetera. There's a cascade of damage. In LAMMPS, you set that up kind of like this. We can talk about details a bit later since I'm running out of time. The visual effect is something like this, where that pink atom is the original atom that was hit by the neutron, and the cascade of damage sort of displaces a bunch of atoms along a tree in the system. Now, I've shown you that there's a possibility to switch between potentials, and this is happening in real time as this atom collides with other atoms in the system. And what's really important to me is that when you look at these really high energy collisions, the number of defects that you generate is actually very dependent on the potential that you use. And unfortunately, I didn't get the data collected in time to show you how much switching between those potentials matter, but maybe in the next day or so, I would have had all of the calculations done. So I apologize, but hopefully the visual effect is still there. And the idea is in your head that you can use these dynamic potential energy surfaces to capture the correct physics of this problem. So again, reconnecting all the pieces of this talk, layering potential energy surfaces gets you access to new physics of your system, much like the spin dynamics. And being able to sort of step aside from the hard physics and chemistry of your system will give you access to new problems that you otherwise wouldn't have had if you just use a simple classical potential. I'll skip this one. If you want to know how I'm training these radiation damage effect materials, I'd love to talk about this. But I'll just leave this up here about what I think is the future of MD and what these data-driven potentials, these machine-learned potentials have opened up for us. And if you're interested in a couple of the publications that were flashed in front of you, the links are here, and I'll leave it to you for any questions. Thank you.
Have time for a quick question or two, and Marcel, if you can come up to get ready for the next talk. Any questions for Mitch?
Or questions online, yeah.
Or come up to the mic if you would. Let's make sure it's on.
So you mentioned about the generalized representative structures, right? So I have a question about that is like, you showed that there was, I think, 2000 atoms and you went to, I think, 50 atoms. So for that second structure, for number of atoms to show that, like to represent that structure, is there any relation with respect to the actual system, like with respect to number of atoms, or like, is there any?
Yeah, so generally speaking, the larger the structure you are trying to use as like your representative structure, the more information it could have, and the more representative is of a full system. So here's an example on the far right where you have a tensile test of a simple metal. You can use a very small structure to represent the perfect crystal, right? Intuitively makes sense. How would you represent the plastic damage of the system? Well, the larger of the representative cell that you allow for, the more information you can capture. Yeah, but there's a trade-off of how much cost you want to run in DFT on that small structure.
So it depends on how much information we want from the structure.
Exactly, but we can be quantitative about it, which is the nice part. We know just exactly how representative it is when we make that conversion.
So are we trying to like match the potential energy for the two structures?
No, but I think I can talk a bit more about it offline if you'd like to know more details.
Okay, yeah, thank you.
One really quick question? Yes, very quick. Okay. It's also about the generalized representation stuff. The examples you showed are kind of like, matching distributions in quite complex systems. could you do this with like a single defect, say like a dislocation? Because obviously like the configurations around dislocation, like the distribution doesn't necessarily match the fact it's a dislocation, you know, like if, like you might just have some messy cell, which isn't
Yeah.
really a dislocation. So
Yeah.
I guess that's my question.
The thing about defects is that we know a lot of what they should be, right? We know a lot of the low energy structures. So our intuition is guiding us more than just the information contained by the atomic descriptors.
Yeah.
You could play games and sort of like inside a crystalline matrix, move atoms based on their descriptor content toward a defect that you like. That's definitely possible.
Okay, thank you.
Thank you again, Mitch. Okay, our next speaker is Marcel Quackel from DCS Computing, and he's going to talk about using GPUs for discrete element models, which are for granular materials.
It's not maximizing there, but do you know how to trigger it? I went there, but it went here, but not there.
Oh, okay, so you got the. You're sharing the wrong thing. Go. Can you go back to Zoom?
Yeah, sure. Stop sharing, maybe. Just share the whole screen then.
Yeah.
I was only sharing one network.
It's because it's the PowerPoint thing. It's a different screen.
I see. Sorry for that. Now it works. Good. The laser pointer. Okay. I can hold it in my hand. Yeah. Okay. So I'm Marcel. I'm the lead developer of Spherix, which is a DM code. So it would be nice to see how many of you know Spherix. I guess not that many. A handful. So you might wonder, what am I doing here at a LAMMPS conference? So to start there, like the software that we are developing, so it's called Spherix now, but before it was called Lights, and it is also based on LAMMPS. So the back end is still based on the same fixes and computes that are also used in LAMMPS. And it is essentially, or Lights, back in the past, it was also still open source in GPL, and it was a specialization of the paired run. So it's only focused on systems like your powders, sands, grains, so way larger scales than the atoms and the molecules. And we also have already, back then, we had like a coupling between the DEM side and the CFD side, so the fluid side of things. And yeah, and then since 2019, we moved from the open source to like a commercial code, and well, that's also when the name moved from Lights to Spherix, and we still use LAMMPS as a backend, but then as LGPL, thanks to the developer of LAMMPS of providing us that option. And the difference there is that we also added more particle shapes. So in the beginning, there was only spheres, but we also added more complex shapes and also additional physics between the particles and the walls. And so we also have like moving meshes, moving walls. And we also made a big improvement in the user experience, since in general, the scripting language is sometimes a bit hard to understand. And well, we made some improvements there, so I will show a bit about that. And besides the CFD coupling, we also have now a coupling that a mesh can deform, and then the finite element is used to deform that mesh essentially. And finally, yes. So we also, a few years ago, we started to develop the GPU version of Aspherics, and that is also based on the same layer that is used inside LAMMPS, so the Cognos layer. And I will also show a bit about that. So here a bit about the features that we have in Aspherics. So we have a whole range of contact models to do the interactions between the particles and just with each other, but also the particles in the walls, and also a load balancing for the particles and the meshes. And already via the installer, you will get also the Ovito that was shown yesterday, which is indeed a very nice post-processing tool to use, very efficient. And one other thing I will show in a bit is also like the lowest one on this list, which is the dynamic coarse graining. That is that you scale up the particles, but in a way that the physics is still the same, but you don't need to fill the whole domain with very small particles. And the industries that we work in are pharmaceuticals, like the machinery for harvesters, some applications in geoengineering, and also your typical things are extruders and kilns. So here you can see an example of the filling of a feed frame, as it is called, and you can see there in here in the top left that the particles first are very big, and then if they go down, like the coarse graining rate is reduced. So only for the region where it really matters, we have like a low value of the coarse graining, and that's all dynamic based on the region where the particles are. And then in the end, you will get like the tablets, as you can see in the bottom right corner. Another one is like sieving, as you can see here. So to separate the big and the small particles, but like in this case, here the stones, which also have like various shapes. And another nice one is like the interaction between the fluid and the particle. So here, like the bed of the river is made out of the particles. So that is the side of Aspherics. And the CFD side is then it's like the water level, and the interaction between the water and the soil there will, as you can see here in the middle, you saw the like the scour that is happening there. So like I said, we have like a user interface, but instead, like in contrast with the GUI of LAMMPS, we have more that the user is not really seeing the script at all. So it's more clicking on some buttons, and then in the backend still a script is made. And also one thing that we have improved, in my opinion, is like the scripting language. Like here you can see like the more LAMMP style of scripting. But as you can see, by using some wrappers, we have simplified like the naming of some of the commands. Like for the example here in the bottom, there is like one line to enable the gravity, and in our case it's just called enable underscore gravity. So we have some simplifications there that make it easier to understand what is actually going on. And in general, we have like the rule that we have the name of the command and then a keyword and a value pair. And one other thing, we also have like minor improvements. Like here we have some commands that is doing the calculation of the mass flow, and then we can, if you want to output it, instead of using the square brackets, we have like a dot access, so then you can just use a word instead of like the number. So here, instead of the 1 and the 2, you can just use the name like of the value that you want to output to your log file. So like I said, we also have been developing the GPU part. This is a bit like the history as from the last 3 years or so. So at the beginning, we only had like spheres and only 2 of the 20-something contact models that we have implemented on the GPU, but later we added some more stuff, and more recently then, so we hope before the end of the year we can release also the version that we have the meshes on the GPU side. And also there we have now included some heat transfer already on the GPU side. But yeah, there are still some more things that we need to port from the CPU to the GPU side, but I think we are making some good progress there. So this is some examples or some studies that we did to compare how well our current implementation, which is more to make it work first and to improve the real performance is a bit later. Like this is like a silo that is being emptied. So it is like a typical case for our for the customers that we have. So that's why we have to take a look at those kind of things. And well, first of all, of course, you want to validate that you get the same results as before, or at least that there are no real weird physics happenings. And sometimes if the system is not set up in a correct way, it just like it might explode. So, but here it is shown that at least the kinetic energies are all okay. And also for the other case, since there are like here 2 setups, one with a very narrow hole in the bottom and the other one with a slightly bigger one. And well, the GPU version is a bit off, but it might also just be the setup of the case. Here, some first results. In black is like the lights, like the old style of the code. In purple is the CPU version of Aspherics, and in red then the version of the GPU. But it must be said right here, it is we try to keep the number of flops like identical. So the GPU flop count is then identical to the CPU flop count. But it's always hard to compare between the CPU and the GPU kind of things, I would say. Right. And also we had to do some hack around the bottom of that silo to make like that, as you can see here in the bottom right corner, to make that shape. It's just a lot of walls that we had, since when we ran this case, we did not have the meshes yet ported. So for that, we did not use that one there yet. And then another case is like a drum with a bunch of particles in there. Here, there are 2 types of particles in here. And also, if you look at, again, the kinetic energies, they are very well matching, I would say. But here, the GPU is actually faster than the CPU. And again, the flop count for CPU and GPU is the same, but for some reason, since we still have to investigate a bit more, like where and how and why certain things are better here than for the other case, but well, still some work to come. So to get to some finals, like I think we improved the user experience by having at least a user interface, also like we have now for LAMMPS, which is always a good and easier step into using a rather complex piece of software, I would say. And also the changes that we did to the scripting language makes it easier to understand and read, or at least from our experience, to like what is really happening inside the simulation. And for the GPU, well, we made some good steps. We already have ported a bit of the CPU to the GPU side of things, but there's still some extra work to do to port some more functionalities, since features like the melting of particles, for example, it's still not on there. But on the other hand, we also need to improve, at least take a look at the performance here and there. So, well, I guess that's it, and I'm happy to answer any question.
Okay, thank you very much, Marcel. Let's thank you. Okay, time for a quick question or two, and Anders, you can come up and start getting ready for the next talk. Any questions for Marcel? Here comes one. Make sure the mic's on.
Thank you for your talk. I had a question about your dynamic coarse graining. When you say dynamic, does that mean you're changing the size of the beads in your coarse graining? No. Okay.
No, what we do is that we split like a larger one in smaller ones. So you get, instead of one big particle, essentially, it becomes then like 8. And we can also do it the other way around, that you then start to merge them again once you, like it depends a bit on the system, if you want to do it from large to small or small to large.
Okay, and then when you're merging and splitting things, do you kind of have to do a back mapping then between your larger beads and your smaller ones, or?
Well, you have to select which ones you to include, like, well, at least if you go from small to large, then you have to select a number of them and make them, yeah, like in a way integrate into one again. Yeah.
Okay, thank you.
Yeah.
Any other questions? Oh, can you read it? Somebody read it?
Is there an academic license with low cost?
Yes, there is.
Okay, let's thank Marcel again. Thank you. And I like the model rubber duckies there as the on the production line. That's a pretty interesting aspherical shape. Thanks. Okay, our next speaker is Anders Johansson from Sandia, and he's going to be talking about the GPU acceleration package COCOS that we use in LAMMPS, and particularly what that means for LAMMPS doing MD on big exascale style machines.
Hello, can you hear me? And you cannot hear me double? Just avoid our mics close to each other. Okay. Okay, can you hear me once now? Better, okay. Yeah, so I'm Anders. I'm a postdoc at Sandia in what is sort of the LAMMPS department at Sandia. So I'll be talking about the COCOS package for running LAMMPS on GPUs. It's one of the 2 packages, and in particular what it can do and on big exascale machines, and also how it works. So since this is a LAMMPS users meeting, I'm just curious if you can raise your hand, how many of you have actually run LAMMPS on a GPU? So a few of you, not Aiden or Steve. Yes, okay, Steve, but not Aiden, okay. Well, to bring us all at the same level, so here I have my laptop. It has a GPU in it. I have an input script, I have a LAMMPS build, and if I do LAMMPS build LMP in my input script, it will run LAMMPS. It will do about 1 million atoms of Lennard-Jones, so you can see 1,188 atoms, and it will do about 3 to 4 time steps per second. That's given by the second column of the log file. If I want to run this on a GPU and I've compiled this for COCOS, then we add the suffix flag. We turn on COCOS, tell it to use 1 GPU per node, and then we turn on the COCOS package, and we give it some arguments like Newton off, nay full, and I'll get into these later. And then it will run on my GPU. And instead of doing 3 to 4 time steps per second, it's now doing almost 100. So takeaway, GPUs are good. This applies not only on my laptop, but also in the HPC world. So if we look at the top supercomputer over time, we're now in the exascale era. We can do 10 to the 18 operations per second. And we can do this on different kinds of hardware. So the CPU heyday is over. It's now GPUs everywhere. And in particular, we have GPUs from different vendors. So NVIDIA GPUs are still big everywhere. But if you look at the biggest machines over the past 2 years, they've all been AMD GPU based. And then there's also now an exascale machine with Intel GPUs. So LAMMPS was a very early adopter of GPUs in the HPC landscape. In 2010, there was the GPU package. This runs the peristyle on GPU and then most other things on CPU, which implies frequent data transfers. But if you run multiple MPI ranks per GPU, it runs pretty quickly. And I think the next speaker will talk a bit more about trade-offs between the GPU and the COCOS package. Then in 2011, Christian Trout's PhD thesis was the user CUDA package, which in 2014 became the COCOS package. And this tries to be GPU resident, meaning everything runs on the GPU, so you don't have to go back to the CPU and transfer data all the time. So this uses the Cocos library for being performance portable, meaning it will run on all these different kinds of machines. So how does this work? Well, when you write pair-style EAM in your LAMMPS input script, that gets mapped to a C++ class. In particular, gets mapped to the pair EAM class. This has a compute method that gets called every time step. If you instead write pair-style EAM/KK, it gets mapped to the pair EAM Cocos class. And if you noticed earlier, I did the -sf_kk flag. And what this does is to append the KK suffix wherever possible. So then we get the Cocos class. So this one inherits from pair EAM, and it overrides the compute method, so that's the one that gets called every time step to compute energies and forces. Then to access atomic data, which is required for computing energies and forces, and the pair EAM class accesses atom-vec atomic, which stores the positions as a normal CPU array, while pair EAM Cocos accesses atom-vec atomic Cocos, which stores the positions in this Cocos data structure called a dual view, which maintains one copy on the CPU, another on the GPU, then keeps track so that you are able to mix and match Cocos and non-Cocos functionality and always have the data be up to date and correct, while also avoiding data transfers when not necessary. And then these inherit from other classes. So pair EM inherits from pair. That's where it gets its compute and communication methods from. While pair EM Cocos additionally inherits from this Cocos base class where it gets the Cocos communication. And then when EAM has to do communication to do the embedding, it will call COM_BRIC on the CPU and COM_COCOS on the GPU. And these inherit from each other. And so you get this sort of two layering of classes that ensures that everything works together the way it's supposed to, even though this eventually ends up looking a little bit complicated. So how well does this work in practice? Well, so there are a lot of different GPUs out there now. Here we have run on 6 different ones. We've run on the green ones, which are NVIDIA GPUs. Blue is an Intel GPU, or half an Intel GPU. Then we have the bright red, which is half an AMD GPU on Frontier, and the darker red, which is a full AMD GPU on El Capitan. And we have 3 different use cases. So Leonard-Jones, simple pairwise, ReXFF, which is more complicated, and then Snap, which is an ML potential. And we see that, first of all, the NVIDIA GPUs, in particular the H100 is doing very well. We'll come back to why later. We get better speed up. So the y-axis is the speed up over a 36-core CPU node. So if you're running Snap on an H100, you can be 50 times faster than a full CPU node. And Snap in particular is faster because machine learning potentials lend themselves well to GPUs. And then the ordering is sometimes a little bit different, where Intel GPUs do better than the MI250X for Leonard-Jones, but not for the others, etc. So this is the ideal case. How do you get there? An important aspect of running MD on GPUs is saturation. So how many atoms do you need to be using your GPU efficiently? And this is very different from a CPU, where effectively you're always running pretty efficiently. And for Snap, it's not too bad. It exposes a lot of parallelism. So if you get to the tens of thousands of atoms, you're running pretty efficiently, while actually for Leonard-Jones, to get full efficiency, you need almost 10 million atoms. So that's a little bit annoying. And if you run, say, 10,000 atoms, you're only at 10% efficiency, 100,000 atoms, you're at 50%. But at least you do saturate eventually, while the sort of saddest result here is ReXFF, where you run out of memory before you reach a proper plateau, and we'll see that that hurts scaling later. Another thing you need to be aware of is how LAMMPS deals with parallelism and neighbor lists and such. So on top here, we have neighbor threading, which can be turned on or off. That was not shown in my command line earlier because this is an implicit thing, or it can be an implicit thing and it has a heuristic. But effectively, for small systems, if you turn on neighbor threading, you get more parallelism, but you get a more complex iteration pattern. So it helps for small systems, while for bigger systems, it's better to turn it off. And so you see that there's a crossover point in the tens of thousands of atoms, which is where LAMMPS will automatically switch for you. While neighbor list styles and Newton's third law are something you often have to specify manually. So back in my terminal here, we saw that I ran with Cocos Newton off and naive full, which means that you don't exploit Newton's third law, so you do redundant calculations, but in return you don't have race conditions. And for a very fast potential like Leonard-Jones, this is beneficial. while for more expensive potentials, like the machine learning based ones, you want to be using Newton's third law to avoid redundancy. But if you do everything correctly, what is the result? So there are now exascale machines. There are 3 of them in the world, at least publicly. There's Frontier at Oak Ridge with the AMD MI250X GPUs, El Capitan at Livermore in the NSA with MI300 GPUs from AMD, and then there's Aurora at Argonne with Intel GPUs. And so we've run on all 3 of them. LAMMPS runs on all 3 of them with the Cocos package. And we also run on EOS, which is sort of a surrogate for the upcoming NVIDIA exascale machines with the H100 GPUs. And what we see are sort of 2 things. First of all, the ordering of the performance is sort of the same as the single GPU performance, meaning effectively that the potential is what matters, and that LAMMPS is scaling very well. And also that if you just have enough GPUs for Lena-Jones, you can get to about 1,000 time steps per second, no matter how big your system is. So even for the 1 billion atoms system, we can get to 1,000 time steps if you just use about 1,000 GPUs. While for 100 billion, we can't get there, but that's mostly just because nobody's built a big enough computer yet. We can do this also for the other potentials that we're studying, so React and Snap. We see that Snap is the one that scales the best. It has the straightest lines. And again, this is partly because it's the most expensive, so communication is a smaller part, and also because you're saturating the GPU better, so you need fewer atoms per GPU to have full efficiency, while React scales the worst because there was no plateau in the saturation plot. So that means as soon as you have more GPUs than you need to fit it into memory, you already start dropping in efficiency. And so that's also why it peaks at less than 100 time steps per second, while for both the other potentials, you can get to about 1,000 time steps per second if you just have enough GPUs. And then one thing you may have noticed so far is that the H100 GPUs are doing very well. They're outperforming on basically everything. And then the question is why? Because if you look at the numbers that people typically look at for GPUs, like memory bandwidth and floating point throughput, the H100s shouldn't really be doing all that well. The MI300A should be blowing it out of the water. But it isn't. So why? And it turns out that if we look at a third column of GPU performance metrics, if we look at the L1 cache size and the shared memory size, this is where the NVIDIA GPU really shines. And what we can do then is to make a little experiment where we artificially reduce the cache size of an H100 and see what happens to the performance. So here we're looking at Lena-Jones, and we're gradually just reducing the cache size by artificially allocating more shared memory. And what we see is that the performance indeed goes down. And if you look at the numbers of what happens when you get over here, where you've made the cache size very small and you've effectively matched the cache size of an MI300, you see that you recover the performance loss between an H100 and an MI300, meaning effectively it's all about the cache size for Lena-Jones. Similarly, the YI kernel in Snap is very cache dependent, while other 2 kernels in Snap are using a lot of shared memory, which is also where NVIDIA GPUs are doing better. Finally, I just wanted to highlight that last year, as part of my PhD sprint, I ran 1 trillion atoms on Frontier with the Flare machine learning potential on LAMMPS. And I'm pretty sure this was the first GPU accelerated trillion atom molecular dynamics. So just want to say, go LAMMPS. And all this just worked beautifully on Frontier. And I get to show this. So with that, I just want to thank you all for listening. Thank the collaborators on this paper. So Meg McCarthy, Stan Moore, Evan Weinberg at NVIDIA, Christian Trott at Sandia, and happy to take any questions. And I'll just leave
this
up here since it has the most data on it.
Let's thank Anders. Okay, time for a question or 2. And Trung, if you want to come up or get ready for the next talk. Any questions on the Zoom call or chat, Slack? Sorry. Any suggestions on flags for PVC? Not sure what PVC is.
Yeah, PVC are the Intel GPUs. So yes, we have some. I can't list them off the top of my head, but we have them if you're curious.
Okay, so the person who asked that question on Slack, if you want to reach out to Anders directly, email or something, you can talk about that.
Yes.
Thank you. Is the Intel machine now considered like fully complete and are they still continually upgrading it, or it's kind of ready for production?
It's in production now. It's not in pre-access or anything, and you can get access to it. And yeah, we run up to 2,000 nodes, and it works.
Okay, good to know. All right,
yeah, we
let's
get good feeling.
let's thank Anders again. Okay, the next talk is by one of our LAMMPS developers, Hung Nguyen at University of Chicago. And he's going to talk about, I believe, the GPU package. Well, maybe this includes Cocos. There's, as Anders mentioned, there's two modes in LAMMPS of using GPUs, and Trung is familiar with both of them. So I'm not sure which he's going to talk about, but take it over.
Can you hear me clearly? Good. Hi, everyone. Can you hear me clearly? The people online too? Hello, can you hear me clearly? Okay, cool. So my name's Chung. I'm from U Chicago. My daily job is not for writing LAMMPS code, but it's one of my hobby, and I'm very happy to continue to work with the LAMMPS team. So I'm going to tell you about my contribution to LAMMPS code base. So the problem that I want to solve boils down to a very simple questions. Can you make LAMMPS run faster? I approach this problem as a user for a given resource. I want to make sure that for any constraint that I have in hand, I can make the best out of it. So I'm showing you here the plot that I compare the performance of LAMMPS to, let's say, 2005, about 3 months ago, with Humdi Blue. In Jack's talk yesterday, Humdi Blue, it's mentioned, it's one of the best highly optimized code for these particular submetal systems for polymer melt with Lena Jones and Finney bonds with very high densities, with a cutoff around 3 sigma. And you can see that in this range of the number of particles in the system ranging around 28K up to 500K. The performance that LAMMPS can offer a little bit slower than Humdi in the lower particle count. And I try to address, to make the gap between the two code as closer as possible. So my talk is very different from Anders' talk, where he tried to see the performance at the exascale, where we have a lot of GPUs in hands and tackle multi-millions or trillion atoms in a single run. I'm trying to look at a lower count regimes because that's the regime where most students and postdocs at the universities like mine trying to do their PhD thesis. So we try to see why we see the gap like this, where we have in hands all the options that LAMMPS can offer, as Anders had talked about. So we now have access to at least 3 options for the for accelerations. LAMMPS supports the hybrid MPIs plus X, where X can be multi-threading with OpenMP and with the Cocos package as well for the CPU side. Or you can use Intel package for Intel CPUs for vectorizations. And in this talk, I mostly talk about X with the GPU acceleration that can be done with the GPU and the Cocos package. And one note I want to emphasize here is that the speed up due to X versus the MPI only version strongly depends on the models that you are using, as in the talk that Anders showed you for different kind of pair styles, and also how big the system that you are looking at. So I try to thanks Anders to set up the stage to talk about the Cocos package. I don't mention too much about how Cocos package make use of the GPUs, but I want to mention the difference between the Cocos package and the GPU package, which I, let's say, developed and I helped develop in the past 10 years. And these two packages, let's say, support all kind of GPUs out there, from the NVIDIA, Intel, and AMD GPUs. And I list here the difference in the sense that the Cocos package up to this point support double precisions. And there's ongoing work that Stanmore has been working on to support mixed and single precision modes, while the GPU package support all three modes: double, mixed precisions, and single precisions. I want to emphasize here, what do you mean by mixed precisions? Mixed precisions here defined by LAMMPS and the GPU package in the sense that atom coordinates store and load in the single precisions. And all the arithmetics are done in the single precisions. But the accumulations for the forces and the energies are in double precisions. In the other two extremes, single or double, everything's in either single or either in double precisions. These mixed precisions are very different from other codes. OpenMM has a different way to define their mixed precision mode. So something that we want to very clear about that. And you already mentioned that for GPU package, we can make use of many cores on a single node sharing the GPU. It is very suitable for the configuration for the compute nodes in the HPC clusters available at the universities around this country and other places as well. The useful thing is that the use or the build of these two packages are not exclusive, meaning that you can build these two packages in a single version of LAMMPS using the CMake build. As I show in here, you can turn on both packages, and then the problem or the thing that you need to keep in mind is that you can only use one package at a time. So we can specify the way that Cocos has been invoked, the way Anders showed you in his talk, or with the GPU package, you can use SF GPU and the package GPU. In this case, we use 4 MPI sharing two GPUs. So what I have done to the GPU package in the past couple of years is to add more couple new pair styles and allow users to add more styles to the GPU package. For example, I work with Josh Reckers and Steve Plimpton to add the GPU versions of the Amoeba and the Hippo pair style, which used to be only done in the Tinker software package. And then I added new pair style for the DPD, MISO, and SPH pair styles. And these features of allowing we add more pattern parameters to the base classes inspired the contribution from others. For example, the DPD Coulomb state long by Eddie Barrow that Steve highlighted in his talk this morning. And also other features and bug fixing that I contributed over time. And also, let's say, working with Axel to cleaning up all the log pages about this package. And then recently we decided to move on with the CMake builds because, as I showed you in the last slide, it's very useful and very easy to use to combine all kinds of configurations for the build. So here's one of the examples that we got with the Amoeba force field, where I work with Josh Reckers and Steve to make sure that the results on the GPU side match perfectly in the double precisions with this pair style. And for a single node, with the system consisting of 600,000 atoms for the proteins solvated in water, we have consistently speed up around 3 times. Going from left to right, I increase number of MPI procs, meaning that we have fewer and fewer atoms per MPI proc, and they speed up constantly at around 3 times. So the question that I want to address there are 2 aspects of the overall question. How can you make LAMMPS run faster? Is that, let's say, if we have a single node, that node can have, let's say, 48 or 32 core and 4 GPUs. How can we get the optimal GPU speed up for that compute node compared to the version that we have, the full node with the CPU only runs? So in this exercise, I play with both package, Cocos and GPU package, varying all the kind of number of MPI procs and all the number of GPUs that are available on that node. And I try to find what are the optimal configurations for either package and what are the best speed up that I can have. So I chose 3 representative submatter systems: the simple lipids, the Lennard-Jones cut in the benchmark folder, and the protein, the rhodopsin examples, and the dipoles with actual volume interactions with the number of particles in there. And I perform these runs on ALCF Polaris with 100 GPUs. So here's what I found. Let's take the baseline. Here's an example where for the Lennard-Jones simple fluids, the light workload are, let's say, upload to the GPUs. I show you here, for example, with the Cocos package, with a single processors and single GPU, you get 3 times speed up compared to the 32 MPI only case. And for the GPU package, the best performance of this package can offer it's around 2.7. And I show in the gray lines here, meaning that if the Cocos package to be run on all 4 GPUs, then the optimal speed up is around only 1.5. It doesn't mean that you should use all the GPUs on the node to get the optimal speed up. But in this case, Cocos with 32,000 particles, it's kind of really tiny, right? Compared to the other talks where you talk about millions of atoms. But for the GPU package, the speed up with the single GPU is around 1.7. And you want to, let's say if you want to use this one. So you should be supposed to something like 3 times if you want to use the GPU package. The same theme apply, and you see when the medium workload on the GPU, then you get the GPU package will say outperform the Cocos package by, let's say, using all the GPU on the node, around 2.8. For the dipole systems, the GPU package can offer speed up around 16 times compared to 32 MPI only proc. So that's the gray line also show you the other numbers too. So I shift here to what I have done to the Cocos pair style. So in the previous talk, Anders talked about the multi-threading over the neighbor list with the nate off. And then if you want to turn that on, we use all the SIMD lane on the GPU. And we fix the thread block size realistically based on the maximum number of the neighbors on each atoms. What I have done in a recent merge PR is that I expose those kernel parameters so that users can set them up from the command line. For example, the line showing here. And what I found is that without tuning the pair style, we saw the red block showing up that at the lower count, it starts to be improving. And if we take into the tuning by changing the threads per atoms and the group size, meaning the pair team size, we can see the blue box going up. And you can see at a little bit higher count, LAMMPS Cocos already, let's say, hand in hand with Humli Blue. So it's the improvement, it's around 50%. And this way of tuning allows a wide range of systems that I'm showing here. And the optimal kernel parameters depend on the simulated systems. And you can see here the speed up compared to the case where we don't have this nitrate on, around 60% to 40%. The only exception is only when you have the Lennard-Jones with bonds. But with the very short cutoff, we have a very few neighbors per atom to tune. So the last slide I want to share with you is the experience to tune and what kind of package that you want to choose for your simulations. With this kind of range is that the COCOS and the GPU package are recommended based on what are the features are available or let's say supported by this package. And with that, I want to thank my collaborators, the opportunity to talk with you here, and Steve and Stan for their feedback.
Thank you, Trung. Let's give him a hand. Time for a quick question if somebody wants to ask before, as we transition between talks. Peter, you want to come up? Oh, he's already here. Question for Trung, or can somebody look on Slack or chat and see if there's a question there? So I'll just make one comment. Trung can verify this, but those tuning parameters for the threads per atom and other GPU settings for different kernels in the time step, that's something we're hoping to add, like an auto tuning option, which I know HUMD and other codes do, to kind of tune for performance based on the problem size and other things, so that you wouldn't have to manually figure out what that sweet spot is to get those parameters as fast as possible. So that's a upcoming plan.
Yes, that's a plan.
Okay, let's thank Trung again. Okay, now we're going to change topics a little bit from lots of GPU and performance discussions. Peter Intveld from BASF is going to talk about polymer properties for industrial applications. Do I need to say something for the chat people? Yeah, so this one for people who are on virtually, this talk cannot be streamed or recorded. And so we're going to shut off for the 15 minutes of this talk, shut off the streaming. Okay, our next speaker is Laura Zicki from Sandia, and she's going to talk about a hybrid method that combines Monte Carlo and MD pointed at alloys.
Okay, thank you for the introduction. So today, I will be talking about an added generalized method for doing hybrid Monte Carlo and molecular dynamics simulations within the LAMMPS framework, and we're specifically interested in applying these types of simulations for alloys. So just a bit of motivation, we're interested in simulating alloys, of course, because they are prolific across different industry applications. Even in our day-to-day lives, we always experience different types of alloys. The simplest example is just a spoon that might be made out of steel. And so using experiments, we can only get so far. We're able to characterize different structural features and different compositions. But if we really want to understand the underlying mechanisms that govern the properties that we see on a microscopic scale, then we need to start looking at our all-atom simulations. And so that is where LAMMPS comes in. And so the traditional way of modeling alloys is that we want to do a combination of molecular dynamic steps, which is the familiar type of molecular dynamics within LAMMPS, where we have some way of predicting our energy, and then we can use Newton's equations of motion in order to integrate our trajectories across time. We then want to combine this with Monte Carlo moves. Now, Monte Carlo is a very broad class of algorithms, more of an umbrella term when you're using a random number in order to propagate your system. So in our case, we want to use Monte Carlo in order to choose an atom randomly and change its species. And so this allows us to rapidly alter the chemistry of our alloys while combining it with molecular dynamic steps to relax our trajectories and explore various configurations. And the great thing is that we can do both of these things all within LAMMPS. And so by combining MD and MC steps, we're able to see really interesting phenomena like chemical segregation and phase precipitation. And if we were only doing pure MD steps without having this MC swapping of our different species, these types of simulations where we're seeing the segregation might be implausible or just impossible to do on current computing architectures, even if you're using supercomputers. So being able to rapidly alter our alloy chemistry is very important. So as I've mentioned, Monte Carlo is a very broad class of algorithms, even within the type of Monte Carlo where we're just flipping our atom species. There's many different underlying ensembles that will designate when you're accepting and rejecting various moves. And so when you choose your type of ensemble, you need to do certain considerations like computational cost, also the different phases that you hope to be able to model. And so in our case, we want to use the variance constrained semi-grand canonical ensemble because we want to be able to simulate multi-phase regions of phase space. And so this prevents large fluctuations in our concentration, which is extremely important when we're inside a miscibility gap where we don't want that concentration fluctuations to migrate to phase boundaries. And so traditionally, when we're doing these MC swaps, we're going to use a global calculation of our energy in order to determine if we want to flip that atom species with respect to our underlying ensemble. And so this is, of course, extremely expensive, especially if we're calculating the energy of our system with a local approximation. So this is a lot of wasted computation. And so Sadiq et al. Came up with this really amazing algorithm where you can instead use your local change in energy and then use that in order to determine when you're making these MC swaps. This was only limited to an EAM potential, which I will talk about more later. And so along with calculating a local energy, that's only one piece of the puzzle. You also need to make sure that when you're then scaling this computation and going to multiple processors, you don't have overlapping MC swaps. And so what LAMMPS does in order to make sure this happens independently is you take your simulation box, you can then divide it across different processors. This is considered your domain decomposition. I'm showing a very simple case where you have a cubic box, but LAMMPS does this automatically for the different simulation sizes that you may have. But when we're doing MC swaps, we can't just let any atom on the processor attempt a move, because what if it has a neighboring atom on another processor, and it might impact whether or not you make that swap. So we need to further decompose the domain of our processors into smaller subdomains to ensure that we can make MC swaps independently on all of our processors. And so we can do that by creating these sampling windows, and we make sure that they're separated by enough of an interaction radius so that our MC swaps are independent, and then we can communicate when necessary. So combining the locality of calculating our energy instead of this global calculation with this domain composition, we're able to have this nice algorithm. However, it is confined to only using an EAM potential. So as many people have alluded to within LAMMPS, one of the most important things that you need to do is designate what is governing the energy calculation of your atomistic interactions. And so this is known as your interatomic potential. So just to quickly review, given your configuration of atoms, how you're predicting that energy, force, and stress is very broad, and there's many different types. So the embedding atom method is a very standard and great method for purely metallic systems. And so that's what this localized and parallel method is confined to being for, is only the EAM method. And so this has obvious limitations if you need a higher level of accuracy. Maybe you have some magnetic spin considerations that you need to incorporate that the EAM method is not able to model correctly. And so we want to move beyond just being constrained to this one type of energy calculation to being able to make this a generalized algorithm. And so that has been implemented in LAMMPS by Aidan Thompson. And so now we can use any pair potential that assumes a sense of locality when it's calculating its energy, and we're able to scale our MC moves. And so this is very powerful, and now we can start using it with any type of potential that we're interested in. And so as many people have talked about today, machine learning interatomic potentials have showed great promise and are very interesting. And so we want to be able to apply those to our alloy simulations. And so just a quick review of a machine learning interatomic potential. You have some underlying model. Maybe you're doing ab initio, density functional theory. And so this is very expensive, and it doesn't scale beyond maybe 100 atoms. And so you can generate training data configurations of different atomic configurations with your energy and force labels, give it to some sort of model, and then have that predict out your energy and force for your MD, and then also in our case for our MC swaps. And so the specific machine learning interatomic potentials we were interested in incorporating in LAMMPS in order to do hybrid MCMD simulations is first the atomic cluster expansion. So this is a very popular choice. We've seen it used throughout talks today. And it's just a combination of higher body order terms together. And in the basis, we have a combination of radial functions and spherical harmonics. So we've incorporated support in LAMMPS for this type of potential. We've also added support for the SNAP potential, which uses bispectrum components in order to characterize local environments. Another type of machine learning interatomic potential that you can now do hybrid MCMD with is the flare potential. And so the exciting thing about the flare potential is that it is a framework for doing active learning, which Danny alluded to in the first talk today. And so it uses a Gaussian process to learn your predictions of energy and forces. And so this allows you to have a notion of uncertainty when you're running your simulations. And so when you're running MCMD simulations, your potential can be very unstable because you're randomly swapping in new species of atoms, and the potential might get confused. And so by having MCMD within an active learning framework, what we can do is we can start running some MCMD steps, and then if we have a high uncertainty predicted by our Gaussian process, then we can update our force field based on some underlying ground truth distribution, and then continue doing our MCMD steps. And so this allows us to naturally explore different MCMD configurations and collect those interesting frames maybe as training data, because trying to enumerate every possible alloy chemistry is going to be infeasible, especially once you have more than a few species that you want to incorporate in your simulation. So just to recap, we now have this general algorithm for doing parallel MC swaps within LAMMPS, and we now have added support for the ACE, SNAP, and FLARE potential, and the ability to really add in any local potential to doing hybrid MCMD. So first we need to validate this approach so we can see that the local method exactly reproduces the potential energy predictions that we would expect during an alloy simulation. Here, we're just doing 2 different species, and we can see that their energies match perfectly when we're calculating it with the local and global energy method. And we do expect it to be exact because the pair potentials assume a local radius, and we're using a random number generator with the same seed. So now we can start looking at the speedups that we hope to gain, the really important part of doing this parallelization and localization. And so even when we're just running only one processor, we can see a significant gain. Here I'm plotting time steps per second, so the higher is the better. And you can see that across these different pair styles, we're seeing really amazing speedups. This is only for 3,000 atoms. And so as you change the cutoff of your pair potential and also the size of your simulation, you would expect to see speedups. This is just a preliminary scaling to show that we are seeing these incredible gains. And again, I just want to highlight that these are 3 new potentials that you have available now in order to do these hybrid MCMD simulations. So you can really tailor it to the material that you want to model and the accuracy that it may require. So now that we can scale MC across different processors, we can start looking at the weak and strong scaling. So weak scaling being that we're keeping the ratio of our problem size to the number of cores that we're using the same, strong scaling being that we keep our problem size the same as we increase our cores. And so here I've done the inverse of the previous slide where I'm now plotting the seconds per time step, so lower is better. And so these are standard scaling trends that we would expect to see. Okay, so now that we have demonstrated the accuracy of the approach and examined that it scales really well, now we can start to use it to actually examine the interesting physics of the different alloy simulations that we care about. And so just as another form of validation, the original method was confined to only the EAM potential, and we're able to replicate the types of physics that we would observe, seeing this nice precipitation of copper atoms. And then we can also examine now systems where maybe you want to use a SNAP potential. And so this simulation was infeasible before because it's just too much compute to do on one node. So now that we can scale it, we can get up to system sizes of over 100,000 atoms and start to see the physical processes that we would expect, like segregation of atoms. So these are just preliminary results of things that we can do with this new method. So just to summarize with some conclusions, we now have a general and scalable method for doing hybrid MCMD simulations within LAMMPS. You, in turn, can really expand this to any localized potential that you are interested in using for MC simulations. Currently, we have now implemented support for various popular machine learning interatomic potentials. So you can, of course, use whatever training data makes sense for your system and then train these potentials. Hopefully, this will then allow a new class of alloy simulations where maybe the accuracy wasn't available before. And in the future, we can use the scalability of these algorithms in order to work with experimental techniques like TEM to really tune and probe the different alloy properties and compositions. So thank you so much for your attention, and I'm happy to take any questions.
Thank you, Laura. Okay, time for a quick question or two, and we'll ask Josh to come up and get ready for the next talk. Maybe. Yeah.
Very nice talk. I was curious about the domain decomposition. So you have these like edges between the domains where you can't select on any given like Monte Carlo swap step. So anytime you're doing a Monte Carlo swap step, do you have to redo your domain decomposition so that atoms that are in those areas do get sampled so that you're fully like sampling your configuration space?
Yes, great question. So in this algorithm implemented by Sadiq, they have this margin around, so within your processor, there's this margin of atoms around their sampling window that doesn't get sampled. We've experimented separately. I haven't included in this talk because it's still in progress. Another method of domain decomposition where you're instead moving your window at each time step, and then each atom would have a possibility of being sampled. Yeah, so there's definitely different ways of doing this domain decomposition to ensure that each of your atoms has a chance to be sampled.
Yeah, because the reason I was wondering is in terms of also like reversibility of, right, if atoms like move in or out of that window, and then are you properly sampling the right distribution if some atoms like move out of the window where they could have been sampled?
Yeah, absolutely. So we're currently working on methods where all atoms would be included in a sampling window and make sure that you are sampling them. So you move your window, in the current method, you have 8 windows. So you move them 8 times within one MC step. So you have multiple attempts per like MC time step in LAMMPS.
Okay.
Yeah.
Thanks.
All right, any other questions? Not, let's thank Laura again. Okay, our last talk before the break is by Josh Kempinen from Michigan Tech University, and he's developed a tool called Lunar, which he's going to talk about, which can be used in conjunction with LAMMPS.
Cool. Can everyone hear me? All right. So yeah, my name is Josh Kempinen, and today I'm going to talk to you about a tool that I ended up developing. And this tool is called Lunar. Lunar is actually an acronym. And it stands for LAMMPS Utility for Network Analysis and Reactivity. And the way you can think about Lunar is it's a pre and post-processing tool to LAMMPS. And before we get into like details about Lunar, I'm going to give kind of the background of Lunar. So in my PhD and in my research group, we do basically this idea of process modeling for composite materials, where we have to like cure the matrix component and get the evolution of mechanical and thermal properties as the matrix is curing in our MD simulations. And that stuff is set up to higher length scales, like infinite elements, so we can model like how the matrix shrinks and how that affects composite properties. And it turns out that trying to model the matrix component it ends being a pretty large task. One of the reasons being is we need to model reactivity. So one of the things about Lunar in particular is it's meant to help do reactive molecular dynamic simulations. We heard Jake Gissinger talk about his tool fixed bond reactor, and Lunar directly helps set up stuff for reactor. And I also work with a force field called ReaxFF for doing really complex pyrolysis stuff for like carbon-carbon composites. And so the idea of Lunar is kind of shown in this flow chart here. LAMMPS is the central thing we're all trying to use. And Lunar is the thing that pre-processes stuff and post-processes stuff. And so the idea of Lunar is we can draw our chemical molecules or our species, whatever we want to try to model, in some sort of chemical drawing software, or we can get it from some sort of database. And then Lunar has a lot of different modules that can understand different file formats. And then we can get into parameterizing in force fields. One thing I should say is the majority of the work that we try to use is, use fixed bond force fields, primarily because they're very quick and efficient, and you can generate a lot of models very quickly. And so we can get our molecules parameterized in any of these force fields shown here. Once we have our force field parameterized, we can pass it into LAMMPS, do our LAMMPS simulations, whatever we're going to do. And then there's some post-processing tools to help analyze some of the properties that we want to get over our LAMMPS simulation. And so we've already seen quite a bit of basics about MD force fields. Again, I primarily work with fixed bond force fields, and there's these functional forms that end up defining our potential energy. So for like our bonded potential, most fixed bond force fields are harmonic in nature, so they end up taking on this blue type of potential shape where the bonds essentially can never be broken. Then there's obviously the Morse bond potential, which allows you to have some bond dissociation. This also starts to induce like anharmonic vibrational states. And I'll touch on that a little bit later on of some fixed bond force fields. But anyway, the primary difficulty with using fixed bond force fields is you have to define all of these parameters in these functional forms, like any potential. And for fixed bond force fields, it can be quite a task to generate your model, generate your bonds, angles, dihedral, and impropers, which is the improper shown here, and then go in and fill in these force field parameters manually, because there can be thousands of them. And historically, this has kind of been a manual process with some scripts and tools being developed throughout the time of using LAMMPS to try to help this process along. And Lunar is primarily focused at parameterizing those all these different potentials. So for fixed bond force fields, if you're not aware, I kind of view it that there's this intermediary state that you have to go to before you even get to parameterization. So you can take this like molecule, this is like a polyether oxide, and it's in your elemental representation. And then depending on the fixed bond force field you're trying to use, you go through this atom typing scheme where you basically start to discretize out and set up local chemistries with an atom type. So like for instance, if we were trying to assign the interface force field to this molecule, we'd have to go through and know that each one of these elements maps onto this specific atom type in IFF. Or if we're going to try to use the polymer consistent force field, we have to go through and assign all these atom types for PCFF. And similar thing for drying. And one other interesting thing about like drying and some of the force fields is they have implicit hydrogens, which is like the smallest way to do a coarse graining. So like your polyether oxide molecule could just be have implicit hydrogens on them. And so Lunar automatically will go through, and I think there's like 9 force fields that Lunar supports, fixed bond force fields, and it'll automatically define all these atom types for you for whatever molecular species you're trying to generate your models in. And so then once we have our, this is going to be a PCFF example. Once we have our atom types assigned, we have to go through that whole parameterization step. So like for like I'll just take the quartic bond for this kind of hydroxyl group. We need to find K2, R0, K3, K4, and so on. And this is where Lunar starts to actually help us out quite a bit. And I'll show you how. And then also for fixed bond force fields, charges are almost always modeled, and they're physically modeled, where Lunar has some charging algorithms built in. Most force fields that Lunar supports actually does charging through a bond increment method. I don't want to fully discuss the bond increment method, but a lot of the charging in Lunar is done through this bond increment method. It also has gas-Steger charge equilibration. And then it uses, for the interface force field, there's these carbon models with these virtual pi electrons to help model pi-pi stacking. And then it also has manual charge assignment if you actually need to go down that road. So the problem I was given as my PhD, I guess, topic was to model the evolution of a material called glassy carbon. And so this image just shows like we have some sort of precursor material, and we can heat that precursor material in reacts-FF. And in reacts-FF, the chemical reactivity is just, it happens. And so it ends up driving this like initial state, some pyrolyzed state. And in my PhD, it was basically we need to pyrolyze to a certain degree and then do a full sweep of like mechanical thermal properties of different states during the glassy carbon generation stage. And it turned out that I found out that reacts-FF was too slow for my computing cluster that I work on. And so I needed to develop a method that would allow me to convert from a reacts-FF force field to any fixed bond force field. And this is just an example of me converting from reacts-FF to PCFF IFF. So the idea is that Lunar can go in here and automatically atom type these parameters. We can then go fit those atom types with the different force field parameters. In this case, it was PCFF parameters and IFF parameters working in one model. And then I added IFF virtual pi electrons in here to model electrostatic interactions. So just like this model looks complicated from a topology perspective, but it's also complicated from a force field perspective because there's 2 charge models working together in here, and there's 2 force fields working together in here. And this was just all done with doing some clicks in Lunar. Lunar is basically a GUI-based way to do this, and we'll look at some of the GUIs. But this is the main purpose of Lunar, and it just so happens that Lunar has filled in some gaps in the fixed bond force field world of LAMMPS. And then kind of another little side project of Lunar and my work was in class 2-based force fields, there's things called cross terms. And I don't want to get into too much detail about cross terms, but the way to think about cross terms is they couple an n-body interaction to an n-body plus one interaction. So like if you're gonna have an angle, obviously there's a bonding potential defining this stretch and a bonding potential defining this stretch. There's an additional cross term that couples how this side of the stretch affects this side of the stretch. And this was done with PCFF, which is class 2. That cross term is harmonic in the sense that it takes on that harmonic shape. And what I needed to do was to develop mechanical properties, so we needed bond dissociation. And it turns out this harmonic cross term in the force field was not allowing us to model bond dissociation. So I ended up generating a functional form. So this is the harmonic form of the cross term, and then I basically made it into like a Moore's bond shaped cross term where we have some bond dissociation. So I don't want to get into details of this class 2. I called it XE, X for cross term, E is for exponential in the cross term. I don't want to get into details about this new force field. It's almost published in NPJ computational materials, but Lunar has automatic force field parameterization for this for this class 2 XE potential. Okay, now kind of just getting into Lunar and how to use it. Lunar is all Python based. It's cross-platform, so it works on Mac, Linux, and Windows. And so the main one is through GUI. So we'll just look at how to do this through GUIs. Lunar also has command line interfaces and such as well. But basically just run Python 3.lunar and it pops up this like overview GUI. And the rough setup of this GUI is top is essentially what's going to build your models. This top row of buttons, and then these lower row of buttons is approximately buttons that you might use to analyze your molecular system. And each little button I just call like a module. So we have our atom typing module, AltaLamp module, and I'll touch base on some of this just to get you an idea of what you can do with Lunar. So we'll just start off with a basic example of sheet builder. And so we click on the sheet builder button, it'll pop up another module. And then the big thing about all these modules is on this bottom right corner, there's always this quick help button. So you can click the quick help button, look at some of the documentation on how to use this. And sheet builder is meant to build like graphite sheets, carbon nanotubes, and so on. So this is just an example of building some sort of like boron nitride sheet. And there's a lot of settings in here, but the idea is you just change, it's all clickable. You can click and build your models and however you want to build them. This is kind of a unique example of building boron nitride sheets and then grafting on like certain molecular fragments if you wanted to model weird like pseudo carbon fiber bonded to some other materials. And this is just an example of the like roughly the 3 steps you take to use sheet builder to generate that model. Just an example of building a carbon nanotube structure. And now here's where the real the main parts of Lunar. Main parts of Lunar is atom typing and this AltaLamp. So we run atom typing. And it generates the atom types for, in this case, this structure here. And the big module in Lunar is this AltaLamp. So if you're an old timer, I guess, in working with lamps, there's an old module called MSI to LMP. I rewrote that I called all to LMP. And all to LMP completely addresses all the limitations that existed in MSI to LMP. So there's audio equivalent support, there's charging support, and so on. So if you're still using MSI to LMP, I would strongly suggest using all to LMP. And all to LMP interfaces a lot of other software, not just Material Studio. Okay, so I'm going to skip through some of this. So there, we do have support for fixed bond react. That's through the bond react merge GUI. I don't want to get into too many details about fixed bond react and how to do it, but it's all supported in a GUI-based setup. And then finally, just some property analysis. I have a tool called log analysis. This operates on a LAMMPS thermodynamic output log file. And the general idea is it's a clickable GUI that allows you to do different analysis setups. So like, for instance, if we're just going to look at the density evolution of a model, we want to average the certain last converged density states, and that average density is the density that you might want to report in a paper or so on. And the idea of the log analysis GUI is you can click and set up all your different analyses, and then you can save it as a mode, and then you can go back and reload this mode. So you have a really like easy way to generate a bunch of different analysis setups. So this is just an example of doing like an annealing run where we heat a polymer up to a certain temperature range, watch how it thermally expands. We can compute things like the coefficient of thermal expansion and glass transition temperature. And then there's another side project that I ended up doing that's implemented in Lunar that we call the regression fringe response, where we strain a molecular dynamic model, get the raw stress strain data, which is this gray data, apply this filtering to help reduce the thermal noise, and then do this idea of running a linear regression dynamically across that filter data, where we can end up defining the Young's modulus and yield strength 100% automatically with quite high accuracy, where we don't have to worry about the thermal fluctuations. And it's just that RFR method implemented into Lunar, where it automatically figured out the Young's modulus and a yield strength prediction. So with that, I'm hoping Lunar is possibly useful if you're into the world of fixed bond force fields and modeling reactivity with a more classical-based force field. Lunar's published here. Lunar has a GitHub here, and then the class 2xe potential I just generated, and the regression fringe response for stress rate analysis is at these papers. So, thank you.
Thank you, Josh. Hey, we have time for a question or two. Anybody wants to come to the microphone here? Or let me know if there's anything in the Slack or the Zoom chat. Okay, I'll ask one question because I think you mentioned a little about this at dinner last night, and I didn't see that you had a slide on it. What is like the future of Lunar? What are you trying to do next?
Yeah, so right now Lunar is the best way to use Lunar is through a GUI. And what we're going to do is we're going to rewrite Lunar so it's more like a Python scriptable language. Right now GUI is the best way to use Lunar. And so like we're going to call a new package called MoonPy, which is going to basically be all of Lunar, but scriptable in a way where it acts like NumPy, where it's pip installable, and you generate just an object that you can like force field or parameterize in a scripting way rather than using GUIs. So.
Okay. Good. Okay. Just, do you want to read it or you want to just tell me?
Can you talk about going from ReaxFF to class 2?
Yep. So, so the big issue here is ReaxFF doesn't have bonds implicit, so you have to end up generating bonds through ReaxFF. And it turns out ReaxFF does have a method for doing this. They have something called bond order. So LAMMPS has a command, I think it's called fix bond or fix ReaxFF bonds, I believe, and it generates the bond order file. And what we do is then we time average the bond orders together. And then use a bond order cutoff. And for ReaxFF, that's almost always 0.3 bond order. And we generate our bonds. And once we have our bonds, we can end up doing our automatic atom typing. And then from the automatic atom typing, we can end up doing the force field parameterization like PCFF or drying or whatever force field you kind of want to do that automatic parameterization in.
Good. Okay, let's thank Josh again. So it's time for a break, and we had a little extra slack in the schedule, so we're gonna get a full 15-minute break, but we'll start promptly at 3:30, is it? Yeah, so be back in the room at 3:30 if you can for the last talks of the day. Thank you.
I just wanted to make a quick announcement about the dinner plans this evening as well. So we have a reservation for 30 people at the County Line restaurant, which is basically at the base of the tram, but it's a 1 mile drive from the restaurant to the tram station. So we're going to try to
Gonzalo, if you want to test it, you can do it right now.
Hi, Richard. Thank you. Okay.
Beware, you're still live streaming, so everything's being recorded.
Okay. Sure. Oh, I can't share because it says the host. Okay. I think everything is great. It's going great.
Yeah, so we hear you loud and clear. Just audio is great.
Okay.
Only
And the
problem is
slides?
we see your presenter view.
Okay. Okay, so maybe I
There
have
should
to
be a button
disconnect.
to swap it.
Yeah. Okay, so how about now?
Perfect. Yep.
Okay, thanks. Great.
Okay, so I'll put back the screen for the break.
Thank you.
Hello, I am Daniel. I will try to test my PC and microphone.
Yeah, we can hear you loud and clear, as well as the rest of the internet.
Great, great. So I will show you the screen if I can
Sure.
share. Disable share this. Disable share. I can't share here.
Try again.
Okay. Now I can. Full screen. Can you see the presentation?
Yes, just maximize and start it.
Okay. I will wait to 5.5.
Yeah. Okay, so it works, but we're still a few more minutes away. People are still
Great. Great. I will wait. Can you see this?
Yes.
Great.
Okay, just mute yourself and wait until I think Aiden, or no, Steve is going to introduce you.
Okay, I will wait that you can give me the introduction and start.
Are we hearing some background noise from you?
Okay. Do you still seeing my screen?
Yes.
Okay. And now?
Yes.
Okay, thank you.
Is there any chance you can get the background noise to stop?
Oh. There are some dogs in my neighborhood. Sorry. Okay.
That's better. Thank you. Okay. We are going to get started on the last session of the afternoon. We've got several final talks, 15-minute talks today, and the first two are, I'm sorry. First two and the last one of the session are virtual. So our first talk is by Daniel Castillo Castro from Chile, and he's going to talk about tensor networks and their connection to LAMMPS and potentials.
Okay, thank you. Thank you for the space to do this talk. I will talk about, as you can see in the title, about the tensor networks and the potential that would have to make better lab simulations and or MG simulations in general. I will start talking about what is a tensor. A tensor basically is a generalization of scalars and vectors. A scalar could be a tensor of range 1, and a vector could, no, sorry. A scalar could be a tensor of range 0, and a vector could be a tensor of range 1. A matrix could be a tensor of range 2, and so on. So I draw a version of a tensor, a 3D tensor with this kind of numbers. So a tensor could be a good concept to simplify some definitions in math physics or computation in general. These methods could be used with different codes in different languages. I show you some examples. ITensor, TempI, tensor operations. I share to you some references about the work on tensors. So tensors is an area of recent interest to several applications. The most interesting application that the most interesting application that I will see is the application in physics. In physics, we can use tensors to represent physical quantities like the stress tensor, the moment of inertia, the stress energy tensor. The stress tensor in LAMMPS is very important to take elastic constants. And we can do two representation of different frameworks of space and time. In relativity, you can use the tensors in different moments, space-time tensor, energy tensor, etc. Another interesting concept is the tensor networks. The tensor networks is the simplification, could be as a method to see on a simpler way and graphical way the matrix products and to generalize the matrix products. So if I can, all these circles can be shown as a tensor, and a tensor in these points we can put different branches. So a point with two branches is a tensor of range 2 or a matrix. So here this representation is the same like multiplying the matrix A by the matrix B by the matrix C by the matrix D. You can see something like that. As an example of the recent interest in tensor networks, I show the statistics that PubMed shows about the use of research in tensor networks, quantum physics materials. So this is an area of very new interest that could be a area to explore. Okay. And very interesting example of the use of tensor networks in physics is the methods that are being developed from quantum mechanics and quantum materials in general. So I show you two examples. The examples of use of tensor networks to simplify and show and give a more intuitive way to understand the wave functions, or the operator products, or the connections between products of matrices of operators and quantum operators, and the techniques that you can use to approximate, for example, a wave function. We can approximate a wave function, for example, using matrix product states. That could be interesting to make 1D systems. For 2D systems, it can be used something like PEPs, or the hierarchical Tucker that could be understood as a tree algorithm. These examples are examples of algorithms that we can use to implement tensor networks to approximate a quantum system. Here are some references. And the question of interest is if can these tools be an adequate tool to improve the molecular simulations as we do in labs. Okay, or another interesting example, sorry. Tensors are useful too for all the related with computing. So I show you the example of NVIDIA that makes some developments about the software writing, software developing that use the theory of tensor networks to have more efficient and more computationally cheap codes. And the concept parallel to the analog to the concept of CPU or GPU, you can use the TPU, tensor processing unit. This can be take naturally vectors and matrices more simpler and computationally and energetically cheaper. Okay. So all this I said can be translated into a meme. Tensors everywhere. Tensor networks could be an ultra powerful tool that we can see in different branches of physics, math, and computing, and we can. And so I had a question that is very interesting. That is, if tensors could be useful for quantum simulation. Okay, we are here in the area of empirical MD or ab initio MD. LAMMPS is a tool for MD, and we can work on some simulations on different scales. From quantum mechanics, simulations using quantum computing or something like that, until simulations like FEA for continuum mechanics or for materials for engineering. So an open question for all the area of computational physics is how to relate a simulation of one area in another area. Why I am interested in this? Because my research, I just finished my PhD degree, was related about the connection between different areas. So I was working on carbon, fundamentally on carbon, using MD, using LAMMPS specifically, and two, working on FEA. I have a published paper about FEA using MATLAB, and some tools on quantum computing or DFT that I am working now. So after 5 years approx in MD for different materials, I have two questions: how to scale from one formalism to another, and can tensors contribute to the result exchange? So I am thinking
Daniel?
in a sorry.
Daniel, I just want to make sure you know you got about 5 minutes left in your time slot, okay?
Okay. No, I will finish soon. The proposed work that I have is the combination of Block 2, a tool to make DMRG for few atoms, approximately 100 atoms, and with Block 2 we can calculate ground state energies. Nekip is a tool that probably some of you knows that can be used to build potentials and is an application of machine learning. With Nekip, we can make a MLIP. And LAMMPS can be implemented to test the results. For example, the energy respective to atomic distance, the RDF, the stress strain curves, etc. Well, here's an example of a code of block 2. We are making a file with some data. The data is related with a lattice we can generate. I tried to do an example for silicon atoms. The silicon atoms can be adapted to make a simulation in a computational basis that is a correlated computational basis. And we can make NDR-MG simulations for a quantity of approximately 32 atoms. And we can write a system that includes the positions of the atoms and the forces. After that, we can, with the NICIP, make a process of train the potential with some data. The file that has the configuration for training can be shown here. We use the file we generated with the VMRG, and it can be shown some metrics about training. Using the library assay, we can make some script for LAMMPS that will be used to test the system. The results are not so good, but could give some advice. I will show you now. For NICIP, using only the library NICIP, we can see this moment of atoms, but including the RMG, we have less control of the movement of the atoms. The results for silicon atoms are not satisfactory yet. Probably it will be need improvements on the DMRG that consists in make new algorithms, for example, using tensor networks or another formalism to calculate the forces for each atom, and possible geometry simplifications depending on any system. So, as a conclusion, new methods could be used to make improvements of LAMMPS, contributing with the connections with another language. This is a work in progress. I wish that in the next LAMMPS, the LAMMPS workshop have better results, and probably I can be in New Mexico to calculate some methods. The relation between tensor networks and empirical potentials is very interesting. The results are not the best, but it could be a good chance to work, and I will work in this the next months. Thank you very much.
Sorry, does anybody have a quick question for Daniel? And can someone check if there's anything in the Slack chat or Zoom chat? Okay, I don't think there's any questions, but Daniel, we thank you for joining from a long, long distance. Okay, let's move to our next speaker, which is also a virtual talk. Not sure on the pronunciation of the first name. It's either Altaf or Aitaf Hussein, and he's at Fukuoka University, which I believe is in Japan.
Hello.
Okay.
Can you hear me, please?
Yeah, can you please unshare?
So, I think someone else is sharing, so I can't share my slide.
Try again.
Hello, sorry, I came back. Yes.
Is it okay?
Yes, it's okay. Sorry, good.
Okay. So, hello everyone. My name is Muhammad Altaf Hussain, and I'm from Fukuoka University, Japan. So today I'm going to present my talk on estimating how the crystallization methods influence the mechanical properties of semicrystalline polymers using LAMMPS. So the motivation of this study is the mechanical properties recycling methods where the physical degradation and physical regeneration theory was adapted in our simulations, where we have implemented the twin screw extruder experiments where the shear treatment gives the two polymer chains to detach themselves as it is an unentangled state. And with the relaxations, this state becomes completely mixed. And due to that, in the melt state, in the crystallization state, they behave differently due to the tie molecules or the quantity of the tie molecules. And these applications are very crucial for, these applications are very crucial. Can I share my laser point printer? Am I audible? Can anyone confirm? Hello?
Yes. Yes,
Okay,
it's fine.
thank you so much. Thank you so much. There are two methods from the crystallizations we can study using the computational methods, using especially LAMMPS. The quiescent crystallization method, where the temperature is held for some time at the constant temperature, and there's a flow-induced crystallizations or stretch-induced crystallizations, where the polymer chains are entangled or elongated in one directions. Then with the relaxations, they form the crystal morphology. And basically the plastics or semi-crystalline materials, so you will see some different phenomenons observed for their crystallization and morphological differences. And their crystallization rate is also different in both cases, as well as the mechanical properties. Due to all these structural differences, they form some isotropic and anisotropic structures. And they have distant industrial relevance, and because of this one, we have adopted to see that how these two methods behaves in molecular dynamic simulations. So initially we have started our simulations. So based on this physical degradation and physical regeneration theory proposed by Professor Shigeru Yao at Fukuoka universities, we have adapted this simulation in our project. So if you see, the typical semi-crystalline structure consists of the tie molecules or bridge molecules, fold molecules, and the tail molecules, which is also called ciliums. And there are several computational methods have been studied, and they have manually they have created some tie molecules and such kind of crystal network in their models. However, we would like to see that how spontaneously these polymer chains will convert from the melt state to semi-crystalline structures. So the LAMMPS plays very crucial role in our simulations. So in this workshop, we are trying to explore that how these simulations were carried out using the LAMMPS. So the basic condition is we have packed this all polymer chains randomly using the enhanced Monte Carlo simulations and using LAMMPS for longer times simulations. We are able to crystallize these structures into beautiful semi-crystalline structures. Then using this Octa and Z1 code from Professor Kroger's code, we have captured the morphological features. And also the mechanical properties also we have evaluated using the LAMMPS simulation techniques. So in the amorphous state, where the crystallization is this is the isothermal crystallization state, where we can see how the polymer chains are packing into semi-crystalline structure. So if you see the crystallization of these chains, they are completely converting into a semi-crystalline structure, where the random coil structure was the initial state. So the density also changed during this simulations, and also as well as the morphological lamellar structures formation we have seen during this evolution of time. So in the stretch-induced crystallization, we have stretched our cubic cell model to an axis to come close to 300% from the original axis length. And After that, with some relaxations, we have seen the laminar chain formations. So during the stretch structure, the simulation box is elongated up to 300%, and all the laminar chains, all the polymer chains are elongated into one directions. So from the morphology, it has been proved that from experiment as well as from our simulations, the isothermal crystallization structures show the random oriented structure, while the stretch induced crystallization shows the shish kebab kind of morphology. So during the stretch induced crystallizations, we have seen the polymer chains are stretched along the one direction and it is completely shrunken in the in the other two directions. So when in the relaxation process for close to 100 nanoseconds, this is beautiful semi-crystalline structure has been formed. We have quantitatively measured 3 samples of such initially packed structures where all the laminar chains are differently packed from using the enhanced Monte Carlo simulations, but the density is constantly maintained at amorphous state, like 0.85 gram per centimeter cube at 300 Kelvin temperature. So in the melt state, the densities are completely elevated, and then also in the stretching process, also they are further elevated, or sometimes it is constant. And while in the crystallization state, the densities are gradually increased to close to experimental density, even though the densities are a little bit underestimated compared to the experimental results. But in the mechanical properties, they have shown a characteristic peaks. So in the stretching process, all the chains are elongated, so the density is completely increased. So the crystallinity using the cosine functions we have calculated using the Python code after the LAMMPS simulations. At different temperatures, they have elongated. And in the relaxation process, initially the polymer chains are quenched, while as the relaxation time is increased, the gradual increase in the crystallinity is observed. So using the Python code, we have also evaluated the laminar orientation in the stretch-induced crystallization model for 370 Kelvin. So in the completely quenched or coil model, there is no a signature for the laminar orientations at one particular angle is observed. While in the stretching process, the laminar chains, the bipolar model has been observed. Here, you can see the laminar orientations are slightly splitted into 2 directions, which indicate that the polymer chains are aligning along the z-axis. And in this semi-crystalline structures, the laminar chains are completely stiffened due to the strengthening or straightening of the laminar chains, and they are slightly tilted into the z and y axis. This is the tilt angle we have calculated for our model, and we also compared with the experimental results. And our simulation results shows that the tilt angle is close to 25 to 35 degrees, and which is close to the stacked laminar orientations observed for the experimental results, where the tilted angle is reported to be 25 to 40 degrees 40 degrees, which is close to our simulation models, indicating that the simulated model is close to the real high-density polyethylene models.
Altaf?
This is
Altaf, just to let you know, you've
Yes.
got 5 minutes left. Thank you.
5 minutes. Okay. Thank you so much. Okay. So this is the quiescent isothermal crystallization model. We have seen the laminar orientation is completely random, even though the model is different and the laminar chains are different. In the realization process, we have seen that the crystals are formed, but their orientation is uncontrollable, even though the van der Waals energy is completely decreasing. And it shows that the model structures are stable enough, but the laminar orientations are still random. So we have also evaluated the morphological changes during these different process in the simulations for 2 methods, and the number of entanglement points were completely showed that the elongation process are completely reduce the number of entanglements, while in the quenching process, the cooling process is slowly in the equilibration process it is increased, but in the cooling process, due to the crystallizations and the number of the polymer chains which are entangled or aligning, so the laminar orientations disentangled from the entangled regions to form crystals. So this is true with the experimental results, where we have seen that some saturation point also seen after after the complete saturation, after the all the unentangled points becomes the laminar chains. Coming to the mechanical properties, if you see the morphology, as we have seen in the laminar orientations, the mechanical properties are random. So the laminar orientation is random, so the mechanical properties also shows the similar behavior in their elongation process in the tensile test. While for the stress-induced crystallization models, here we have seen some anisotropic mechanical properties. A high stiffness and high elasticity modulus were observed when the polymer chains are elongated along the deformation axis, while in the perpendicular direction or transverse direction deformations, the lower elastic modulus has been observed, indicating that the mechanical properties are anisotropic. This is morphologic changes showing that how the voids are formed during the two types of deformations for the stress-induced crystallization model, which mimics the earlier reported model by Professor Yamamoto. So indicating that our models are reliable and it is regenerative. So from the studies for this project, we have concluded that to understand further for capturing the industrial relevance, we understand that the uniaxial stretch-induced crystalline methods will enable us to investigate the high-performance fibers, films, and packaging materials, which where the shear history cannot be captured, to see how the physical regeneration theory will be reproduced from the simulations. And the isothermal crystallization model, where the quench crystallization happening for the rheological applications, this model is very suitable, and we should prefer this kind of model for our project purposes. So all the simulations we have used the LAMMPS code, and we have used the high-performance supercomputing facilities from the Kyushu University, Ito campus in Fukuoka, and also the Tokyo Institute of Technology from the Tokyo. So we would like to thank you, thanks the NIRO project for this financial support for this project. So thank you so much for your attention. If you have any questions, I would be happy to answer you anything.
Thank you, Altaf.
You're welcome.
Is there a quick question? Anything online? Here, one quick question. Are the structures you're seeing, like the semicrystalline orientations, are those sensitive to how fast you do the pull, the elongation rate?
It is 10 power 10 per second, which is quite faster than the experimentals, which occurs in seconds. It's much faster.
Yeah, typically much faster in the simulation. Okay, thank you.
Yes.
Okay, our next speaker is Meg McCarthy, one of the LAMMPS developers, and the first part of her title is Journeys into the Third Dimension and Beyond. So for those of us who live live, this will be a very interesting talk.
Got it. Okay. Hello. Hello, hello. Can you all hear me? All right. Make sure this is off. All right. So it's me again. Hi, everybody. So let me share my screen. Okay. gosh, the Zoom window. Okay, there we go. Yes, hi, I'm Meg McCarthy. I work at Sandia National Labs. I am a staff scientist there. Thank you for the introduction, Steve. And I also live in the third dimension, like most of us, but not everything that we simulate does or that we want to simulate does, right? So I will show you a little bit of what I've been working on through a project funded through the lab-directed research and development funds on stainless steels. But before we go there, let's think a little bit about what it means to have a drawing and what it means to have motion in something. So as we all know, something that we've all been fascinated by the past 200-ish years is taking a drawing and making it live somehow. And of course, this might be something you find absolutely fascinating if you're in the current, paying attention to the current era of generative artificial intelligence. You might find something like this a bit of nightmare fuel. I personally do a little bit, but it is beautiful. So I couldn't actually embed the video here. So just imagine this looping over and over again, that Mona Lisa begins surfing. And so that what we learn from having time in things and structure and evolution and dynamics, we can learn a lot about the Mona Lisa itself, right? We learned she likes surfing, for example, and leather jackets, apparently. Now, for mod sim folks, we also like the idea of taking something that's static or impossible for us to do and giving it life, making it more interpretable, giving it more dimensionality. So, if I'm allowed to say that. And also making things beautiful, fun, funny, entertaining, memorable. And I wish I could animate the beautiful tutorial images from the GitHub. You'll have to go there yourself to see those. I thank Mitch Wood and Steve for their animations here, which are, to me, very fun and just as worthy of animating. So now, what does this have to do with my science? So what I do and what I'm working on right now is taking high-resolution transmission electron microscopy, HRTEM, and pairing it with molecular dynamics with LAMMPS as much as possible. And they are a very natural pairing. You can see from these little videos here on this side, we have an actual in situ TEM video of gold, defects in gold at a grain boundary moving. And over here is an MD simulation of the same thing. And you can see this structure kind of retreating into the grain boundary and then re-emerging here. And this is a wonderful paper where they explored this defect and what effect it has on the mobility of that grain boundary, something I studied in my PhD. Now, in my PhD, I loved these kinds of studies. I thought they're very, very powerful. But you can really only do this when you have a simple enough structure. What if you have something like this? So I'll explain what the green, all of this over here is in a moment, but this is a this is a TEM micrograph of deformed 304L steel, and 304L is just a low carbon, quite common steel. And under deformation, it forms lots of different phases, Martensitic transformation, some of you probably know, and you get structures that look like this. How can we put that into something neat and tidy like we have here with TEM and molecular dynamics? I would say we can't, not really, and not get the same fidelity that we get from something simpler. What if we want to understand the intersections here with these complex kind of stacking faults and bands of epsilon martensite? How do we go about learning about this? Before I continue, I'd just like to explain briefly what this image here is, this green and red. So you recognize maybe from Oviedo the color scheme of green for FCC, red for HCP. I wrote black here, I meant to write white here for the unidentified or other coordinated atoms. But this is actually not from LAMMPS. This is from my TEM collaborators at Sandia have written a very nice MATLAB code that does two-dimensional polyhedral template matching. So we all know and love that from Oviedo and from LAMMPS itself in 3 dimensions, but you can actually do a projection and get very similar template matching in 2D. And this is what these folks have done. They have a paper and a GitHub and so on. If you've MATLAB license, you can run this too. Now, this MATLAB code does a very nice job so I'll have to go like this, does a very nice job of extracting features, so phases, stacking faults, and so on. I'll show you a couple more later, from these TEM images, which my co-author, my colleague Alejandro Hinojos at Sandia, California, has kindly identified and is working on characterizing. But even then, this is not quite giving this life, right? It's a static 2D image, and Alejandro and our other collaborator, Douglas Medlin, want to know what would this look like alive and moving. Now, we know what it takes to take a drawing into a movie. We know from 200 years of doing this, lots of science, actually, lots of technology, money, these days GPUs, and actually in past decades as well. But what do you need beyond that for taking a static image like this and putting it into molecular dynamics? I'd say all you need beyond that huge amount of other stuff is a plane spacing. So I'll explain what I mean in a moment. Once we have a once we have a TEM micrograph, and we can, from this nice software, or maybe even through LAMMPS or our own methods, we can get some kind of phase mapping. So I've got some phases here you might recognize if you're into steels. Gamma is austenite, FCC, epsilon martensite, and so on. But what we need to make it 3 dimensions in a crystal, and using crystallography, known crystallography, because we have these phases, are these little unit cells. And we need to know what's called the zone axis. So that's what the axis you're blasting your electrons down to get your image. And once you have, the crystallography and your zone axis, you can then deduce almost, let's say, most things about the crystallography and thus the 3-dimensional structure of your TEM micrograph. By the way, this is called an epsilon martensite intersection. So I might say that again, just wanted to point that out here. So I decided this was a good place to start to attempt to add 3 dimensions to the 2D micrographs that my wonderful TEM colleagues had made. And so I went about just doing kind of what you do when you have images. You segment them. This is the first thing that we do, is getting the edges and borders identified. And then comes the important part, where we add that plane spacing, where we add that 3rd dimension. And so I have several algorithms. I'm not going to go, this is going to be a very image-heavy presentation, but I use several different kinds of algorithms to identify the local atomic environments of all of the, yes, that's an important phase, of all of the atoms, to exactly align them to the identified atomic intensity peaks that you see in TEM and that the phase matching program in MATLAB finds, so that they're exactly aligned. Now, the only thing they can't align is that Z direction. And that is the tricky part here. So you can see in this animation, there's kind of these filling algorithms. They're kind of piecing things together. The red means it's sort of okay. It goes to gray. And this ending section, can I pause it there? There we go. This is the key part. You can imagine that. And you'll see it very clearly in the next slide. This part where you have these stripes kind of matching is where you're really matching the crystallography and embedding the actual defects and kind of phase information, dislocation information that you're already picking up in your micrograph from the 2D PTM software. So this is kind of this thing in the center is the key part. And that's, I'm doing this chop thing. These are these lines, these rows of different heights of Z atoms. If you can imagine looking side on, we need to change in the plane spacing the height of all of these different rows. And we need to align them perfectly between phases. I know this is not the easiest thing to look at, but imagine the purple is lower and the yellow is higher in coming out of the plane. And so I've kind of overlaid where we have an HCP phase or an epsilon band and the FCC phase matching, and also some dislocation-like structures here where they intersect. You need to have these aligned so that your zeros always follow the correct crystallographic pattern to kind of have that phase matching merge. And performing, many of us know and love the Burger circuit. Getting the Burger circuit around these phases, we can start to deduce what kinds of, for example, dislocation content exists at this intersection. Now, in addition to being able to identify phases and defects, we can also do fun things. So we can do things that may or may not be true, may or may not be reality, but we can't test in TEM easily. Or we did our TEM years ago and we can't go back to that sample, right? So we can do things like experiment with chemistry. That's what I have over here. This is actually just a random solid solution for a fairly traditional steel. But using things like the Alloy Express molecular dynamics Monte Carlo software that Laura Zecchi was talking about, we can then do some experimentation. If we observe something unusual, we can say, hey, was there a precipitate there? Was there unusual chemistry there, something? Or maybe it's actually, more or less a random solid solution. We can also do things like build and test hypotheses about why and how these intersections formed. I think I'm running out of time, so I'm going to go ahead. And we can add time. So this is what I meant by beyond in my somewhat cheesy title. This is the fourth dimension that we can play now with dynamics. So we can add temperature, we can strain things, we can indent it, we can do all the fun things we saw in tutorial. So this is kind of the goal for not just one of these images, but many. I have dozens of these from my collaborators. And so I am now working on sets of algorithms with the help of lots of folks in my kind of Sandia vicinity and elsewhere, computational and experimental, and making some software that can automate this quickly and give you all that information that you want without too much fussing about and needing to do things by hand. And so this is an example of a structure that takes a lot more time to build algorithms for, but is going well. And I hope to have a manuscript out describing all of this in the next few months. One last thing is that the software is quite conservative. And if it doesn't, so the 2D PTM software from my TEM collaborators is quite conservative and will refuse to identify things if it doesn't find a good template for it. We like this behavior. And so another thing we'll be doing is experimenting with what to do with unknown structural regions. And we can then hypothesize and say, hey, what could this be? We can test the stability with different interatomic potentials. And there's a large range of things that we can do. I think I'm almost out of time, but I will just very quickly pick up on something that Mitch was talking about earlier that is also exciting. We can also, once we have these structures in LAMMPS, we can extract parts of those using active learning like in FLAIR, or this new generalized representative structures for atomic systems that James Goff and Mitch and other folks have developed. We can extract regions of uncertainty and make small enough DFT cells to run as training. And I think that means I'm out of time. So thank you so much for your time today, and happy to chat more sometime if you're interested.
Thank you, Meg. I think we have time for a quick question or two. I want to just make sure the microphone is on. There's a button on top, pull towards you.
Cool. Yeah, great talk. Really cool. Thank you. I don't know much about TEM, really. Is there a way to get composition information out of TEM, or is that like totally impossible?
Way to get what information?
Like composition information, like what elements are where, I guess.
Yes, but it's a separate technique that is time consuming and may not be feasible for the samples you're looking at. But yes, you can get composition information.
Cool, yeah.
In some types of TEM.
When you have a final atomistic structure, is your measure of goodness that it matches the TEM exactly, or that it's a low energy structure in the MD model?
Oh, that's a good question. Since the structures are imaged at usually a finite temperature, the thing I ran is actually at 1500 Kelvin. It definitely wasn't run at 1500 Kelvin in the TEM, but yeah, my goal right now when I'm working with folks is to get it to be stable at 300 Kelvin, so about room temperature. Okay. So yeah, but there's a lot of arguable, you could make a lot of stability metrics, and probably many of them are very good. So,
okay.
Yeah.
Thank you again, Meg.
Yep. Thanks.
Let's see, is Ilya here? Okay. All right, our next speaker is Ilya Nikiforov from the University of Minnesota, and he is part of the OpenKim project centered there and is going to tell us about some of the latest developments.
All right. Thank you all very much for coming. As Steve said, my name is Ilya Nikiforov. I'm a research scientist at the University of Minnesota, and I'm one of the head developers on the OpenKim project. And today I'll talk about mainly the project in general, but also our efforts to generalize our property evaluation framework to arbitrary crystals. And I'll go through exactly what I mean by that. So first, the OpenKim project in general. This is the blurb we have on our website, openkim.org, about what we do. I think it communicates pretty well, so I'll just read it. OpenKim is a curated repository of conventional and machine learning interatomic potentials that are compatible with many major simulation codes through a simple plug-and-play API. Each potential is verified for coding integrity and benchmarked against a variety of material properties, empowering users to discover and use the best potentials for their research. And a little more information, we are funded by the NSF. We were established in 2009. We have 661 interatomic potentials at this time, including classical potentials like EAM and ReaxFF, and machine learning potentials like GAP and NetQuip. By my account, we are the largest repository on the internet, and we're still growing. And content is contributed by staff and the community at large. So hopefully Lucas's talk earlier in the day kind of convinced you why repositories of interatomic potentials are important. So I'll talk what makes Kim different from other places on the internet where you can get interatomic potentials. And the majority of this talk will talk about the evaluation framework, but I'll start by talking about the Kim API. So I said it was plug and play. What does that actually mean? So the Kim API, it's a system-level binary package for Linux and Mac OS. It's installable from Conda, Homebrew, or from source. It is a mature and stable package. It includes a command line package manager for installing and downloading potentials. So let's just go through this thought exercise. Let's say that just suspend your disbelief a little bit and say that you've already gone on openkim.org and decided that this is the potential you want to use. This long string is a specific potential in our repository. And let's say you don't have anything installed. So one thing you could do is you could just install the Kim API and LAMMPS from Conda like this. And then you use the command line package manager to install the potential just with this command. And then on the lower left here, you see how you would use this in a LAMMP simulation. This is just a LAMMP script. It's kind of split it up in the same thought process as the tutorial yesterday, where there's an initialization step. That's where you use the Kim init command to declare what potential you want to use. Then you define your system. In this case, I'm just reading some data for copper 3 nickel or cobalt 3 nickel. And then instead of any kind of pair style command or anything like that, you issue the Kim interactions command. And you issue your mapping of atom types to numeric type labels. And then you run your simulation. And the Kim commands are documented on the LAMMPS documentation, of course. On the right, you have the analogous non-Kim input, which is, at this point, I don't think you're going to be too impressed. It's not very different. Setting up an EAM potential is not very complicated. You do have to go and find the potential file somewhere. And a really important thing, I think, about the Kim version of this input script is that it automatically prints out citation information in your LAMMPS log file, which is very important. And that's because each Kim potential is a digital item with its own DOI that you can cite, and it also references the source papers. But now let's say you want to change the potential you're using in the simulation. This is also an EAM potential, but it's combined with a ZBL short-range repulsion. So since you've already installed the KIM API on your system, you just use the package manager again to install that potential. And the only thing that changes in your KIM script on the top left middle, sorry, is the name of the model. Whereas if you want to change the potential in a non-KIM script, a lot of things change because you have to change from EAM to hybrid overlay. You have to add the ZBL repulsion. The specific numbering only works if you have the specific atom type 1 is cobalt, atom type 2 is nickel, and it's et cetera. So that's an introduction to the API and how that works. And LAMMPS is just one of the softwares that has this kind of potential type agnostic plug and play functionality. These are other projects that use us. The NIST IPR Pi software that Lucas talked about allows you to access KIM potentials and these various other softwares. Okay, so now moving on to doing calculations with these potentials. So we do this automatically in the KIM processing pipeline. And it's any potential that's uploaded to OpenKIM, it's automatically run through a bunch of simulations using our distributor pipeline that sends computations to various HPCs around the country. Something I'm not going to talk about a lot, but I think is very, very important is what we call verification checks, which are automatic computations that make sure that potential makes basic sense, that it's rotationally invariant, that it's translationally invariant, that it's invariant to permutations, that it correctly supports periodic boundary conditions, that it's continuous, that it doesn't have memory leaks, stuff like that. That's, I think, very important. And now moving on to computations of material properties. So before this crystal genome project, this is a list of stuff we've done. There's some very impressive stuff here, I think. I'm not going to go through every single one of them, but there's thermal properties, and here's on the right side, I think, a very cool picture where we did a study of grain boundaries using hundreds of potentials, and that was all just done by querying our public database, and we could make beautiful graphs like this and really think about the behavior of different potentials for this property. But the problem is that until we started this crystal genome project, that was all for simple single element structures like FCC, BCC, et cetera. And of course, the point of the slide is just to show you that that is only a tiny fraction of the materials that we know, of even the crystalline materials that we know. And there's just two pictures of some structures. So this is where crystal genome comes in, and where we are kind of restarting our development of our computational protocols to generalize them to arbitrary crystals. Specifically, we are using the AFlow prototype designation to classify materials, which is in that those are the strings like AB underscore, et cetera, that you're seeing in that graphic there. So this is a both human readable and complete symmetry reduced description of a crystal. And we can create these material entries from any coordinates file, but for now we've just ingested 32,000 materials from the AFlow DFT database. And that also allows us reference data for comparison of evaluation of these potentials. Another thing that we're doing with Crystal Genome, with this kind of restart of our property evaluation framework, is that our software has always been open source. You've always been able to go online and read the source, but it's really been very catered to working in our pipeline. So it was always difficult to use our computational protocols outside on your own machine and stuff like that. For the first time, we're making our protocols accessible as a Python package called KimVV. And this can run with KIM models, which also means that because it's possible to locally create a KIM model from any LAMMPS pair style, that means that it can run with any LAMMPS pair style or any ASC calculator. So theoretically, that means you could actually use these protocols, the same exact protocols you're using for interatomic potentials, to calculate with DFT. I haven't tried that. I have tried with DFTB, and that works. I calculated elastic constants with DFTB. So in the final few minutes, I'm going to just show some screenshots of our new website, because now that we have 32,000 materials instead of just a few single element structures, we need to rework our website to be able to find and display these things. The first thing I'm actually going to show is an old part of our website that's still up, which is focused on the individual potentials. Each potential has this web page that you see on the right side, which contains a ton of information about the potential, a ton of metadata. This really cool graph you see on the right, that is an AI-based model that analyzes the citations that cite this model and determines whether the citation used the potential in computations or merely cited it as context. So that's what happens if you click on the right button on our new front page. If you click on the left button, you are going to go to a search like this. So this is a crystallography-based material search. Everything on our new system is very crystallography-based. You're going to have some filters for narrowing your search for materials. There's a bunch of question marks you can click on for explanations, and below you'll get a summary table for each unique crystal that fits the chosen criteria. And then if you click on one of those blue buttons that save your results, you'll be taken to a page like this that is for a specific material. And there's a drop-down where you can see select an interatomic potential to view the predictions for that interatomic potential that we've computed. There's a section where there's a visualization of the structure and crystallography. You can download the structure. That's the relaxed structure with this particular interatomic potential. And below that, there's a bunch of sections for the properties that we've computed. So far, we have a few static properties like elastic constants, anisotropic pressure versus volume curves, which I think is kind of cool and not a lot of people do, where we actually impose pressure boundary conditions, not just stretch isotropically. Obviously just the equilibrium structure of the crystal at 0K. Very soon we have vacancies coming, we have phonons, and we have some finite temperature properties like heat capacity, free energy, and anisotropic thermal expansion. And we put a lot of effort into making these protocols really, really robust. Like, for example, the elastic constants computation. If you've ever computed elastic constants, you know that it's sensitive to step size and stuff like that. Our protocol actually iterates over several step sizes and methods. It computes uncertainty, and it chooses the lowest uncertainty. And then if you open one of those sections, you'll see a page like this. This is specifically just the equilibrium crystal structure. And because we're very focused on making everything crystallography based, this is symmetry reduced. So this is the crystal structure. And instead of just giving the XYZ coordinates, although you can get those, you can just download the file, we are giving the symmetry reduced description based on that AFLOW designation that I talked about. I guess I didn't give AFLOW enough credit. AFLOW is a consortium that does DFT calculations, but for their own convenience, they developed this really, really great crystallography software and repository of crystallographic prototypes. Yeah, so there's pages like this for every single property that we've computed. On the right, there's an interactive bar chart that you can click on to get more info. There's a lot of work that goes into getting this info and the crystallography exactly correct, both that we've developed internally and third-party software that we use, like the AFLOW software and SPGlib. So that's the bulk of my talk. For more info, I encourage you to go to the breakout session tomorrow. It'll have an introduction to crystallography so you can better understand those weird strings that are in AFLOW prototype label. And I think if you're a material scientist that does solid crystal materials, you should know crystallography anyway. On the openchem.org website, there's documentation. You can email us directly at support.openchem.org. We are one of the founding members of matsci.org, which is a forum for material science that includes many projects, including LAMMPS. And then also Chem Initiative is a part of a larger effort, or sorry, OpenChem is a part of a larger effort called Chem Initiative, which includes other projects, including some exciting ML projects like a database for fitting interatomic potentials. It's first crystal data, and there's a foundation model that we're developing. And thank you. That's my talk. Thank you to everyone for coming. Thank you for the organizers. And I just really want to acknowledge the team, all past and present OpenChem members. This has been going on since 2009. So there's a lot of work that has gone into this that made this possible. Thank you.
Thank you, Ilya. All right. Have time for a question if somebody wants to ask.
Hi, thanks for a very nice talk. Have you thought about trying to run all of the potentials in KIM on publicly available databases like Materials Project, Meta, and Google?
So Materials Project, yes. So our whole infrastructure is kind of based on starting with some kind of equilibrium structure. So when you say meta, I'm thinking kind of non-equilibrium fitting data, right? So that maybe doesn't really fit, but Materials Project definitely, and we have the infrastructure to ingest anything that starts with a coordinate file. And we've done the AFlow database. There are 32,000 structures. So just 32,000 is enough for now for us to develop a good vertical slice of our new system.
Okay, let's thank you again. Okay, our next speaker is Mark Decoto from Harvard. And he's going to be talking about improving or lengthening time and length scales with Allegro and NetQuip.
Hello? Okay. So hi, everyone. I'm Mark. I'm from Boris Kaczynski's group at Harvard, and I'm going to talk about some developments in the NQUIP and Allegro machine learned force fields. So first of all, what are NQUIP and Allegro? Well, they're deep equivariant neural network force fields. So if you give them a structure, they're going to predict the energy of that structure as a sum of local atomic energies. And then they predict the forces on each atom in this structure using torch autograd to compute conservative forces. And so what sort of makes these force fields special is this equivariant part. So what that means is that if you give them an input structure, the features that they learn to represent this structure are scalars, vectors, or higher order tensors. And these mathematical objects are going to respect equivariant symmetries. So like if you rotate the input structure, then the internal features are going to rotate accordingly. And then to preserve the equivariance of these mathematical structures, they interact with each other inside of the model using the Clebsch-Gordon tensor product. And so what are the differences between these two models? Well, the key is that NQUIP is a message passing model and Allegro is not. So what that means is that if you give them a pile of atoms, after the first layer, NQUIP is going to learn some node features around some central atom. Allegro is going to learn edge features. And then if you do a second layer, NQUIP does message passing. And so what this means is that the effective range that is impacting the sort of local atomic environment around this sort of teal atom here is growing, whereas in Allegro, it stays the same size. So what that means in the context of LAMMPS is that in order to correctly compute local atomic energies, you need larger and larger effective radii if you have a deep model. And so really that means that you have a lot of ghost atoms or a lot of communication. And so that's sort of the difference. And so what are some advantages of these force fields sort of in the context of the growing collection of machine learned force fields? Well, as equivariant models, they turn out to be very highly accurate and data efficient while staying linearly scaling in the number of atoms of your system. And additionally, because they're sort of working with neural networks and their efficient atomic species embedding protocol, they can handle a lot of different atomic species at once and also basically infinite training data as long as you have a lot of compute. Then if you look at particularly in Allegro, due to its lack of message passing, it scales extremely well. NQUIP also can scale, but Allegro is really designed to be a scaling model. And so at the LAMMPS conference, it's important to know how you use them in LAMMPS. And so we have a special pair style that lives outside of LAMMPS that you can patch LAMMPS with. And then with only a couple of lines inside of your LAMMPS code, they will act as a pair style for you. And sort of as recently as last week, we've now integrated them with LAMMPS ML IIP, so you can test this out as well. And so if you want to get to the point of using an MLFF in LAMMPS, there's a couple of steps. The first step, you have to have some sort of training data that represents your system. Normally, this is some sort of DFT calculation, and you can collect it in a number of different ways. Then you have to train models, and you have to sort of optimize this cost accuracy balance. And there's a lot of different components that go into this part. And then you have to deploy them for inference. And sort of why this part is important is because when you're training them, you have sort of Python code that's maybe not so fast at runtime. And because you're trying to evaluate these models many times, you need it to be extremely fast. So we do some sort of model compilation to export it into C++ so that it runs very quickly. And really the NIQUIP infrastructure for training Allegro and NIQUIP models really focuses on these last two points. And this is what I'm going to talk about today. Yeah, so the NIQUIP infrastructure, and then I'm going to sort of demonstrate it and the new updates within it by using Allegro to train a foundation scale model on the SPICE2 dataset. So earlier this year, we released a full overhaul of the NIQUIP infrastructure. This NIQUIP infrastructure is like sort of separate conceptually to the NIQUIP model. It's like it lives outside both NIQUIP and Allegro. And it's for training deep equivariant machine learned force fields. We've, in the overhaul, embraced an extensible and modular structure. We've integrated with PyTorch Lightning and the Hydra configuration file management, which means that sort of if you're really interested in doing a lot of development or becoming some sort of power user with this code, it's very powerful to iterate and develop quickly. And the new overhaul comes with a number of train time improvements to improve the speed of training and the scale of training, and a number of inference time improvements similarly to improve speed and the efficiency of your models. And mainly these improvements in speed come from using Torch Compile, a new feature from PyTorch that allows you to better export your models into C++. And also the addition of using custom kernels to replace the tensor product that I talked about earlier. And the tensor product tends to be a pretty inefficient operation unless you write some sort of specialized code for it. So we've done that. And really the new infrastructure is designed so that you can keep up with all the cutting edge things going on in machine learning for molecules. So the SPICE2 dataset is a quick introduction. This is a dataset of 2 million frames of organic molecules, and particularly targeting sort of small molecule protein interactions. It's using a hybrid level of theory, and it has 15 elements. And so what I did here is I trained 3 different models that have a different balance of cost accuracy trade-offs. You can see sort of some of the key hyperparameters in the bottom left. And then sort of, so you can get a feeling of how the different hyperparameters affect the accuracy. On this benchmark data set, the large model has about half the error as the small model. So the first thing I want to talk about is how we've improved training. So this is a huge data set, and we're training some pretty large models. So really, we want to be able to parallelize the training process. So we've now allowed you to do distributed data parallel training, which lets you use up to, here I'm scaling to 256 different MPI ranks, and we scale the training costs very well. And then we also use Torch Compile at train time. And so if you compare sort of the solid lines to the dashed lines, we've introduced a factor of 2 to 4 times faster than previously in terms of the training by using Torch Compile. And something that I don't have data for yet, but we now have some special custom tensor product kernels that run at train time because they support the double backwards operation for the 2 different models. And this will improve your training cost and also sort of the memory cost of training even further beyond this Torch Compile. And then I want to talk a little bit about how we're trying to make these models more long-lived. So imagine you spend a lot of compute to train a big model. You want this model to hang around a long time. Maybe you want to put it in something like the OpenKim database, and you want people to be able to use it all over the place, basically. And so, for example, in this case, I'm training models on Frontier, and you use an NIQUIP train command for this, and then at some point you end up with a Torch model checkpoint file. And this file is a little bit fragile because it requires some sort of external environment, like a particular version of PyTorch or NIQUIP, in order to load it into Python and make it a usable piece of code. So we've introduced an equip package, which takes the checkpoint file and it takes all the important parts about your Python environment and puts it into one larger package file. And this is something that you can distribute. You can carry it around to different environments, different machines. It's supposed to really be designed to live for a long time. And from the model package file, you can then use an equip compile to export it to something that you can run in LAMMPS, or you can continue training somewhere else on a different data set, doing some fine tuning, etc. And so now, assuming that I have done some equip compile, I want to show what you can do in LAMMPS with these models. So first, TorchScript is the sort of legacy way to export a model into LAMMPS. And using the small model that I trained on some periodic boxes of water and a single H100, you get this sort of number of time steps per second as a function of the number of atoms. Now, if we use the torch compile with the ahead of time inductor, we can do full graph compilation, we can use dynamic shapes, and we can tune the kernel settings of each operation within the model for the specific hardware that you're trying to run on. And this gets us a factor of, like, depending on your model, 2 to 5 times faster. And then if you put in our custom kernel, you can get an even further speed up. And so, for example, at this point, where the TorchScript model has run out of memory, we end up with a 6.2 times faster model compared to the old version of an equip. And then sort of scaling out, so now we have the same plot in the top left, but now I've added the medium and large models, and we've got AMD and NVIDIA hardware. You can see that as you make a larger model with a larger tensor product, the speed up factor gets larger, and sort of also critically, compared to TorchScripts using Torch compile and the custom kernels gives you a significantly more memory efficient model. So whereas the large model here is like running out of memory after about 50 atoms or something on this MI250X, we're able to get all the way out to a couple thousand with the large model. And the small model and medium model, these plots are truncated, but they go out to around 20,000 or 30,000 atoms, respectively. And then lastly, we want to show that Allegro can still scale. So using Frontier and Perlmutter on some biological benchmark structures with 25,000 or 400,000 atoms, we're able to scale up to 512 nodes on the 2 machines and hit a top speed of around 200 time steps per second with the medium model in this case. And I will say, if you want to make faster models, you definitely, for your specific applications, is definitely possible. These models are tuned for, like, foundation scale, so they have all the possible bells and whistles for accuracy. So in conclusion, if you're a new user, an equipment Allegro gives you leading accuracies as equivariant machine learned force fields. They live in a PyTorch infrastructure and they have integrations with LAMMPS. If you're returning, basically everything that you've done before is now more powerful, faster, and more memory efficient. And if you want to see more detail, you can see our preprint from earlier this year. And so thank you for listening. Thanks to all our funding. And this was really a team effort with the whole group, basically. And the lead developers of the effort are Chunwei and Albie. So if you have any questions, please.
Okay, let's thank Mark. Okay, question or two? You can come to the mic, please.
I have one general question, like, can these ML, like the force fields you showed, like the potentials you showed, can be used for like studying the reactions? Is it possible?
So these particular ones, the SPICE dataset does not have any reactive structures in there. But if you train it on a dataset that does have reactions or something, like one of the other foundation scale datasets, or you augment this one with something else, you for sure could do reactions.
So if we get like data set from the DFT, which studies the reactions, we can train them for.
Yeah, as long as it's in domain for your training data set, the model should be able to handle it depending on the hyperparameters.
Okay, because currently I'm using ReactSF for studying the reactions. So I just wanted to know, like, if we can use this and compare the results.
yeah, if you're interested in reactions, this is definitely a good way to do it.
Thank you.
Okay, time for one more question if anybody has one. Okay, thank you, Mark.
Thanks.
All right, our last talk of the day is virtual. It's by Gonzalo dos Santos, University of Mendoza in Argentina. And he's going to talk about an application of spin lattice dynamics.
Thank you. Can you all hear me?
Yes.
The slides, is the presentation showing?
We can see the slides too.
Okay, thank you. Well, first of all, I would like to thank you for letting me to share my work here. And I want to acknowledge our collaborators on this project, Flavia Gómez Albarracín and Diego Rosales from Universidad de La Plata in Buenos Aires, and also Carlos Catania, Tania Parlanti, and Emiliano Flores from Universidad de Cuyo here in Mendoza also. So I will be talking about skirmions that Eduardo already presented them earlier on his talk. But they are basically these vortex-like spin structures with interesting topological properties. Due to this topological protection, they are pretty stable structures. They are small size and they can be manipulated with low currents, orders of magnitude lower than those needed to manipulate, for example, domain walls. So for those properties, they are being proposed as candidates for next generation memory devices, like, for example, these skirmion-based racetrack memories. When you would replace, let's say, domain walls or domains for single skirmions. So there is a need to find ways to manipulate skirmions, make them more stable, move them, carry them to other places, etc. Well, Eduardo and also Mitch, they give a very good explanation of what is this spin lattice dynamics implemented in the spin package of LAMMPS. So I will give just a brief overview of it, but basically you can think of it like a combination of molecular dynamics and spin dynamics, right? So as Mitch already said, this is implemented by adding like a spin vector, a magnetic moment to each atom. So you end up with an atom described by three vectors: position, its momentum, and its spin. And then you have this spin lattice dynamics Hamiltonian, which is basically a classical MD Hamiltonian plus a magnetic Hamiltonian, which can include many magnetic interactions, anisotropies, etc. One of them is the exchange, this Heisenberg-like exchange interaction that is crucial here for the coupling between the lattice and the spins, because you see here that the intensity of this interaction depends on the interatomic distance. So you end up with these coupled equations of motion where spins are affected by atoms' positions and movement and vice versa. So let me just introduce you to the model that we are based on. This is the model that studied previously by our collaborators from La Plata. They mainly studied this system through Monte Carlo simulations, but it's basically a Kagome lattice and spins interacting through this Hamiltonian right up here. So you have exchange interaction. You have the interaction with an external magnetic field along the z direction, perpendicular to the lattice. And you have two separate terms of the Losinski-Morilla interaction. One in plane, these black vectors drawn up here, and one out of plane, these red vectors drawn up here. And if to this particular model you add these particular values of the parameters, this particular set of parameters, you end up with this phase diagram, which is more or less a typical skirmion phase diagram where you have this skyrmion crystals area painted here in red, where you will see like skyrmions perfectly ordered. You have this helical phase, typical for many systems that hold skyrmions, and at higher magnetic fields, you end up with field polarized phase where all spins are pointing in the field direction. But the particularity of this model is that you have here this like skyrmion fluid phase, where you have like diluted skyrmions acting like a liquid or a gas of skyrmions. So that's the model we are based on, and we are going to apply spin lattice dynamics to this model. Particularly, we were interested on applying strain on this lattice, on this Kagome lattice, tensile and compressive strain, and see how can we control, modify the phase diagram or some skyrmion properties. So basically, that's what we did. We did a uniaxial strain along the x-axis, which is this axis on the Kagome lattice. So how spin lattice dynamic will capture the effect of this strain is through the interatomic distance dependent exchange interaction. And here you have to pick some functionality for this function. Since we're not simulating any particular material, we choose to simulate this like a function similar to that of iron. So if the lattice is strained by 10%, the proportional change on J is the same that it would feel an iron sample. So Eduardo already showed this, but I can show it again. So we are here on this point of the phase diagram where we have this skyrmion fluid, and we applied strain at different degrees on the lattice. So by tensile strain, we see that the number of skyrmions is reduced. Then we found these, like we like to call them fried egg skyrmions, and then we end up with this apparently disordered phase. But I will come back later to both of these phases to explain a little bit more. And when we do compress the lattice, the overall effect is that you get more skyrmions with a larger radius and apparently more stable. So moving on to more quantitative results. Here you can see clearly that compressive strain increases the number of skyrmions and also their size. And tensile strain has the opposite effect. But here we see this peculiarity effect here when we found these fried egg skyrmions. Again, I will come back to that later. And then if you focus, for example, on a compressed state, let's say at 8% strain, and then we increase the temperature, we see that by increasing the temperature, we still have some skyrmions, smaller skyrmions, or small reminiscence of skyrmions. So we're showing here that strain can stabilize skyrmions at higher temperatures, which is desirable for many technological applications. And here I show you like the complete or semi-complete phase diagram of strain versus temperature. We have a strain here on the vertical axis and temperature on the horizontal axis. And what you can see is basically what I have been telling you overall this talk, that compressive strain tends to produce more skyrmions, more stable, and increase their sizes. When you with tensile strain, skyrmions tend to disappear. And then we found for some region of strain and temperature, these strange fried egg skyrmions, but they turn out to be anti-skyrmions. So we have found here like a phase transition between a skyrmion state and an anti-skyrmion state driven by lattice strain. And if you tensile with sorry, with higher tensile strengths, you end up with this apparently disordered state, which is not really disorder. Well, here you have like an order in every plaquette of the Kagome lattice. So we have found here another phase that we call like umbrella because of the configuration here of the magnetic spins. And we have also here simulated this, this neutron scattering simulations. Well, this is what a neutron scattering experiment would see, right?
Gonzalo?
And here, yes.
Gonzalo, just wanted to let you know you've got 5 minutes left.
Yes.
Thank you.
Yes, I'm just finishing. Don't worry. So here I have this complete phase diagram, strain and temperature. So we have this Skyrmion lattice here. If we compress the lattice, we end up with diluted, elongated Skyrmion lattice. At higher temperatures, we still have a Skyrmion. We see this Skyrmion fluid. And there is a particular region of this phase diagram where we found anti-Skyrmion, where we found an anti-Skyrmion lattice. And then there is another region where we found this, Skyrmions are lost, but we have this umbrella type phase that is similar like a chiral spin liquid or something like that. So I'm just going to move on to the conclusions. We have found that among other applications that we have studied in the past with spin lattice dynamics, is also appropriate for studying Skyrmion dynamics. Skyrmions, we can control Skyrmions with a strain. We can change its size, number, density, phase. Also, as Eduardo showed, we can change its dynamics, its velocity, its diffusivity. And compressive strength helps stabilizing a Skyrmion at higher temperatures, which is really important for technological applications. And with tensile strength, we found an Skyrmion anti-Skyrmion phase transition followed by this plaquette order on this umbrella phase. So that's it, and thank you very much for your attention, and I'm open to questions.
Thank you, Gonzalo. Let's thank him. We have time for a couple questions, either here or online. Nothing online? Yep, somebody's coming up. Just turn the switch on top, pull it towards you to make sure it's on.
All right. So as someone who has like no background in skyrmions, could you maybe explain like how anti-skyrmions are different from skyrmions and how they can be used in data compared to just regular skyrmions?
Did you hear that, Gonzalo?
Okay. Yes, I hear perfectly. Okay, so skyrmions are different from anti-skyrmions because they have opposite chirality. Here you have this, how the scalar chirality is calculated. We calculated for this skyrmion, for this, I'm sorry, Kagome plaquette. And I have an extra slide showing that the skyrmions are found, sorry, this is not the one. Here. You see that here is the chirality plotted against strain. So for these strains, chirality changes its sign. It becomes positive. So this is a sign that you have anti-skyrmions. So that's how we found that there are anti-skyrmions. And about the technological applications of anti-skyrmions, I really don't know about that. Sorry.
Okay. All right. Well, let's thank Gonzalo again.
Thank you. Bye-bye.
Bye-bye. Okay, so that ends our session. I just want to remind you before we close that tomorrow, right after lunch, we have 4 breakout sessions. And today you've heard 15-minute talks by all 4 of the people who are running those breakout sessions tomorrow. So that's Ilya just a few minutes ago about OpenKim, Lucas Hale earlier about the NIST repository, Peter Intfeld about his enhanced Monte Carlo package that works nicely with LAMMPS, and then Ethan Holbrook and a collaborator, I think it's Juan Carlos Verduzco. They're from Purdue, and they're going to talk about the large language models, leveraging AI to try to write LAMMPS input scripts for you. So if any of those topics were of interest to you today, as you heard the short talks, you can come to the breakouts tomorrow for the long version. Okay, so does anybody, Stan or Aiden, want to say any more about dinner plans?